Good morning. Welcome back to the day 2 of Underwater Robotics Workshop UWR 2026. I trust that yesterday's technical session and laboratory visit and interaction provided valuable insight. May I request everyone to kindly take their seats as we commence the technical program of day 2. Today's session will explore recent advances in vehicle design focused on autonomous vehicles. The session chair is Dr. Varikesh Kumar from IIT Kanpur, and the co-chair is our very own Mrs. Nidhi Varshne. Over to you, ma'am.
Thank you, Anand. So good morning, everyone. Welcome to the second day of Underwater Robotics Workshop. I hope you had a very wonderful day yesterday, and we are going to start another fruitful day today. So I have chairing with me Dr. Varikesh Kumar from IIT Kanpur, who will be chairing the session for autonomous vehicle. We have 5 talks in this session. I think Captain Nikunj is not there, so we have 4 talks in the session. Dr. Varikesh Kumar is an assistant professor in Department of Mechanical Engineering, IIT Kanpur. His research focus is on advanced manufacturing processes, thermal and multi-phase systems, integration of transport phenomena with engineering application, heat transfer, fluid dynamics, and phase change phenomena. His key contributions are in research on complex thermal systems in manufacturing, development of advanced material processing techniques, bridging fundamental science with practical engineering solutions. Over to you, Dr. Kumar.
Thank you, ma'am. Yeah, so we'll welcome our first speaker, Mr. Rajeshwar Reddy. Yeah, please join me in welcoming Mr. Rajeshwar Reddy to deliver his talk. Okay. Yeah, please join me welcoming Mr. Rajeshwar Reddy to deliver his presentation. And Dr. Rajeshwar Reddy has expertise in autonomous underwater vehicle system, naval platform integration, defense production and manufacturing, digital transformation in naval programs. He is going to deliver his talk on AUV's technical challenges and achievements. Thank
you. Good morning, distinguished guests, research community, industry partners, students, and guests. I am representing L&T, and my name is Rajeshwar Reddy. My colleague Amay Soni couldn't travel because of these travel restrictions, and I am here to present the technical challenges and achievements of our AUV. The agenda for this coming 15 to 20 minutes is the overview of the vehicle, the design philosophy, and the mission context, AUV design life cycle, key technical challenges which we faced, and subsystem deep diving, validation and test results, achievements and conclusion. This is the AUV which I am going to talk about. This is a 3D image. The length of the vehicle is 1500 mm and diameter is 240, and it's a man portable less than 50 kg. Further deep diving into the vehicle overview, it's made out of 3 sections. Section 1 is the payload section, which is acoustic, transducer and hydrophone, and it's a free flooded area. And the second section is a watertight section, which is housing of battery, electronics. And the third section is of propulsion. This vehicle is depth rated of 150 meters, and which is having greater than 4 hours endurance, and which can attain maximum speed of 8 knots. And this vehicle can be launched from ship deck or halo. Up to 50 meters, we can launch it from 50 meters. The philosophy which was there before designing this vehicle was to meet the defense standards. As I said, it is man portable, and keeping the future interests in mind, so we have adopted a customizable design. And the target was to increase the indigenization greater than 85%. Also, we should keep it low cost because the numbers are high. And the one more is that we need to increase, the scalability was also in mind. And the other feature is selectable expandability. So here this was designed for Navy purpose, so it was an expandable AUV. Primarily the architecture consists of 4 boards, which is a vehicle controller, is the brain of this vehicle, and the power distribution board, servo power board, and acoustic board. And the mission context is mainly for the training the sonar operators and ASW training purposes. And the acoustic signature is of active and passive for multi-scenario training fidelity. Mainly, this vehicle will help the Navy for its operational readiness without risking the assets. And the profiles which it supports is straight line and customizable speed, depth, and heading. And triggered evasive maneuvers also is programmed in it, which is varying depth and heading. Also, random drift also is customizable in this. As I said, this acoustic signature profile is also keeps varying based on the mission profile of the user. And these are the design lifecycle decision gates which we have overcome during our journey. So since it is a low cost, we have limited options with respect to the communication. So this was a very big challenge for us during trials. And we anticipated the trials will conclude within 6 months, but it has taken us 1.5 years to reach to TRL-8. And energy. So within that space, we have to achieve more than 4 hours endurance, that too at varying speeds. So this was also very challenging, and we had to model and then customize our battery to this use case. Material selection was also one criteria, whether to go with CRP or aluminum or any other material. So this also played a major role. Stability and integration challenges, as we know, it is rated for 150 meters. So the tolerances plays a critical role. Obviously, this cable routing within that space available was also very tremendous task. And within all these power systems, maintaining this EMI EMC without affecting our navigation was also a big challenge. And since acoustic is there, the payload, the acoustic card generates a lot of heat in this. So dissipation of this was also a major challenge for us. And at every stage, we had to open for any modifications. If we open the vehicle, so then the calibration, we had to do, recalibrate the sensors. Since it is mill grade, we had to do the qualification test, vibration, EMC, spray test. So this also, this cycle time of the qualification testing was itself is 3 months. And the validation during our journey, so as I said, it took a lot of time for fine-tuning the vehicle. The PID gain tuning was done in phases. As we go, I'll present it. First in the pool, then followed by lake, then harbor, then sea. So gradually we have improved. And as I said, this vehicle is capable of dropping from the halo. So every subsystem was witnessed at the vendor premises, then at the isolated land, then again at the sea with the dummy, and then with the actual UUT. So it's a phased manner, a lot of administrative efforts, and then it's a challenging activity itself. And if the halo doesn't, if the parachute doesn't open in time, so we tend to lose the UT. So So I'll just touch upon the challenges at the each gate. The design challenges, as I said, we had only Ethernet. So if the vehicle is launched and then to spot the vehicle after the completion of the mission was a tedious task. So we had to position the scouts and then the multiple boats and the multiple observers with the drones and then the cameras. So this was a very challenging task for us. And since it is a low-cost item, we had very few sensors and then low-cost sensors, which also we faced in achieving the required heading tolerances. So balancing the power requirement versus the cost was, we had to keep a high balance on that. So coming to this manufacturing and integration challenges, so what practically we saw is that, so when we give the drawings for the vendors of manufacturing, so they tend to overlook the critical dimensions and they commit high. But after delivery, we understand and then we type test is, we had challenges in it. So it went for multiple manufacturing, remanufacturing, and then we had to sit at vendor premises to understand and then deliver it to our requirement. So since the quantities are less, the value is less, it's a typical challenge when we come to prototype building. And as usual, we had the challenges with respect to the earthing and then grounding issues. So to identify which is causing that issue, we had to run through all the cables, then test it in an open environment, again close, retest. So it's a journey altogether. So testing challenges, we had the leak test challenges. So we had a chamber for testing for 150 meters, that is 15 bar. And we had leaks in it, and to identify from where the leak is there, that itself is again, we had to place the tissue papers and then all typical methods we have adopted to identify where the leak is. And again, diving into the root causes, what was the reason, so then the root cause analysis and the preventive and corrective actions. So every issue was addressed methodically. Endurance trials, the battery testing was done at the vendor premises, and then we tested it with our own load bank, and then coupled with again AUV, again we have load tested it, because this is a critical parameter for our success. The ESS testing, we had our own ESS testing facility, so we have done. And heels validation. So every time before making any changes in the vehicle, so heel setup was there. The changes were done and then the logs were recorded. And after it's confirmed that, yes, now we can make changes on the vehicle. So that's how we have done it. So all the fail case scenarios were identified, what all can go wrong. And those fail case scenarios were injected into the heel setup. And we have eliminated each fail case scenario by changing the software, hardware, and then there are communications between the subsystems. So as I said, the typical validation strategy was first to test it in a heel setup, then tank, then a lake environment, because sea conditions are very harsh and it's not easy to do trials in a sea environment. So that's how we have adopted, so you can see the photograph. So where initially, when we have tried out, it was not following a straight line path. So it was turning towards the port. So to counter act it, so we have placed the weights on the surface we can see. such that the CG is towards the starboard, so it can counteract it. And there's a lake where we have done, we have requested the INS Lonavala for conducting these trials. So we were there, whole monsoon we were there conducting trials in the rain. So ma'am, can you just. So as I said, this was one of the typical land drop with a dummy. We cannot afford to drop it with the actual AUV. So this was done at vendor premises and then done at our Kattupalli L&T facility with a crane. And that time we have recorded all the values, what is the impact, what is the speed it is achieving with the parachute, without parachute. So a lot of analysis went into it. So we can see this is a typical arrangement where we had a fisherman boat had and is continuously with us and then for the trials. So as I was talking more about that's the ESS test and then the random vibration test, impact test, all the tests were done in a qualified QA labs. On the right side you can see that typical heel setup so that the change management or the changes can be done very quickly. So coming to harbor trials, now we have graduated from pool to lake to harbor. So harbor trials, since sea is involved, a lot of administrative clearances needs to be obtained and the dedicated resources has to be assigned. So first, the mission planning based on the area in which the mission is being conducted, the aim of the mission. So we used to prepare DOP and DPI sheets, dive operation performance and dive performance indication sheets. Then the launch and the mission execution was conducted. And the recovery. Recovery is a big challenge since this is not having any communication, as I said. So we had to be very sure that where it is going to surface of the end of the mission. And then we used to be ready or positioned for recovery. And thereafter the log analysis, the devil dies in details. So the log analysis used to throw a lot of information. And based on the logs, the PID tuning or the software modifications, the mechanical corrections, and the electrical changes were done, and the repeat. This is a cycle. Typically, the experience is that we intend to plan something, but the weather doesn't permit, the high tide, low tide, the sea state. And if we are successful in that, then effectively we get 3 hours a day, even we plan early. So that's enormous efforts which goes in doing sea trials. These are typical graphs. You can see early in our early trials, the heading we had issues. It's overshooting. Depth also we can see clearly in the graph in the right side bottom. Thereafter, slowly the performance got improved. And this is the deep sea trials, which was conducted at 65 meters. So absolutely, we have reached to a stage where the results are satisfactory. So I'll play a short video. So this is how the boats for scouting the vehicle, because in sea hardly anything is visible, the small vehicle. The radius stickers are for reflections, so that if we miss the vehicle, then it is easy to identify. So we have strapped the acoustic pinger and then the flasher in case he doesn't retrieve it in the daytime, at least in the night time, that flasher will help. So, we had 10 AUVs. So this is the number of missions conducted and then the operation time for each vehicle. So this we have already just discussed. This is a summary of the issues.
Mr.
so
Reddy, please summarize your.
Yeah. And lastly, the achievement is that whatever we have targeted indigenization, we have achieved. We can see the screen grabs. So my perspective, even though whatever calculations we do, simulations we do, but ocean invalidates our simulations. And space and communication is the key, at least while validating the prototypes. And ecosystem challenges, as we know, everyone, we know that any item for importing, we had to apply for WPC license, we had to apply for BIS certification. So we have to now address these challenges together. And for the reliability, the multiple trials is the only solution. Autonomy is not optional, it's the product. And 85% indigenization is a strategic asset, not a metric. So we had a chance to get away with, reduce this indigenization and be faster, but we have decided that whatever was our target, we maintain that. So we are in this conclusion slide. Yeah. So this enables us for the next generation AUVs. So with this confidence, we are moving very aggressively in this field. So we are targeting high endurance AUVs and XL AUVs. And also with this indigenization, we have achieved this Atmanirbhar Bharat in action for undersea domain. Thank you very much for your patient listening.
Thank you, Mr. Reddy. We have time for two questions.
Number one, your presentation is so generic. Except the drop test, I can make this presentation for any underwater vehicle by any company. So it's very too general. There has to be specific. So there's something for you to keep in future. You're a young man. So see, there's no point making such generic presentations, which can be applied everywhere. Number two, see, you made a statement that ocean invalidates simulation. What does it mean? If you understand the meaning of simulation properly, what it means that we have not simulated it properly.
Yeah.
Okay. Simulation has to really bring out the physical. What is simulation? Simulation is nothing but a mathematical modeling of the realistic conditions. And many times, the mathematical model, you can't derive directly the differential equations because too nonlinear and all that. But in simulation, you create all those conditions. So that statement fundamentally is wrong. You have to do this simulation means I have to capture the physics, capture the things completely. So if you say simulation has failed or ocean simulates, that means I have not simulated properly. Okay?
Yeah.
So that is second part. Thirdly, you see, when you are making, let's say 80%, 85% is, what is that 15%? Actually, focus as L&T should be more on that. So because we have to really make the country, you are talking Viksit Bharat or something like that. So we have to really focus on that. So your presentation has to be a little more sharper in future. Thank you.
question, let's thank our speaker, Mr. Reddy.
Thank you.
Sir, 1 minute. Request Dr. Palniappan to present a memento to our speaker, Mr. Reddy. Thank you, sir. So we have our next speaker, Dr. Shiju John. Dr. Shiju is a key member in high-endurance autonomous underwater vehicles team in DRDO. His research and technical expertise is in experimental hydrodynamics, autonomous underwater vehicles, ocean engineering, and underwater systems. His research focus is basically on development of high-endurance underwater robotic platforms and advanced underwater vehicle design and performance analysis. Over to you, sir.
Good morning, ladies and gentlemen, dignitaries, officers, professors, and students. I thank NIOT upfront, Professor Dr. Vedajalam and team NIOT for giving me an opportunity to speak. Thank you. So this is what I'll cover today. An introduction which will be taking around 5 minutes. The design process we'll be briefly discussing, and we'll touch upon the AV hydrodynamics. And we'll conclude by just looking at the AV market trends, which was discussed yesterday also. So this is, as we all know, this is a classical definition of an AV. It's an untethered underwater robot that is used for various missions with minimal human intervention. And this is where the AV development started. The University of Washington, the Applied Physics Laboratory at the University of Washington, deployed the first ever AV in 1957, which was supported by the Office of Naval Research. So I'm just telling you the background when it started. India was born just 10 years and the world had deployed its first AV. So this is a timeline of the global AV development. Right now, we are looking at the world is progressing towards resident AV systems, which are very intelligent, networked AV systems, and AVs as strategic platforms for naval applications. This is a classification of the AVs by weight classes. All of us are aware. The XL AVs, which are ranging from around 20 tons to 100 tons. Then we have the high endurance, large displacement class of vehicles, heavyweight AVs, lightweight AVs, man-portable class of AVs, and micro AVs. So this is some of the well-known AV systems in the world. I just wanted to show this slide because I just wanted to tell you that there is no single configuration for an AV, as all of us know. It's a design-centric configuration that is required for an AV. All of us are familiar with the Remus class of AVs, which is mostly torpedo-shaped AVs developed by Woods Hole Oceanographic Institute. And the IXC Explorer is also similar configuration, but with a different control surface configuration. These are all flight class vehicles. And then, this R2D4 is a Japanese AV, very interesting shape, different shape is there. Oceaneering has developed the Freedom AV, which is a flatfish configuration, basically for hovering applications. So it has a hovering thruster. And then Hui has also developed the autonomous benthic explorer Sentry class of AVs for deep diving applications. So you can see the configuration is completely different. It has to maneuver in the vertical plane more. Bioswimmer is a biomimetic AV made by Boston Engineering Corporation. Houston Mechatronics has made a very interesting shape-shifting AV. It is like the transformer. So it transforms from a flight class AV into a ROV with a manipulator arms once it reaches the location. And then EELS is an extraterrestrial AV developed by NASA's Jet Propulsion Laboratory for deployment in the moons of Jupiter to explore the icy waters in the moon. I mean, it's not water, but the icy formations. Evologics has developed Quadroin series AVs, again, penguin-inspired shapes. And Eloom, they brought out a resident AV called Eloom S. This is being exploited by the oil and gas industry. Just wanted to bring out that the configurations are so varying, and these are all the extra large AVs that are available in the world. So this is the Indian AV ecosystem. So we have also done various organizations, including the organization I'm representing, have developed various AV systems, and many are under development. So there is a rich AV development history in the country. The ecosystem is there. So this is the autonomous underwater vehicle that NSTL, which I am part of this team. So we are developing it for Navy. It's a multi-mission, high-endurance autonomous underwater vehicle. It's a 6 tons class vehicle. So this has uh, the challenge as well as the advantage here is that we are mostly indigenizing most of the systems. So I can just tell you what is not indigenous, that would be easy. The inertial navigation system and the Doppler velocity log, the CTD sensors. So these are the few things that we are actually importing from outside. The propulsion system, the control system, even the lithium and battery is a transfer technology from NSTL. So that is a scale of indigenization, due to which there are a lot of challenges that we are encountering. This is a video of some of the initial trials we have done in 2024. So this was done in a lake test facility in order to initially study the vehicle dynamics. The vehicle will dive down here. So this, I forgot to mention, there are a number of DRDO labs that are associated with the projects and also a number of industries in the country. So we have developed indigenous sonars. So the front-looking sonar, which is developed by NPOL, is actually doing the obstacle avoidance performance here. The left side was showing the USBL track of the vehicle while the vehicle was diving. And it has surfaced after the mission. The video, yeah, we have done trials at Kochi also. So this is during one of the harsh weather conditions the vehicle was doing the trials. So it's a very robust design that has brought out. So I'll just cut short to the next slide. So this is some of the results from some of the trials that we have done. The first shows the trajectory of a 4-kilometer run and the vehicle parameters. It has dived down to 10 meters and the stabilization in roll and pitch and yaw was very satisfactory. The obstacle avoidance of the vehicle is shown there. The red is an obstacle. The vehicle was taking a lawnmower path and suddenly the vehicle realized that there is an obstacle in front and it has taken a replanning. So this motion planning also, CARE Bangalore is actually helping us, our sister lab. And this is a 100 minutes run, almost covering around 9.5 kilometers with 17 waypoints. This was also a major achievement in which the vehicle could achieve all the waypoints put. And another milestone here is that for the first time in the country, we have developed a side scan sonar and gap filler multi-beam echo sounder, which is done by NPOL Kochi. So this is the first picture shows during a straight run, it has imaged the lake bottom. And then some mine-like objects were deployed at various places in the lake. So during the run, the AEV has actually imaged the mines, and even the multi-beam echo sounder also has imaged the mines. And then the autonomous target recognition algorithm, which is running on board, which was again developed with the help of CARE Bangalore, has actually detected the mines on the fly. So this was a major breakthrough that we could achieve during our trials last year. And this is a sea trial that we conducted this year. In fact, as the speaker before me brought out, sea trial is a very challenging endeavor, and there are a lot of factors associated with it. We could do only one trial because of the ship availability. And yeah, the vehicles, we have developed 2 prototypes. The vehicles are ready, but we're just waiting for the season to be, as all of you know, this is the monsoon season, so the recovery and launch of the vehicle is extremely difficult in these conditions. So coming to the design process, all of us are familiar with this process. We start with the concept design, and then we move on to the configuration design. So concept design, the goal is to select a suitable concept from competing alternatives. And then we move on to the configuration design, where we see how major systems fit together. We see the interfaces, the spatial and functional compatibility. And then we move on to the detailed design, where we look at how the actual vehicle is built. So here we focus on engineering drawings, the component specifications, materials, tolerances, test procedures, etc. And then we move on to prototype manufacturing, trials, and with the results that we obtain from the trials, we move on to the critical design, which is actually a fine-tuned design ready for production. So this is a standard system engineering flow of the concept design, wherein we look at the stakeholder expectations, and then we derive the top-level requirements. We carry out functional analysis of these requirements, and then we go into a sort of a loop wherein the concept of operation, the product breakdown structure, and then the allocated requirements are translated to system requirements. Then we consistently check whether it is meeting the user expectations, and this is a bigger loop that comes in. So this is, the concept design actually is a very important stage, that's why I'm emphasizing here. So this is a basic design spiral which is iterative in nature. So here, the trade-off studies are an important factor here. And then coming to the requirement analysis, we follow the practice of, this is a level 1 product breakdown structure that we make for the autonomous underwater vehicle. Similarly, for each subsystem, we have to go into further levels. And the trade-off studies are an important part of the concept design, along with the feasibility studies. So these are some of the techniques that we use: brainstorming, decision metrics, or the Pew matrix, and cost-benefit analysis, Pareto analysis, QFD. So these are some of the techniques that are important in order to arrive at a proper concept design, because this, you have to spend sufficient time on the concept design in order to avoid revisiting the design at a later stage. So this I want to mention. We actually followed the NASA system engineering document. So the concept of an end-to-end architecture we actually implemented initially itself. So how it helps different stakeholders upfront during the early stages of design to understand what is the flow of information inside the vehicle. For example, the person who is developing the side scan sonar, he would like to see how the sonar configuration will be preset before the mission, and during the mission to what he will be communicating. So all these things are captured in this end-to-end architecture. This helps during the design stage. Coming to the configuration design, it is important to quickly estimate the hydrodynamic parameters, the control parameters, the weight buoyancy balance. Then we have to make a detailed 3D arrangement of the vehicle to see the spatial and functional compatibility of the subsystems. So here, mainly we'll be looking at the interfaces pertaining to the mechanical systems, the electrical systems, and of course the inter-system communication. And coming to the detailed design, at the detailed design stage, our technology readiness level will be around 2 to 4. So wherein we do the subsystem design now. So we go into the details of subsystem design, and then we prepare the interface control documents. The hydrodynamic model test is done at this stage when the configuration is finalized. And we also extensively used sim to real, simulations to reality. So here we have used actually the Ross Gazebo extensively in order to fine-tune the motion planning system and also the obstacle avoidance capabilities of the vehicle. This was, in fact, helped by CARE Bangalore and also the control plan design. So this is kind of a minor loop that comes in there. Extensive simulations were done before actually going to field. Then we move on to the mechanical part. The engineering drawings are done with the help of FEM analysis. We fine-tuned the structural design. The wiring and connectorization, thermal analysis, and to some extent, we do a design optimization. Being the first design, we try to make it more robust than an optimal solution. And of course, the qualification tests and environmental specifications are finalized at this stage. Then we move on to the prototype development. Our Cochin Shipyard Limited is our industrial partner. So we have our integration bay there. We have, these are the integration jigs that you are seeing, which is used to integrate the high endurance autonomous underwater vehicle. A snapshot of the trials. During the trials, we do the measurements, then we do a performance analysis and fine-tune the design, and this is again an iterative process. During this process, we fine-tune the design and again go for the trials. So then follows the critical design, wherein the design is fine-tuned and finalized. We go for a technology demonstration. Once the user is happy, we go into the production version, wherein the TRL reaches around 10. So coming to the third part of the presentation, I'll move on to the AEV hydrodynamics. So as all of us know, the AEV dynamics is a highly nonlinear and coupled phenomena. So a control system is designed, required to be designed for trajectory tracking. So in order to implement this control design, we need to mathematically model the AEV. And the important part here is that the hydrodynamic coefficients, which are the parameters in the equation, have to be evaluated. So these are the coordinate systems that is followed for underwater vehicles. There are two coordinate systems. One is an inertial frame and a body fixed frame. So as all of us know, the velocities and forces are calculated in reference to the body frame, and the position and orientation of the AEV comes with respect to the inertial frame. And these are the assumptions. We consider it as a rigid body, which is a fairly good engineering assumption. The Earth's rotation is negligible. The primary forces act on the AEV at the center of buoyancy. So these are the standard notations depicting the forces and moments, the linear and angular velocities, and position and Euler angles. So hydrodynamic coefficients, we all know, we follow the Snam notation. So they are nothing but partial derivatives when you expand the forces and moments as a Taylor series expansion. And another important factor is that when you have to translate the forces and moments from the inertial frame to body frame, we use Euler angle transformation. So these are the two significant things to be noted. And this is a famous Poisson's equation, which is describing the sixth of nonlinear dynamic equations of motion. I'll not explain what it is. It's just a textbook thing. You can follow any book like Poisson or anything. You can And this, by deriving, applying the Newtonian-Euler formulation, you actually derive the nonlinear coupled equations of motion in 6th. So these are the equations that we have seen in the 6 degrees of freedom. And the important things to note here is that what are the hydrodynamic forces and moments of interest? So we basically look at the added mass due to fluid inertia. These are the coefficients that come under it. And the hydrodynamic damping due to viscosity, which is due to skin friction and vortex shedding, and the restoring forces due to the weight and buoyancy of the vehicle. The propulsion forces due to the thrusters, the control forces due to rudders or thrusters, and of course the environmental disturbances. Now the important question is, how do we determine these hydrodynamic forces and moments? So in the early stage of design, we always use analytical and empirical methods for a quick estimation to cross-check your design, particularly during the concept design stage. We can also use strip theory to quickly estimate the added mass coefficients. And CFD nowadays is extensively used, but of course, as all of us know, CFD takes time and CFD needs resources. So once the design is mature, we can invest on CFD. CFD is used for, and most of the hydrodynamic coefficients, like added mass terms and all, it gives with a lot of confidence nowadays. And of course, the experimental methods. It is the most expensive and resourceful method among all these. So at NSTL, we have a towing tank wherein we use a vertical planar motion mechanism in order to derive these hydrodynamic forces and moments. And some other facilities which are existing elsewhere, like we can also use a rotating arm facility to get the rotary coefficients. And some places they use water tunnels, and we can also use wind tunnels for the flow visualization and the static hydrodynamic coefficients. And another technique that can be used for smaller vehicles, if suppose you don't want to invest on hydrodynamic model testing, it's not mandatory. You can go for system identification. You can actually look at a similar AEV, derive your coefficients, and then go for an open loop control experiment, and then fine tune your coefficients. People are nowadays using even neural networks for this process. So this is actually a faster route, whereas the experimental method is actually very traditional approach. And it may not be necessary unless your AEV shape is totally different from what is actually existing, or it is a new thing that you're trying out. So these are the hydrodynamic test facilities at NSTL. We have a high-speed towing tank. It's a 500 meters long and 8 by 8 meters cross-section. And there is a seakeeping and maneuvering basin, particularly to generate sea states, to study the hydrodynamic performance of ships and underwater vehicles at the model scale. And then there is a open circuit wind tunnel to study the pressure distribution and flow distribution of underwater vehicles. And there is a cavitation tunnel, which is used for studying the cavitation performance and the hydroacoustics characteristics. Of course, these are the specifications of the CFD setup that we have at NSTL. We have a quite good CFD team. Now, concluding the hydrodynamics part. So these are certain, thumb rules that are used to check the stability of the vehicle during the initial design, wherein this is the equations which determine whether the vehicle is stable in the horizontal plane and vertical plane without any control action. So I'll not go into the details, the time does not permit me, but this is actually a thumbnail, you can use it. And what are the variables here? Typically for an AEV, to play with these hydrodynamic coefficients and improve your stability of the vehicle, you can actually play with the rudder design, you can actually play with the form design of the hull form, and also the location of CG with respect to the center of buoyancy of the vehicle is an important criteria. Now coming to the drag part of it, a streamlined vehicle, streamlined hull form gives you the least resistance, and this is a very important factor for a high endurance vehicle. So as all of us know, an elliptical nose and a parabolic tail is theoretically the best solution, but when it comes to actual practical design constraints, we have some limitations there. And it is important to streamline because you can see the drag coefficients in a bluff body case and a streamlined case. There is so much of variation. And coming to the length to diameter ratio or the slenderness ratio of the vehicle, around 6 is optimal from the drag point of view, but when you consider the controllability and the handling of the vehicle, 7.5 to 8 is considered ideal, but there are designs which deviate from this because we have very robust control architectures in place today. Now I'll conclude with this global market scenario. If you look at the global market, this is the deployment scenario across the world in the year 2023. So the North America and Europe substantially captures the market, but there is a significant demand in the Asia Pacific region also. Okay, so the global AV market in 2025 is around $3 billion US. And the market is entirely captured by around 15 OEMs, which are from North America and Europe. So this is an eye-opener. Asia has a rich AEV R&D history, particularly the Japanese. The Chinese have pumped in after the 2000s. India is also trying. South Korea, Singapore. But hardly there are any AEV products in the market that come from these countries. This is due to various factors. And China is actually aggressively venturing into AEV and underwater vehicle development. They are the largest operator of deep sea autonomous underwater vehicles at present. More than 44 universities in China are working on more than 150 research problems related to AEVs. That is the scale that they are working on. And the 3 state-owned enterprises, they are extensively pursuing AEV development. So the question for us to reflect, in fact, we had enough discussions yesterday. What are we going to do to meet those expectations and match the global standards? We need to create a demand, because the US and the NATO countries, they have extensively supported the OEMs and the research organizations who brought out skilled manpower. Those ecosystems demanded the AEV generation, particularly the oil and gas industries in the Gulf of Mexico and also the North Sea. They have created tremendous demand for the AEV. So this is something which we need to replicate in the country. Otherwise, our OEMs may not be able to survive. Thank you. That's all from me.
Thank you, Dr. John. It was a wonderful presentation. We would like to have 1 or 2 questions from the audience.
Commodore Dalbir from Director of Submarine Operations. Thank you for your presentation. As I understand, NSTL is already working, has experience of last 40 years at least on torpedoes. And difference between torpedo and AUV is only, I think, minor speed and the autonomy part. So your research, your presentation shows more of the research on your hydrodynamics part, which is, I think you have enough institutional knowledge there on hydrodynamics of an underwater vehicle. What research has been undertaken in the autonomy part? Because that is one of the critical technologies where we should research, because nobody will give you. And that is where indigenization will happen. So, and the second point that you made, again, I come back to my yesterday's point, demand. How do we create demand when there is no product? If you have product now, government is allowing you exports also. But if you have a working product, you will have demand, at least in our Southeast Asia or Indo-Pacific region. So 2 questions. What is the status of indigenization of autonomy? And demand part is just a comment, it's not a question.
Understood, sir. So the first part, as you rightly pointed out, we have been working on torpedo systems, but there are a lot of differences from a torpedo system. Torpedo is a weapon class system, so it is hardly used for, say, the deployment time is 1 hour. Whereas AEVs like this, it is a vehicle class. So this is fundamentally the philosophical difference that we tried to bring out in our lab itself. We had an internal struggle to make people understand AEV is totally different from a torpedo system. So autonomy is a major factor there. And we have a very good embedded systems team, a group of youngsters led by actually Suresh sir is there. So he has actually, they have developed our own autonomy software stack within NSTL for HEAV as well as the man-portable class of AEVs, which they will be presenting in the next session. So this is, I would say, tremendous efforts have been put in, and we have got very good results. In fact, CARE Bangalore also helped us a lot in the motion planning part. Because when it comes to autonomy, one of the major part is the trajectory tracking and autonomously avoiding the obstacles and carrying out the missions. So this part also, we had a good association with CARE Bangalore, and some startups helped us in this. But as you rightly said, we have some distance to cover when it comes to the actual autonomous missions. For example, the mine detection we could achieve with good confidence so far. But some other missions like detecting a submarine. So it is more to do with the sensor performance rather than the autonomous part of it. Autonomy, we have fairly a good strong grip with NSTL, and we have also discussed with NIOT during their initial ventures, and we have given them leads as to how to progress and all. So this is something we have actually worked in the last 5 years, and we have full confidence in our teams. The second part of it, I think it was discussed enough yesterday, the demand, and so I'll not talk about it.
I just to supplement, One is, see, he has only presented mine countermeasures, but Navy has given us about more than 7 or 8 mission requirements which are to be incorporated. That's how this is totally different from torpedo, which we cannot disclose everything here, but many missions we include. Like that's the reason why he has shown radar, many things he has shown. All those things are included, and it's an integrated. It's especially the heat, thermal, and power management was also difficult. And autonomy, we actually planned autonomy for a totally different purpose, for which it is ESA Delhi did the complete environmental planning. Like Goel sir was saying, simulation to actual condition. In this case, what is simulated and what we found in sea, we were exact. For different sea states, we have done it. So this is one more aspect which was done. That's how the autonomy has become very strong in this factor. And those things will come out when time comes, when the actual scenarios happen, those things will come. But one thing I'm still not satisfied is, we wanted the power management to go to PFM-based, fuel cell-based power management, so that your endurance of 45 days, what we want achieved. But that should have come in rather than still going to the old lithium-ion battery, which NMRL, I think, has made the module and it's not yet been integrated. That has to take it. But second thing is, we also done excellent artificial intelligence in the man-portable farms. I think I personally know it's one of the best AI-based systems that we have built. How to integrate this bigger one to the smaller one to give the entire maritime security? Because now you can actually run 15 or 16 AUVs, small AUVs, so it can be attached to it, or it can stick to it. What people do is they stick to it, it can be released, and it can be networked. Then you can do a larger area cover operations. And that will be very helpful when there is an intrusion detection system which we are planning. Yes. So this can be thought about it.
Yes, sir. Definitely the networked AV is the future. I mean, working in silos, whether AV development or actual deployment scenario is not going to work out. So.
I forgot about the market process. What we have done is parallelly we established this. So this one was done as a concurrent engineering, where the entire production setup at CSL was established. In fact, CSL opened a different complete area group where we have production lines have been established, and we also told the CSL business development team to look at the global market also. In fact, we wanted them to compete even with the Blue Whale.
Thank you, sir. Maybe we can have further discussions during the lunchtime. I request Dr. Vedachalam to present a memento to Dr. John, please.
And I thank NIOT for giving me an honorary doctorate. I have not registered for the PhD yet.
Please join me welcoming Dr. Abhilash Sharma, Associate Professor, IIT Madras, Ocean Department. So he has 50 plus publication in international journals. He has expertise in marine robotics, autonomous marine vehicle, guidance, navigation, control systems, reinforcement learning, and AI for marine system, collision avoidance, and intelligent perception systems, hydrodynamics, and multi-agent marine systems. Yeah, please go ahead.
All right. Good morning, everyone. So thank you very much for NIOT to having given this opportunity to me to present on this idea. So I was given the topic, guidance, navigation, and control frameworks, and while I was debating on what I should present, because the conference here is called Underwater Robotics, but whereas my lab primarily works a lot on surface vehicles. We work a lot on autonomous surface vehicles, and we are venturing into underwater vehicles recently, but the principles which go for guidance, navigation, and control map out to be the same between both these vehicles, with some differences, of course. So I think I'll spend some time to talk about the 3 blocks of guidance, navigation, and control, how that ties up together into the autonomy. But we will restrict to or see more examples in terms of surface vehicles and ship-shaped structures, which our lab has experimented more with. Okay, so We'll start off with a little bit of understanding of why there is a need for an autonomy for vehicles, and followed by how does the guidance, navigation, and control structure favor the autonomy paradigms. And then I'll leave you with 4 different examples. I'll try to show you that how can we do path following with traditional and artificial intelligence-based methods, and followed by collision avoidance using traditional and artificial intelligence-based methods. So the takeaway primarily should be that at the end of the day, the guidance, navigation, and control framework is the one which we can build on top of different layers in order to achieve different levels of autonomy. Okay, so the motivation for autonomous ships. So this is a study which was conducted, it's almost conducted every year, and this shows you what are the different reasons for the different marine incidents out there. So accidents, casualties, different types of incidents where damages have happened. And if you look at it, one primary area jumps out of there, which is the human erroneous action. So whether we like it or not, human is the part of the reason why several of these incidents are occurring. Now, when we look at it, the primary motivation for autonomous systems is whether can we reduce the human risk, or kind of, let's say if we are looking at mundane operations which are repetitive in nature, can those be outsourced to an autonomous system so that these risks can be mitigated to some extent? Sorry. Okay, my slides are not moving for some reason. Okay. Okay, so primarily when we look at autonomous operations for ships, the main idea is to see that whether we can outsource the mundane operations, but we want to maintain remote operation for critical infrastructure. So specifically when we are having critical cases where a human is still supposed to be in the loop and we can't really do away with that. And this is where we differ significantly from autonomous cars. So autonomous cars may have the flexibility to say, hey, we will go completely driverless and no need for any monitoring systems. But ship-shaped systems or anything that we put in the ocean is definitely going to require some level of human in the loop will be necessary. Whether they are actually actively participating in it or not at every time would be a portion which will determine what a level of autonomy you have. But the idea of a human in the loop will definitely be required at all times. Now, as of currently, you do not have any fully autonomous ships operating in international waters, and that's not because that technology is not available. The technology is available. It's the regulations and the framework for regulations which are not fully in place. In fact, you'll see that very recently, in fact, 2 weeks back, IMO has come up with the MAS code, or Marine Autonomous Surface Vehicles Code of Conduct. And it's at least a step in the right direction of understanding what is safety, how do we appreciate safety, and if we want to go into international waters, what are the liabilities associated with when something happens with an autonomous vehicle being involved in it. So those are the main reasons why we don't see a fully autonomous vehicle plying the international routes. But there are several localized within one country vessels which are plying in the autonomous areas. This includes container ships, which are transporting about 40,000 containers from one side of Norway to the other side. And probably this has been in operation for 2 years now, and they're really looking to get into a fully autonomous operation soon enough. And in other examples, you have ferries, which allow you to cross over from small inland ferry waterways and other things. Those are also fully autonomous because the regulation is a little lenient in the sense that you are within one country's borderland. Okay, so we'll try to understand the framework for the autonomy, and we'll see what is the need for this guidance, navigation, and control blocks, and how do we tie on top of this, and how do you develop autonomy in this particular framework. So I want you to draw your attention to the very right side of the block, which says the vessel. So this could be either an autonomous underwater vehicle or a surface vehicle, and this is going to be operating in some environment. And the environment will be ocean, which is going to be laden with disturbances. And the disturbances can be in terms of wind, waves, or currents of different categories, which will determine what is happening to the vehicle within the environment. Now, we want to control this particular vessel to do what we want it to do. And that's the whole reason why we need an autonomy in the first place. So the first step of the autonomy paradigm is to figure out whether the vehicle can know where it is. And that's the problem of navigation. The navigation really talks about the idea that whether can we figure out whether the vessel can know where exactly it is. That will be complemented together with the guidance block, which will tell us where the vehicle should be. So the guidance block answers the question, where should the vehicle be? The navigation block answers the question, where is the vehicle currently? And the difference between them, the error, or the so-called difference between them, is what the controller is trying to reduce to zero. And that will eventually lead you into a loop of this feedback loop, where you're looking at the error and trying to get the error to zero, and will lead you to whatever you want to achieve. And in most cases, you will see that all levels of autonomy will be looking at some such framework or building on top of one level of framework beyond the other in order to achieve the different levels of autonomy. Okay, so when we are tasked with a task to actually look at any of these systems and want to develop a control navigation or a guidance framework for it, the first thing to do is to probably look at simulations versus experiments. Obviously, we are always interested in doing simulations first because it's a low-risk environment and you can actually tune your systems much better in the low-risk environment, but it comes at a cost that it is having only simplified dynamics of what really happens in the ocean. And you want to move from the simulations to the experiments, and the experiments are where you have moderate to higher risk. There's a risk of a loss of a vehicle which can happen, and you want to validate your algorithms in the field where the true dynamics is present, which means whatever you simulated versus whatever you did in experiments, there may be a mismatch between the dynamics, and you want to understand that dynamics well. So a natural progression for any control engineer is to start at the simulation level and go towards the experimentation paradigm. So we too in our lab have our own simulation stack which we have developed, and we try to develop everything here from scratch because we are interested in making a total control of the vehicle. So we won't want to go back and look back and say, somebody else wrote the code and that did not work for us. We definitely want to be blaming ourselves when it doesn't work. Okay. All right. So the natural progression to a simulation system is what we call as a digital twin, and we'll talk a little bit more about it later down when we show you some examples. The idea is that you can maintain a digital logbook of your vehicle, and the idea is you are feeding your sensor information into your simulation model, and that allows you to figure out when your expected outcomes and your actual outcomes differ from each other. And then when they do, you have a pertinent question to ask, why do they differ? Is it the physics which is different, or is there a faulty sensor, or is there a faulty actuator? And that is what the digital twin concept really allows you to go forward with. And the natural extension is that if you want to train your crews, or if you want to be able to test your autonomy algorithms, these environments really help you a lot in failing fast in the simulation model before you actually even touch the field deployments, so that you can minimize the number of times you actually fail in the real world. Okay, so coming to the sensor stack, so we do have to have different types of sensors, and not all sensors measure everything. So for example, inertial measurement units measure accelerometers. It has accelerometers which measures acceleration, has a gyroscope which measures angular velocities. You have GPS coordinates which give you positions. If you underwater, you do not have GPS and you have to rely on DVL where you actually have only velocity measurements being present. In addition to these, you also have what are called perception sensors, which means you try to perceive the environment in which you are, and that comes from cameras, LiDARs when you're above the water. Under the water, you have cameras and sonars. Obviously, under the water, you have a lot more challenges, especially with cameras, because you are going to have an attenuation which is going to restrict you to see how far into the water that you can see. And sonars are the only primary way that you can see really far away into the acoustic domain, or especially inside the under the water. Now these sensors which give out these different information needs to be fused together in order to understand what is the current position of the vehicle. When I say whether the vehicle knows its current position or not, I'm really talking about 4 different quantities. What is the position of the vehicle? What is the orientation of the vehicle? What is the velocity of the vehicle? And what's the angular velocity of the vehicle? These will determine whether I know the complete state vector of the vehicle or not. And that would require us to fuse these different estimates coming from different sensing modalities, in addition to the fact that you know something about the physics of the vehicle as well. And this natural progression happens through the sensor fusion module, and we typically use what are called extended Kalman filters. They have become the industry standard these days to fuse different estimates together. People have gone for higher order approaches too, such as particle filters, unscented Kalman filters, and others as well. But we see that fairly widely, extended Kalman filters have become the sort of state-of-the-art technology which is currently used for sensor fusion. Following for a guidance and control block, so especially with respect to surface vehicles, even with underwater vehicles, line of sight guidance has become quite the norm these days. And these guidance algorithms have originated quite long back, especially in the defense sector, when they were primarily looking at the idea of being able to do surface-to-surface missiles, air-to-surface missiles, so on and so forth. The idea here is pretty simple. Let's say I want to move from the star on the left side to the star on the right side, and my actual vessel's position is not on the path. The guidance algorithm tries to tell us where should I point my vehicle towards, which is what is defined as psi desired. Let me see if I can actually point this. Yeah. So that is the desired heading angle that you want the vehicle to actually have. And the actual heading angle is denoted by psi, and the task of the controller is to make sure that this psi reaches the psi desired so that your vehicle will eventually come to the path that you want it to follow. And a typical control law for these situations would be what we call as a proportional derivative control law. In most marine systems, you will see that we don't require a lot of higher order control laws such as sliding mode control or backstepping controllers. PID control works really well as long as it is tuned fine and properly. And that seems to work well for the industry for most of the applications. There are applications which would require different types of controls, especially when you have a lot of uncertainty on varying speeds or varying operational profiles. That's where you would require a different type of a controller. All right, so putting these things in together, we wanted to test this algorithm in our simulation model and then on to the real world. So this is one of the test experiments which our lab has taken up on the lake of the campus. So this is the campus lake at IIT Madras, which is spanning about 300 meters by 100 meters wide. And this is a scaled container ship, which is of the 75:5 scale ratio. So the real one will be about 230 meters. The actual model scale vessel here is about 3 meters, outfitted with a propeller and a rudder, and which means it's an under-actuated system. And we were interested in seeing whether it's able to do a path-following exercise within our lake. Now we'll talk a little bit about the digital twin aspect of it. So what you see here is also a similar exercise of path following, but with a slight modification that whatever is the real data which is coming from the sensors is actually being fed into the simulation model, and we are trying to observe whether the simulation model and the true path, they are agreeing with each other or not, whether the dynamics is agreeing with each other or not. And if they do not agree, that poses a good question for us. How can we improve our hydrodynamic models? And in the previous speaker talked about system identification. That's a whole lot of business that we actually do. We try to identify what that difference in gap is and see whether we can improve our mathematical modeling to actually match, achieve a better match between experiments and simulations. This also leads us to a very interesting set of trials. So I teach a course on marine autonomous vehicles as well as maneuvering and control of marine vehicles, where I challenge the students to actually implement this inside our wave basin on a smaller boat. And you can see that some of them are successful, but some of them are not. And it's a great learning experience for students to actually put all of these concepts together and see them working and have it all click together so that they can understand why the different components work and what their effect is when it doesn't work. I'll take a switch of gears here a little bit and try to give you a slightly different example here. So we'll talk about the same path following example, but with a non-traditional approach where we'll look at a deep Q learning approach. And Q-learning really looks at the idea of a reward and a punishment model. So the agent is given rewards if it is performing something better, versus it is given a penalty when it is not taking actions as per what it is supposed to take. So in this case, we have 4 observation states. So given that we want to move from one waypoint to the other, the 4 observation states are cross-track error, course angle error, distance to goal, and the yaw rate. And this is a very simplistic model where the vessel can only take 3 rudder angles, 35, 0, or minus 35. Very, very simplistic model, just to give us an idea of how things move. The crux of any reinforcement learning algorithm or even artificial intelligence-based algorithms usually lies in this reward engineering. You have to specify what does that reward look like, and a whole lot actually goes behind the scenes on how do you tune these rewards. Now, we'll not be spending a lot of time here because of the paucity of time, but please understand that these values did not come up magically in my head. They had to be tuned quite a bit in order to understand why those particular values were chosen. Once we do that exercise, we try to see and simulate it forward and see how does that work out, and we see that whether it is able to reach different waypoints in different quadrants. And we also are interested in seeing that now if I give a series of waypoints instead of just one waypoint, is it able to follow the path effectively or not? The plot on the right-hand side is a very interesting plot where we introduce a strong wind disturbance where the agent has not seen any of the wind disturbance in the training paradigm, but we are interested in seeing whether it can still keep course even when I have strong winds. Those winds are pretty strong, almost close to a hurricane set of winds, so about 200 kilometers per hour. And we are able to see that it still is able to keep course. We also tested out with different other types of reinforcement learning algorithms, and I'll not bore you to details with it. So the DQN algorithm only has discrete actions that you can take, but there are other algorithms which can allow for a continuous action space, and DDPG and PPO are 2 classes of algorithms which allow you for a continuous action space in it. And we tested these out again in the lake and see whether it is actually working out well or not. Okay, I'm going to probably go a little faster here where we are looking for obstacle avoidance paradigms. And the main takeaway which I want you to take here is that it still follows the same guidance, navigation, and control framework with the only small caveat that if an obstacle is present within a certain radius of its current location, then you must try to look for a reactive guidance which will try to avoid collisions actively rather than just looking to follow your goal. And that's how you build the autonomy layers one on top of the other. So you see here that we are trying to build an obstacle avoidance guidance, but it works together with a path following guidance, and only the switch happens, then the framework of G and C is still preserved. So here we were looking at a obstacle avoidance algorithm and how we can do the obstacle avoidance using artificial potential fields. And I'll kind of move to the scenario where, the interesting scenario where you have 3 vehicles which are trying to avoid collision with each other. And what I want you to observe is that between the red and the blue path, they're not having a similar behavior. And that's because you have now 3 vehicles which have conflicting Colreg requirements. So the vehicle which is going from the left to the right, the blue one, has a stand-on requirement with respect to the overtaken vessel. So it must keep its course and not change its course. Whereas with respect to the head-on vessel, it is supposed to change course and get out of the way. So we were interested in seeing what happens when we put this conflict scenarios in place, and do the vehicles are able to actually do better or not. And we were happy to see that it was able to do better than some of the traditional algorithms like velocity obstacle. And we were trying to compare what is the minimum distance between the agents as this encounter happens through. We also did a lot of statistical analysis to look at what the if you put in a constricted environment with multiple agents being put together, whether all of them are able to reach their goal or not. Soon enough, we do want to do experiments on it. We did find that the percentages are pretty high, but they're not exactly 100% which you would expect. And that gives us an opportunity to go back and understand why was there a failure. And every study will have its own limitations and improvements which are possible with it. This algorithm actually was implemented by our students in one of the ASV challenges where they were actually able to implement it and come head-to-head with top schools like MIT, NUS, and others. And they were actually able to win a third best prize in this. And this is an actual competition footage where they were able to win the third prize in the ASV challenge in 2023. They're preparing to go again for 2026 in coming August. Okay, I'm going to skip over these two parts. You have different types of, I was hoping to show you a different algorithm here, but probably we'll skip over that and look at one last, this one. So this here is multiple agent reinforcement learning. So the same paradigm can be extended where you have multiple agents interacting with each other and trying to find a path which is collision free, while at the same time maintaining a safe distance from each other. So we do test these out in our simulators first, and then we take on to the real world applications. So I'd like to conclude that when we look at marine autonomy, there are both defense and commercial applications, and it builds on layer. It's not as if that all of them combine together from the bottom up. So you have the low level controllers first. On top of it, you build the guidance and navigation stack. On top of it, you bring more autonomy, level 1, level 2, level 3, so on and so forth. So if I want you to take away one single takeaway from this talk, is that the guidance, navigation, and control framework is what actually allows for this feedback to happen, and we must try to leverage upon it as we build levels of autonomy. So each level of autonomy will have its own loop to close, and that will allow you to have mathematical guarantees on whether the system will work reliably when you have more uncertainty or a congestion with different types of vehicles together. Okay, that's all for me. Thank you very much.
Thank you, Professor. Now we have question.
Somebody has a question there. Yeah.
Yeah, thank you for this nice presentation. And regarding that path following, are you using a closed form function like a circular path? You are giving that equation, or it is based on waypoint?
No, so it is based on waypoints. So I can actually choose the waypoints however I want to choose, and I can parameterize a more complex path as a set of line segments or a set of spline curves, and then ask my model to follow those paths. So it's not necessary that it's a closed form.
But that is based on PID only, you are doing the all
This
tuning
one,
or others?
yeah, the one which I have shown here is based on PID only, that's right.
But there are some standard functions also can be used, like elliptical part you want to follow, or lawnmower also you want to follow.
Yes.
That path can be formed in that way.
Yes,
based on
parametric path formation and trying
directly
to follow.
it can be used based on some feedback linearization methodology.
Yes,
Yeah,
yes.
that is another. And regarding that obstacle, so you are able to, I mean, this is for surface motion only, width also you are measuring that.
Sorry, come again?
Width of the obstacle also you are measuring.
Yes, yes. So perception part of it is not what I have shown here a lot. I primarily focused on navigation here. Perception will look at whether we can look at the camera feeds and determine what is the size of the obstacle, whether you can look at the LiDAR map cloud and fuse it together with the camera feeds together to estimate the size of the obstacle, its velocity parameters. Those will also play a significant role in obstacle avoidance.
Okay, so but as you said that you are working with potential field, there are lot of constraints in that. So attractive potential and repulsive potential, if there are some conditions where the people will get stuck. So there are other methodologies we are also using, like fuzzy logics based obstacle avoidance, and also AI based techniques based on the priority for our homing docking system. So I am from CMERI, Dr. Nandi. So thank you for this presentation.
No problem. So this was just one of the possible examples which I have shown you. This is not the only methodology we use all the time. We do use velocity obstacles or artificial potential fields, even a combination of AI-based approaches. So for example, the DQN approach is leveraging some part of guidance and control together into a new block, which is being now taken over by artificial intelligence. So the main point that I wanted to convey is that there's no one way to do the things. Probably the best way is where you can have a combination of these things. That's where the sweet spot actually lies. And what we have realized is, from a path following point of view, you really don't need artificial intelligence based approaches, and traditional approaches work really well. It's when you want to look at obstacle avoidance problems where you can have a conflict occur or a conflicting scenario occur. That is where artificial intelligence have a leverage over the traditional approaches. It's not that you can't do with either of them, or you don't have to choose between one of the other, but it's a much better suited problem for the artificial intelligence when you're looking at a collision avoidance problem. That was the primary goal.
Okay.
Professor, just a issue of definition.
Yes.
See, navigation, guidance, and control, normally when applied whether launch vehicle, satellite, ship, or car,
Yes.
they are part of automation.
Yes.
By definition, autonomy is automation plus decision making.
Autonomous plus?
Automatic plus decision making.
Plus decision
Autonomy is a automatic automation plus decision making.
Correct.
Now, decision making can come from various
Algorithms,
reasons.
yes.
I can have an algorithm.
Yeah.
I can have a artificial intelligence, or I can derive from even some other intelligence.
Yeah,
So-
something like rule-based
So I just want to
Yeah.
clarify that as far as navigation guidance control, that is a part of automation itself. Just wanted to think that. It's
Yes.
part of autonomous.
Yes, yes. I
And
agree.
Autonomy is always autonomous. Autonomy is automatic plus decision making.
Yes. So I would probably only add on to that in one way, that autonomy is a level which is built on top of GNC structure. The guidance
Top of-
navigation.
It is a plus.
It's a plus, yes.
It's a plus, and that is by definition.
Yes.
Thank
Any
you,
other
sir.
questions? Yeah.
Yeah, maybe we can have rest of discussions during the tea time.
Perfect.
So we have Dr. N.R. Ramesh to felicitate Dr. Abhilash, please.
Yeah, we have next presentation by Dr. Raju, Senior Scientist, DRDO, NPOL. He is going to talk on underwater sonar systems. It is going to be online.
Morning. I hope you are able to hear me.
Please bear with us while we try to connect Dr. Raju online. Yeah, he's here.
Good morning. I hope you are able to hear me.
Yes, sir. We
Good
can.
morning. Madam, I'm not able to share the content presently. Is it possible? It is saying that you can't share content unless the host makes you the presenter. Can this be rectified?
No, you have to present it from there, sir.
Yes, ma'am. I'm not able to share the content here.
Yeah, we have given the permission. Now probably you can try once again.
Okay. Okay, ma'am.
So can you share now?
I'm starting. Yes, ma'am.
Yeah.
Madam, you are able to see my presentation?
Yes, sir. You can put it in full screen mode.
Yes. Is it okay, ma'am?
Yes, it is visible, but it's still in slide mode only, not in full screen mode.
Okay, 1 minute, let me just try it. Give me a moment. Madam, are you able to see the full screen now?
Yes, sir, we can. Thank you.
Okay. Thank you very much. Sorry for the thing. So, good morning, all. I'm R.P. Raju. I'm presenting this on behalf of my director who could not be present there today. So, I'm speaking about sonar system engineering perspectives for autonomous vehicles, autonomous underwater vehicles, and we'll be sharing some thought processes that NPOL applies when we do product design here in defense industry. So, let me move ahead. So the maritime surveillance is a very crucial challenge for national security, as you can see, and everyone in the audience is aware that India has got a very vast coastline with coastal population, wetlands, fisher folk population, and the coast that is affected by erosion, mangroves, all this. So maritime surveillance is a crucial challenge, and we have got adversaries around us who we need to detect. We need to estimate where they are coming from, and then we need to classify whether they are a threat or not. So coming to Indian Ocean region, the interests are galore, as you can see from this very well-known chart over here, which is showing us the various choke points in Indian Ocean region, the different sea lanes of communication, what we call as SLOCs. Then there are the Indian Ocean coastal states, and there are landlocked states which are linked to the Indian Ocean. Why I present this particular thing when we are doing sonars is that when we design a sonar, or for that matter any system for underwater scenario, we need to know where we want to deploy it, how we want to deploy it, what are the ranges that we want to achieve, what is that we want to detect. So those are very, very important parameters when we design a sonar system for any vehicle for that matter. For a surface vehicle which is not autonomous, or even for a vehicle that is autonomous which is dived, or which is capable of autonomy in the on the surface. So coming to Indian Navy, the preamble of Indian Navy is about deterrence, decisive military victory. So the primary need of Indian Navy is detection, and NPOL, as you know, it works towards equipping the Indian Navy with these state-of-the-art surveillance tools for reliable detection of underwater targets. So now coming to what are the different technology competences that are required for sonar design and development. So as you can see from this cycle, let me start from the top right. ASW oceanography is the first and foremost important technology competence that is required for sonar design. That is the anti-submarine warfare oceanography. We should know the environment very well. We should have long-term observations. We should have observations which are made for the anti-submarine warfare discipline. They cannot be any observations which are not made with that perspective. For example, we know what is the bottom loss by using echo sounder data. But if the echo sounder is operating at 256 kilohertz, the bottom loss that we arrive at is for 256 kilohertz. Whereas probably the sonar with that we are operating at maybe at a frequency of 5 or 6 kilohertz. So having relevant data set for doing in oceanography for doing this ASW is very, very important. Apart from that, we require a strong modeling and simulation of this environment and see how the acoustic wave propagates through the ocean. Then the type of materials that are required for this sonar, and then the transducers. The transducers are the heart of a sonar system. The piezoceramics, how they need to be, how they are designed for producing a particular acoustic wave of a particular frequency, of a particular source level, or if we are trying to listen to something, what is the receiving sensitivity of the transducer, how do we design that. So those competences are very, very essential, and it's very important they are all indigenous. We try to be as closely indigenous as possible. Then coming to sensor structures, what are the type of sensor structures and handling systems that we require? For example, in case of a hull-mounted sonar, I'll come to the autonomous vehicles a bit later. In case of a hull-mounted sonar, just building a cylindrical array that is fitted in the bow or in the hull is not sufficient. We should have the proper handling systems for deploying that, handling systems for measuring it, for calibrating it. So those are very important. That is a very important aspect of sonar design and development. Then coming to signal conditioning, the signal that we receive, how do we pre-amplify it, how do we digitize it, how do we look at do the processing for detecting a target, for classifying a target. And then coming to the user perspective, when a user is interacting with this particular system, what is the type of human machine interface that is required? Now, when I say about HMI or display, for a manned system, HMI will be somewhere as operator is sitting and he or she is going through the data or going through the display and trying to arrive at conclusions about how to estimate, how to classify a target. But in case of a autonomous vehicle, probably this display is not available inside the vehicle. It is probably in a data center. It is probably a data center where there is a common operating picture that is being displayed for a variety of AUVs that are being deployed in a given location. Then coming to product design, that is also a very important aspect because we are delivering it to Navy with some MIL standards. So product design, adhering to those standards is very, very important. Then coming to algorithms. Algorithms is the area where AI and ML come into picture, where we use data probably from previous missions, from our previous understanding of the ocean to arrive at better detection performance for our sensors. So these are the different technology competence requirements for sonar design and development. And at NPOL Kochi, we have got all these departments or all these technologies and technology groups that work towards a sonar system. So what is the goal of a sonar system? Basically, it's detection of a target. Target can be a moving target. So what are the possible underwater acoustic detection scenarios? The possible underwater acoustic detection scenarios are mainly three. Either it will be a surface duct path, as you can see in this figure, or it will be a bottom bounce path where the signal hits the bottom and then we detect in the fan that is available after the bottom bounce, and then or there can be a convergence zone path. So what do we want to detect? Do we want to detect a target which is in the surface layer, or do you want to detect a target which is below the layer? And what are the possible modes? These are the three possible modes of detecting a target. So there are two types of sonars, as you are already, you will surely be aware of this. One is the active sonar and passive sonar. Active sonar, we send a signal, we get the echo, we process the echo, and we arrive at conclusions regarding what is the target, what is the range of the target, or what is the type of target, and we also try to get even the Doppler by using this active sonar system. Passive, we listen and we try to do detection. Let me first look at the active sonar equation from the perspective, and each term I will speak in terms of what does autonomy does to each one of these terms. Now coming to a sonar that is fitted on a ship, it transmits a signal. It travels through the ocean and it undergoes transmission loss. Then the signal impinges on a target. So there is a target strength that is associated with the target. In this case, I have shown an underwater vehicle or a submarine or for that matter, any underwater vehicle. This target can be an obstacle also. The target can be any target which is available in the ocean for which this sonar is designed. So as I started off, there is a source level, it undergoes transmission loss, it impinges on the target, and there is a target strength for every target. And then this echo travels back, undergoes transmission loss again, and the signal that is available for detection is basically source level minus 2 times of transmission loss plus the target strength of the target. This particular signal has to be detected against the prevailing noise. Now, when I speak of this particular signal to be detected against the prevailing noise, one of the major aspects of having a sonar instead of you can always place a single hydrophone detection of targets, but then the advantage of a sonar is that we can do beamforming, we will be able to look in a particular direction, and we will be able to reduce the noise that is coming from all the directions. If this signal minus noise is greater than a particular detection threshold, then we say that the detection has taken place. So in sonar design for an autonomous vehicle, what is very important to understand here is that this term, especially the term DT, that is the detection threshold. Detection threshold, it's a detection problem. So detection threshold depends on the type of processing that we are doing. It also depends on what is the probability of detection that I want to achieve and what is the probability of false alarm that I want to achieve. The probability of probability of detection. For example, I want to detect a submarine. Usually we look at probability of detection of around 50%, sorry, 90%, and a probability of false alarm of around 10 to the power of minus 5 or 10 to the power of minus 6. So depending on this particular value of PD and PFA, we know what is the value of detection threshold against which my sonar has to perform. Now, one very important thing to note here is that detection threshold is a function also of the operator who is sitting looking at this particular data, trying to estimate and classify. So the operator usually in a sonar room, in a manned vehicle, in a ship or in a submarine, it's the operator's experience, the operator's knowledge and the operator's brain that is also adding to the detection threshold values, which is not something which we can perceive. But a better operator is someone who can probably pick a signal by listening to it than just by looking at the processing that is being done over the screen. So DT is a very, very important aspect, and it gets affected by the autonomy. It either gets reduced or it increases because of the various factors that are put in to the system because of the autonomy. So now I move the transmission loss term to the to one side and then write what is the figure of merit of this particular system. When we look at the figure of merit of active sonar, we look at the equation over here. It is source level plus target strength minus noise level minus DI, that is the array gain, minus DT whole divided by 2. So what is figure of merit? It is the maximum allowable transmission loss for a detection to take place. Now, if you look at the two terms over here, apart from source level array gain and detection threshold, which is something that a sonar designer can work on, target strength and noise level is something that is not in our control. Target strength is a target parameter and noise level is a parameter. Either the AUV or the platform which is there, like a ship or a submarine, has got its own noise, that is the noise level, or if it is silent, then the noise level is because of the ocean, noise which is prevalent in the ocean. Coming to these two terms, the present knowledge of the target strengths that are available, for example, for a submarine, average or mean target strength is around 12 dB. For a ship, it is around 8 dB. For mines, it is around minus 20 dB. For a diver, it is around minus 25 dB. So the challenge is that this target strength varies with pulse length, the depth of the target, frequency, speeds, aspect, bottom type. So, and coming to the type of modeling that is being done to do target strength modeling is still a very nascent area of work here in India. I'll just go back to this particular site. So as I told you, the maximum allowable transmission loss for an active sonar to work, as you saw over here in this equation, target strength and the noise level will play a major role. Now, an active sonar is operating in a deep water or a shallow water. What do? We get a signal and we usually do replica correlation. That is, we cross correlate the transmitted pulse with the received pulse. The assumption is that when the signal propagates through the ocean, there is only a decrease in the amplitude of that particular pulse. If you see in this particular side on the left side, there is a transmitted pulse, LFM pulse, linear frequency modulated pulse, that is sent by an acoustic source. It travels through the medium, which has got a sound speed profile structure like this. It has got an ocean bottom with a particular structure like this. And then it travels through the ocean. The actual received pulse will look like this. Whereas that is the actual received pulse R, whereas the assumed received pulse is this. So this distortion in the signal is not taken care of. So the replica correlation that we do has got a correlation loss that needs to be accounted. This is a very, very important phenomena in shallow waters especially, and probably littoral waters where many of our AUVs are to operate, and this particular energy spreading loss, as we call it, is a very, very important factor that needs to be considered when we are designing a sonar. That is where do I operate it? If I operate it off Porbandar, there is a different type of bottom. If I operate it off Chennai, there is a different type of bottom. If I operate it off Vishakhapatnam, there may be a very, very fast varying bottom. If I operate it in Cochin, so this ESL is a function of the location where we are operating a particular system. So knowledge of this is very, very essential. It's very crucial for designing this sonar. Then coming to the active sonar equation, when reverberation is present, so instead of noise, we are trying to detect the signal against reverberation, against the detection threshold. So reverberation is also a major factor, especially in shallow water, because there the reverberation from the bottom will be more stronger than that of the noise that is prevalent in the ocean, and the signal has to be detected against this reverberation. So there are different types of waveforms that we can design, which we also use here at NPOL and in our sonar systems for reducing the reverberation. And there are different frequencies also that we design for different frequencies at which we operate to reduce this reverberation. Then coming to passive sonar equation, we have got radiated noise which travels from the submarine towards the thing, and we listen to it, and the signal has to be detected against this. Here the most important thing that I want to listen passively is the radiated noise level. This radiated noise level is a function of frequency, and these are various radiated noise level curves that are available in literature for different types of targets. So passive sonar is trying to listen to a particular target and detect that particular target. So radiated noise level of different aspects are shown over here. Then that is submarine, submerged nuclear submarine, torpedo, noisy torpedo, and convoy of ships. So a typical sonar specification, we look at what is the array geometry, what is the mode of operation, what is the frequency band, what are the sampling frequency, beam forming, what type of, how many tracks do you want to do, means how many, and what is the integration time, what are the range scales. These are the various aspects of a typical sonar, and the building blocks for this are given from the type of transducer array, the front end electronics, the digital signal processing, and the display that we do to display this particular signal. Then coming to the system development processes, we look at what is the requirement, as I already told. We define what is the scope, then we design, and then we develop, integrate, and test it. This particular phase of testing is, I'll just skip some of the slides on mine. This step of testing is basically we do a prototype testing at the lab, then we do factory acceptance trials, harbor acceptance trials, and then we go for the sea acceptance test. Coming to
sorry to interrupt you, sir. Can you please summarize your session in another 2 minutes?
Yes, ma'am. Thank you. So the sonar systems, these are the various sonar systems on the platforms. So we do SATs and UVTs where we do our things. So now coming to the new technologies, sonars, we are looking at enhanced performance, easy integration, and easy maintenance. Coming to sonars that are developed by DRDO at NPOL, sonar was the first system that was exported from DRDO. To different, these were some of the first export orders that came to us from Myanmar, as well as some of the facilities that we developed at Vietnam. So these are the portfolio of indigenous sonars right from 1980s. DRDO's sonars have been fitted on Indian naval ships and submarines, and our auxiliary systems, underwater communication system. These are all systems that are already fitted. They are operational on Indian naval platforms, and I think already the speaker from NSTL would have shown you about the various sonar systems that are fitted on the AUV that has been developed by NSTL as well. Apart from, as I told you, apart from the technologies that are there, very important part is how do we survey our region, know what is the ocean environment over there to design our sonars for a particular scenario. So coming to future, we are looking at network-centric surveillance and submarine detection using squid quantum sensors and synthetic aperture sonar as well. Coming to various infrastructure that are required for testing of sonars, we have got a space platform at our lake facility. We have got a new acoustic research ship. I think the only acoustic research vessel presently in India that is designed for doing underwater acoustic research is INS Sagardhani. We are getting a new one now, underwater acoustic research ship. And then we have got a CTEC facility that is coming up, and we have got a mobile acoustic ranging system also that is coming up. So as we move forward, thank you very much for listening. So this is about the sonar systems from the perspective of any platform for that matter, and how it actually changes the sonar equation and the FOM values when we start to design for the autonomous vehicles.
Thank you, Dr. Raju. We can have a quick 2 questions from the audience, if anybody.
So can you bit explain sonar?
You have to be a little louder because he's online, and keep the mic closer to you, please.
So can you bit explain sonar fabrication material? Because based on the range, how you decide a material and all?
We usually have, we use piezo ceramics in our most of our underwater systems. But in recent years, we have started to design and develop and make products with using fiber optic hydrophones as well. Coming to the material, so they are basically piezo ceramics as well as fiber optic hydrophones. More than the design of the material, we are more into type of transducer that we use. For example, we will be using Tonpils transducers designed for it, or we may be using magnetostrictive materials, or we may be also going for fiber optic materials for passive sensing. So the type of application will decide the type of design on the same piece of ceramic that is available with us. So coming to projector, for example, I want to get more source level. I will use different type of designs. For example, there is a fully threaded ring, or there is a flexural disc that can be used for low frequencies, or we can use what we call as FFR, as well as flex and Tonpils, what you call projectors also. So it's on the material. We design the transducer in such a way that we produce a particular source level, or we are able to listen to a particular sound. So we are working mostly in that way with respect to materials in sonars.
Yeah, hello sir. This is Sarang from BITS Pilani, Goa. I have one question with regard to the sonar equation. It calculates the transmission loss.
Sir, closer to your...
It calculates the transmission loss, which is essentially both way. In acoustic communication, we need transmission loss one way. That also is very difficult because it's temperature, pressure, salinity dependent and all. And as you also rightly said, you do this analysis every time the actual region of operation changes. Do we have any database of channel models with us? Is available is a central repository for us to use?
Actually, NPOL, as you know, was probably the first oceanographic lab of India. So 1952 onwards, we have got data sets collected all over India. So we've got a very large repository of sound speed profiles that are available with DRDO at NPOL, a very long data set, as you can make out, from 1952 onwards. This database is I will use the term restricted, because restricted for use for sonar design for Indian Navy. But if you interact with NPOL, or for that matter DRDO, through various forums like NRB, or through forums like Directorate of ER and IPR DRDO, we will be able to sit with you here at NPOL and you will be able to see this particular data set. Coming to channel models, at NPOL we use open source channel models that were available till recently, like Bellhop, Kraken, or for that matter parabolic equation models. We also have fine-tuned these models for our for Indian Ocean environment to arrive at predictions with respect to ranges, or with respect to data rates, or with respect to bit error rates, through various experiments that we have conducted using our systems. And coming to underwater communication system, we have an underwater communication system developed at NPOL long back, and it has already fitted and functional on many of our naval platforms. It is not available for civilian use presently, but then you will always be able to interact with NPOL and with NPOL Kochi for these channel models, or for this data set, or for these system design as well. And we will be happy to collaborate with the academia and the industrial partners as well.
Thank you, Dr. Raju. So we thank all our speakers of this session. And I'm sure that we have gained a lot of knowledge about design and development of autonomous underwater vehicle, especially the young generation students community who is here, and they're passionate about designing a AUV themselves. So thank you, everybody. Please join us for high tea in dining hall now. We come back to the same hall after 15 minutes. Thank you.
Madam. Welcome back, ladies and gentlemen. This session is an autonomous multi-robot system. The chair for the session is Dr. J. Pranita Roslin, and the co-chair is our very own Mrs. Nidhi Varshane. I hand over the forum to Nidhi ma'am to take over the session and introduce the chair.
Good morning, everyone. I welcome once again. So I'm again honored to be your co-chair for this session. So we have this next session on autonomous multi-robot system, which will be chaired by Dr. Preeta Rosalyn. Dr. Preeta Rosalyn is very famous with us because she has been associated with NIoT for many projects, and her research interests are digital twin for wind grid integration, energy management, microgrid power system stability, and marine robotics. She has been offered MTA Special Commendation Award as well. She works in Department of Electrical and Electronics Engineering in SRM Institute of Science and Technology. Before we proceed with this session, I'm sorry I missed to felicitate our chair for the previous session. So I invite Dr. Muthuvel to felicitate Dr. Virkesh Kumar. My apologies to you, sir. Thank you, sir. So this session is an autonomous multi-robot system. We have, again, 4 talks in this session. So I request Dr. Preeta to take over.
The first session is by Mr. Kushal Bhattacharya. He is Scientist F in NSTL DRDO. He has 20 years experience in underwater weapon systems and autonomous underwater systems. He is associated with underwater structural development since 2004. He has his MTech in Mechanical Systems, Dynamics and Control in IIT Kharagpur. His technical expertise includes pressure hull design and analysis, underwater structures, advanced composite materials for underwater applications, and AUV systems. He is currently the project director for man-portable class autonomous underwater vehicles, and his research focus is mainly on concept formulation and system engineering, design, realization, and deployment of underwater systems, multidisciplinary development of advanced underwater robotic platforms. So we are much privileged to invite Dr. Kushal Bhattacharya, NSTL DRDO, to present his topic on design and development of man-portable AUVs for MCM.
A very good morning. I would like to thank Director NIoT, Dr. Vedachalam Sir and Team NIoT for giving us this opportunity for presenting on the work which we are doing at NSTL for last 4.5 years. So here what I will be doing, I will be presenting on design and development cycle for development of man-portable class of AUVs for mine countermeasure operations. For the larger audience here who may not be aware about what is a mine and what is MCM, I will dwell upon few slides on mines and mine countermeasure systems. So then I'll go into the development of AUV. So when you talk about mines, so what is a naval mine? A sea mine actually is an explosive device which are laid in water with the intention of damaging a ship or deterring a ship or making it incapacitated so that it cannot carry out its operation for which it is intended to. So what is the strategic importance it actually plays? It's access, anti-access, area denial, harbor defense, strategic blockade, psychological impact, which is the most important thing here, and disruption of maritime operations. So there are different types of mines which actually are designed and developed across for last almost maybe 200 years or more than that. So sea bottom mines which are laid onto the bottom of the sea, the mines which lay in between the water column, we call it mood mines, mines which are actually on the surface, or the old mines of the World War II vintage mines which drifts or remains just under the water and act upon when the ship came in contact with that. So if you see the current mines, mostly they are bottom mines, mood mines, and some kind of mines which actually goes up, which actually can climb up, or means actually attack the target on detection. So those mines we call actually rising mines. So these mines can be deployed from various platforms. They are very low cost weapon, as I said. So they can be deployed from ship, they can be deployed from submarines, even they can be deployed from aircrafts. And if you see on the top right corner, that casualty due to mine, out of missiles, torpedoes, air, small water mine, we can see that mines has created maximum damage till today for any of naval assets, if you consider. So this is the newspaper clippings I have put, I have jotted down that in the recent mine warfare, what is happening across the world. For this may be from last few months, or maybe from the time the Ukraine-Russian war has started. Actually, a very good time for the mine developers as well as for the MCM mine warfare guys to highlight that what are the importance of mine warfare. Always historically, investment on mine was always very less, and whereas on MCM it is very high, but still detection of the mine is one of the most challenging naval mission possible. So, as I said, what is the importance of a mine countermeasure operation or a mission? Mine threats significantly impact the fleet mobility, amphibious operations, logistic chains, and commercial shipping. So MCM operations are mission critical because it stops entirely the intended operations of the parties or who is involved in that. Conventional MCM operations are slow, manpower intensive, and expose high value platforms and diverse to risk. Generally, MCM mission is always termed as dull, dirty, and dangerous. It is a repeated task, very highly dangerous. So that is how it has been always considered. If you see from the economic point of view, economic asymmetry, a mine barely costs a few thousands of dollars, whereas a MCM vessel, which a dedicated MCM vessel, can cost us around hundreds of millions of dollars. Whereas closure of a port of Hormuz, we know what is happening. It actually massive economic impact per day, and all of us across the world is facing it. So critical operation challenges in a mine countermeasure operations. We can see on the right side, I have put 4 figures. On the top, if you can see, it is not very clear, but a mine can be seen with a very distinct shadow. Where the mine is a proud mine, it is on the surface of the sea bottom. Whereas the second figure, the mine is partially buried and hardly the shape is visible. Even the mines are developed nowadays, one is called the Turkish mine Malaman or Rokkanaz, having such a different shape, it becomes very difficult actually for any MCM equipment actually to detect it because it will get completely submerged into the noise of the environment or the ambient. So presence of a non-mine bottom objects that resembles mines in sonar imagery, categorized as mine-like objects and non-bottom mine objects. Non-mine bottom objects can be debris, can be anchor chains, rocks, barrels, or discarded ordnance. And the ratio of mine-like objects and to actual mines is typically can go up to 100:1. So they can be buried fully, they can be buried partially. So the sonar imagery completely gets changed based on its present position. So if we see the different types of mines and what is its MCM implication. So the bottom mine or ground mine, it goes onto the seabed where it requires, for detecting that, it requires a seabed survey, which is hard to detect in a clutter. And AUV with the side scan sonar is the primary sensor for doing such kind of missions against bottom mine or ground mine. If you go for a mood mine, it remains in the water column in between. So it also influence activation only, but in this case, sonar detection of the mooring cable or maybe a front-looking sonar is a volume search sonar is actually a requirement at a correct depth range for detect a mood mine. If we go for a drifting mine, actually the autonomous systems in what means AUVs are less suitable, whereas a UAV or a airborne surveillance are more effective for that. If you go for a limpet mine, which is actually the divers can come and attach onto a hull and go away, hull inspection by an AUV and ROV with an optical camera or possibly a front-looking sonar can be an MCM system. If you're looking for a rising mine or captor mine, these mines actually carry a torpedo inside it. So that actually requires detection of a canister which actually carries that torpedo inside, and in that also AOV with a side scan sonar or a synthetic aperture sonar can be a possible MCM system. So what are the different phases of mine countermeasures? There are two ways of detecting mines. One is mine sweeping, where we run an autonomous boat with systems which can simulate the signature on the surface and expect that the mine which is underwater, mostly the influence mines, will get triggered by that. But there is no way that we can confirm that yes, all the mines in that particular area are cleared. So another process is mine hunting, where we positively detect, identify and neutralize those mines. So there are 5 phases for a mine hunting. The first 3 phases are detection, classification and localization. We detect all mine-like objects, then we classify it, which are mines and which are mine-like objects. Then we try to find out its exact position into the seabed. These 3 things are actually can be carried out with a surveillance AOV which can carry the payload required for detection, classification, localization. Whereas the 4th and the 5th phase, the reacquisition and the neutralization, can be done by a neutralizer AOV or an ROV. So their reacquisition in the 4th phase is mentioned. The main reason is that we have to again reacquire the target. Though we know approximate positions, we are not aware that exactly the mine is there or not. Means it can be, similar objects can be there, and we have to again classify using a neutralizer. So it is preferred that for the reacquisition and neutralization, we carry a tethered vehicle and put human in the loop. So how this, as we discussed, that the AOVs are very, very important for an MCM mission. The reasons are that it keeps the sailors out of the minefield. The sailors or the ship, that mother platform can be away from a suspected minefield, and the AOVs will have lower operating signatures, so there is very less chance that it will trigger the mine. Even if it triggers the mine also, the purpose is solved for an MCM, but the AOVs will generally have a lower operation signatures. Higher persistence and scalability, we can deploy multiple numbers, and it has a higher, for longer durations. Human endurance is limited, but whereas in AOV, it is only limited by its size and its energy on board. And faster area coverage, by multiple numbers, we can cover more areas. So these are the different famous MCM AOVs, so-called famous MCM AOVs. On the top 4, they are Eugene, Remus 600, 8 NAME, and Bluefin 21. They fall in the class of bigger class, whereas Comet 300 and Remus is actually comes into the man-portable class. They comes in around 32 to 50 kg in that range. They are generally used for shallow water mine hunting. The problem which was posed to us by Indian Navy is actually to develop a man-portable class of AOV, from where we have started. And we have taken a man-portable class of AOVs for carrying out our missions. The platform, what is the advantage of having a man-portable class? It is platform agnostic naval MCM operation. We can use a REEB or a Gemini or a crafts of opportunity for deployment of those AOVs. We require minimum launch and recovery infrastructure and can be deployed from, as I said, REEBs and all. Better suited for littoral and shallow water warfare. Lower acoustic and magnetic signatures, which will reduce the vulnerability against the influence mines. And faster mission turnaround time or logistic simplicity. These are the main reason why a man-portable class has been preferred of late. So it's I would like to bring out that with whom we have worked for this particular project. So we have worked with 4 DRDO labs who has developed different payloads for this system. Whereas the Young Scientist Lab at Hyderabad, they have worked on swarm intelligence. They have developed this algorithm, acoustic mesh network. HML has developed the explosive for the warhead for us, miniature warhead for us, for the neutralizer AOV. And RCI has developed an INS for this swarm vehicle. We have worked with academia, IIC Bangalore and IIC Bhopal. IIC Bangalore has mostly helped us in development of algorithms for synthetic data generation, whereas IIC Bhopal has worked on development of a multi-vehicle simulator. And Dr. Sujit from IIC Bhopal is present with us here in the auditorium, and sir has helped us in development of this, which has actually helped us taking the project faster, get the solution faster. And what are the challenges? I have brought down 3 challenges only here. There's AI-driven target recognition, which we have thought of deploying into this vehicle, where in a man-portable class of vehicles, we'll try to carry out a real-time detection and classification, inter-AOV communication so that we can cover an area faster. And development of a GPS and DVL-aided navigation for this class of vehicles for the first time in the country with the help of RCI. So where RCI has developed the entire algorithm, the INS, everything has been done indigenously for the first time. These are the two vehicles. The top one is a surveillance vehicle which carry all the mission payload, the side scan sonar and the camera. It carries a DVL, MEMS-based INS, an acoustic modem for communication. The neutralizer replaces the side scan sonar and the camera, and actually not the camera, and the side scan sonar and acoustic modem, which actually has been changed into a warhead. So these are the defense subsystems which has been developed. As you can see that the main challenge was, other than those three which I brought out in the previous slide, is the miniaturization, the form and the volume factor, which actually plays a critical role here. All the system needs to be miniaturized and to be proven, and we have gone through a rigorous qualification procedure where we have involved the inspection agencies to clear it, the ESS, the ETs, ATs, and the EMIMCs, all has been done. So the vehicles needs to be prepared. So the salient features I put on the right. These vehicles have an endurance of around 6 hours. It is around 30 kg in weight. It carries side scan sonar and camera as a payload, and we could integrate deep learning based ATR algorithm into this. And mesh networking has been tested in an actual operational environment, and it has a very portable command and control station considering the final application into consideration. I will only highlight few of this. One is that the development of an onboard computer. Therefore, us to deploy an AI-based algorithm, actually we need the computational power onboard, and considering the vehicle size, its form factor, the most critical challenge was to develop an onboard computer which actually can carry out all the job which we are looking for. So this particular system, which is around 1.25 kg in weight and 200 into 100 into 57 is its dimension. So we are carrying two boards, one is a SOM and another one is both the SOM. So these two boards are along with the power module has been put into this OBC. This OBC carries out pre-launch, mission sequence, recovery, everything. It controls the vehicle, it processes the data of the payloads, it takes the decisions, communication, everything has been done by this OBC. It has been developed for the particular application. If you come to this ATR, what are the challenges? So traditional image processing techniques were there, machine learning was there, then comes deep learning. We thought of going for the deep learning because we are looking for a real-time application, and the data sets and the environment where the data has been collected are very different. So we have gone for the deep learning. We have decided, deliberated, discussed with academia, finally gone into this deep learning mode. But still, though we have chosen deep learning to be deployed into our hardware, but the main challenge we faced is actually development of a database. The side scan sonar data sets is something which is very scarce, not available almost in the country. When we went around the country, we hardly find any data. So we have decided that yes, let's go and generate our own data sets. It's almost become a project for us when we are carrying out this particular exercise. We deployed mines as NSTL develops mines also. We deployed different types of mines into different locations in harbor, in lake, at sea, and used an ROV which was developed by IRO Kochi, a startup. We have customized it with side scan sonar and deployed it to generate the data sets. Then we went to academia, IC Bangalore, we worked with them. Diffusion techniques has been developed for synthetic data generation. Finally, we have a substantial number of side scan sonar data developed for this particular process. So you can see on the right corner the real images which is collected and the synthetic images which has actually helped us in increasing our data set size. So there are a few representative figures are put. Once the data sets are generated, the next challenge was that we have to generate the image in real time. None of the OEM for side scan sonars gives you the software which actually helps us in generating the real time images. So we have taken up the task on ourselves. Our team has worked on it, and the top one, the data was given to us by our OEM. They says that you try to see that your online generation data sets are, your algorithm is working fine or not. So what we have done, we have used in-house software to generate using that data, we have generated both the data sets and checked. There are different techniques of checking how close both are. Then once we are convinced, confident, we have deployed that particular algorithm into our system. So this is the pipeline for the MLO detection pipeline. As you know, side scan sonar, then we have started acquired the data, we have processed it. Then in real time, once the data or the image is generated, that has been fed into the detection algorithm on board in real time. And finally, the detections are being stored into the system, and even when the vehicle comes up to the surface, it passes on to the deployment platform via RF. This has been done, and we have achieved an inference time of around 50 milliseconds for this entire process. The bottom one, ma'am, you can play the video. Yeah. So the right side is an optical. The right side is an optical detection which is happening in real time. The left side is an acoustic one. These are small videos which we have cropped in here to show that how we are able to detect. If you see at the end, there will be a similar object coming, but that's not a mine. But this algorithm did not detect that, and it detected the one with a MAP of around 87. And the optical image detections have been done in a relatively clear water. Even getting a range of 5 to 7 meters in actual environment with camera is really challenging, and we are not yet, means we have got around 3 to 5 meters, to be frank. So after this ATI algorithm, another challenge was to development of these miniature INS systems, which will be aided by DVL underwater and GPS in here. So the form factor was the biggest challenge. So we could achieve and develop an INS with the help of RCI Hyderabad, which actually is a 60 mm cube box, which actually encompasses an IMU, a processor electronics, and which has a connection to the GPS. And this system has gone through various stages. For development, we have initially done it in van trials. Then we have made, as you can see at the center, a video that we have made a test setup. We have defined test facilities in NSTL like HSTT, SMB. They can move, they have a calibrated speed sensor which moves at a particular speed. We have fixed the systems into that, carried out the different runs in different geometries, and checked how it is responding. Based on that, we have finalized our configuration, and then it has gone into deployment into our actual UAV. We have achieved less than 10 meters accuracy in a 4 hours endurance run. So finally, when we come to this multi-vehicle thing, the swarming, what is the swarming? Swarming behavior is an aggregation often combined with collective motion. A number of swarm behaviors such as flocking in the case of birds, shoaling or schooling in case of fish, and herding in the case of quadrupeds, these all are considered as swarming. In our case, it should not be as large as to be dealt with the statistical average, or not as small as to be dealt with the few body problems. So this is what actually the swarm size to be decided to. We have decided from the operational point of view, logistical point of view, that we will be deploying 4 AUVs which will be moving underwater, 4 to 6. We have tried out up to 4, and our vehicle will be on the surface. The swarming configuration will be 4 in water, 1 on the top, and the master slave configuration has been attempted. So the systems, if you look for an actual swarming, so actually it should be, all the systems need not be homogeneous. All systems should have their specific role. Based on that, they should carry out the operation. And finally, the data should be fused and the decision should be taken, which actually may be an emerging thing. So we understood that in an MCM, a true swarm may not be possible and may not actually take us to the end goal. So what actually we have attempted, we can say it as a cooperative multi-AUV system. True swarming is what we have not attempted. We can say cooperative multi-AUV system is what we have done. So multiple AUVs operate simultaneously, vehicles may exchange mission data, mission sectors can be pre-assigned, and however the vehicles do not significantly modify their behavior because we are carrying homogeneous vehicles, so they will be carrying out their operations, they will stick to their predefined missions. Then after the pre-course search is over, maybe in the final search, they will be taking the update from the vehicle which is on the surface or the master. So there are different types of configurations which are formation is possible. We have tried the line average, which is more optimal actually for an MCM point of view. Other shapes are possible, other formations are possible, but we have not attempted. We have attempted it in simulation, not in actual operational environment. If you see then the autonomy maturity curve, where are we? We are in level 2, where reactive cooperation is what we can say. That the collision avoidance, spacing regulation based on the nearby vehicles is what we have tried out in actual scenario. We have done it repeatedly multiple times and seen the vehicles, how they are performing in a particular scenario. We are attempting the level 3, the coordinated geometry, where information sharing and dynamic plan modifications is also being attempted, but in actual operation scenario, we have not yet done. These are the different functional categories of swarm. So swarm can be used for search operation, which we are doing for mine countermeasures. It can be used for X search, for seabed mapping, SW or ISR. Communication, it can be used in a communication network, where for longer communication can be made possible by multiple AUVs, so they can act as a hopping network. tracking. Multiple AUVs can be deployed into an area. Everybody will be doing detections on their own. Finally, the decision will be taken by fusing the data from different sensors. So that can be used for that. The seabed mapping, it can make actually the mapping and survey operation much faster. Massive reduction in mission time and distributed sensing coverage, because each AUV can carry different payloads, and actually finally the data can be fused, can be synchronized to get a better solution. This is a typical plot of XY trajectory of a multi-AUV mission. What we have done has been put here. In the leftmost side, the purple color, that is actually the AUV which has recorded the data of other 3 AUVs. You can see those vehicles are given a straight line path. So those vehicles, when you move, it has received the data from other vehicles, and the same thing has been passed on to the vehicle on the surface. That vehicle actually in real time is communicating it to the LCS or the launch control station. At the same time, these vehicles actually completing their missions which it has been intended to. We have used 2 different techniques. One is token-based acoustic mesh network and TDMA-based technique for doing this communication. Each AUV records its neighbor AUV mission data. That is what we have said. This is a typical side-scan sonar search and object detection scenario which we have put. Then the mother platform of the mission which will be deploying all the vehicles. This vehicle will be going to an initial waypoint. Then the master AUV will be on the surface. So it will be communicating with all the other slave AUVs. These AUVs, in case they detect something, will be passed on that information as an additional packet to the master. The master will get the instruction from LCS in case they want one of the particular AUV to carry out certain operations, which maybe to going to a particular area and carry out a finer search or do a localization task. So that can be instructed by the master. So this topology has been tried and tested in an operational environment. For doing all this, finally we understood that if it is a craft of opportunity or a small vehicle, we should have a launch control station which is compatible to that and can be carried anywhere. So a very small tablet or laptop based launch control station has been developed which can control multiple AUVs. It has an antenna, means it can communicate with the AUVs through Wi-Fi, at the same time through RF, and generally when the vehicles are deployed through RF, through that antenna we can actually control those AUVs and actually give the task. This can be used for mission planning, subsystem monitoring, mission replay with bathymetry, mission replay with SSTBLS mosaic, even side-scan sonar analyzer. All those things are inbuilt into the small system. So at the end of the mission, you can actually get all the data, analyze it there on board, and take the next step of the decision. These are a few of the trial runs. I have just put it to show that how we have gone ahead with the trials. Initially, when we have started at a surface run to see the vehicle dynamics on the surface. Then some runs, ma'am, if you can play this, runs at SMB in our test facility, captive waters. Then at the bottom, you can see a composite trial where we are deploying multiple vehicles. This is a mission planning. When we are giving a mission planning, we are planning the missions, uploading it into the vehicles. Then once the mission plan is over, then the vehicles are deployed. Those vehicles will start moving to their initial go-to point. Once those vehicles go to the initial go-to point, we have an USB also deployed there with an USB which can actually track those AUVs in real time and pass on the data that how those vehicles are moving. Even this is what actually the side scan image, what I have already shown. We will be able to do it in real time, get those informations stored into the vehicle, and the vehicles when it comes to the surface or through master can pass on to the LCS also. At the end of the run, the vehicles come back to the home, go to home positions can be given. That comes on the surface, it comes to the point, you just go with the Gemini, lift this particular vehicle up and come back to the shore and hand over it for the next mission. That is how this has been done. Then once you get the vehicles back, you can get the mission statistics, you can download via Wi-Fi or RF and see the entire what has happened, how the vehicles have moved, what are the parameters, what has happened, means whether any direction has happened or not, anything to be modified, everything can be done, everything is available with us. What we want to do with the data is based on the plan only. So this is how this entire ecosystem has been developed. We have, at present, we have multiple vehicles, tried it out. We are doing more trials to increase our autonomy levels. This is what actually is our journey for last 4.5 years. So I would like to end here. If any questions are there, I would like to take. Thank you.
We would like to get some questions from the audience.
Hello, Dr. Bhattacharya. I think excellent presentation, and I am also aware of this thing from the beginning. My suggestion is that INS, whatever has been developed by RCI, the technology has been transferred to some industry so that we can also use that thing for.
Sir, I think NIOT has already signed an MOU with RCI, but RCI is open to help out anybody is interested. You can always get in touch with them.
Okay, so they can directly give. It would be better if they transfer the technology to some industry. That will be more appropriate.
And they have developed an industry which is Ellora, which is actually positioned at Hyderabad. So even I think MOU with RCI, and then you can go for this particular system to.
Okay.
Take.
Another thing is whatever mine-like object you are detecting, because it is real-time processing, real-time data processing you are doing, and based on the location of that object, so that if neutralization has to happen, then you need to have proper coordinates of that.
Yeah. So when we are detecting an MLO, we are actually getting the information of range, bearing, and the estimated lat long. So that is the information we have. So do a finer search closer to it, so that you get a better perspective of that lat long. Estimated lat longs is bound to have some error. So do a finer search, and that is why the neutralization, if you do an ROV, so the reacquisition and neutralization becomes much simpler. With that estimate lat long, your search area becomes drastically comes down, and the neutralization part becomes very fast, and it is possible to with that.
Okay, best wishes.
Regarding this INS DVL, two people are doing in India. One is ISRO, that is a lab in Bangalore, which is doing this one, and another thing in Kerala, they are integrating that one. The problem is that we tried for 4-5 years to get from ISRO's background, but ultimately ISRO could not give it actually. Then after introducing by Dr. Srinivasa Rao sir, actually, we approached RCI and the Inertial Systems Group actually. They have agreed to supply 2 numbers of that one, but still that is a joint development. So they have the inertial measurement unit alone, which is accelerometer and this one, and NIOT will co-work with them to integrate the DVL and come out with the results. Basically, it is a joint development. Probably when this is done, maybe we can patent it, and then probably this can go as a product to outside. Probably in another 8 months, I think the product will be ready, in my view.
Any other questions?
Yeah, I have one question. Sir, it is very nice to see the swarm of the AUVs in the diving. What is the minimum distance between AUVs you have maintained, sir?
Ma'am, it is actually dependent on the swath of the side scan sonar. So 200 meters is what we have actually maintained. So the swath at lower frequencies are around 100 meters for the side scan. So based on that, with some overlap, it is less than around 180, 170 to 180 meters is what we have maintained between the AUVs. Not in the one I have shown, because that is done in a lake and we don't have that wide area, but in other location we have done up to 170, 180 meters.
Okay, means that is the overlapping zone, everything.
There is an overlap because the overlapping zone is there.
Okay, thank you, sir.
We would like to appreciate your effort in starting from sea mines and entering into the coordination of multi-AUV systems and then the swarming concepts also, and ending with the mission planner. So it gives us an overall picture about the entire system. And so this speech is not only an informed one, it is also an inspiring speech, which makes us think beyond the boundaries. Thank you.
Thank you, ma'am. Thank you.
And also, we would like to say that today we are likely to sign an MOU with NSTL, but unfortunately that could not happen actually because of some administrative procedures. But however, I think in the area of INS, batteries and all these things, we will continue working.
Sir.
And let it be a formal event at the MOU. Our work can continue. Okay, sir. Thank you, sir.
Now I would like to invite Dr. Panikumar sir to honor our speaker. Now we would like to invite Mr. Shibu RM from CDAC to start his presentation, and I would like to summarize his bio sketch. He is a senior scientist heading the Underwater and Marine Systems Division of Strategic Electronics Group at CDAC Trivandrum. He has more than 25 years of experience in design, development, and field deployment of strategic underwater systems for national security and avionics applications. And his core contributions include development of advanced technologies for naval ships, submarines, amphibious vehicles, military aircraft, underwater platforms, and supercomputing systems. And he has successfully deployed several indigenous systems currently operational with Indian Defence Forces. And he has recently awarded General CDAC R&D Award in 2025, and he has couple of Best Performance Awards, Project Awards, and certificates and citation of excellence at CDAC. So he has filed 4 IPRs and authored 7 research publications in the area of underwater systems, defense electronics, and strategic technologies. Please, sir, you can continue.
Thank you, and thank you, madam, for a nice introduction. Welcome all of you for this presentation, respected senior members and distinguished guests. My name is Shibu. I represent Center for Development of Advanced Computing. I am from Thiruvananthapuram. At CDAC, we have multiple domains, starting from the high performance computing. And one of them is strategic technology. In the strategic technology, we have multiple verticals. One of these is underwater area. Here I will be presenting the AI-enabled underwater systems. This is regarding the strategic technology which we are dealing at CDAC. We have aerospace technologies and underwater technologies, semiconductor technologies, and land defense technologies. I will start with a video. This is a 1-minute video which shows our efforts in underwater and marine areas. This is the recent deployment we did at Himachal Pradesh, around 4,500 meters above the sea level. And we also developed echo sounder systems in the underwater domains, for which we have transferred the technology, and Indian Navy is using our ship echo sounders and submarine echo sounders. We did that for, now we are doing it for ICS also. This is an underwater drone which we developed around 6 years back. It's a 100-meter depth it can go. This is a ground vehicle. What I am showing here is because of the SLAM which we have developed for this application. In this area, we have some major achievements. We have, as in the video, we have completed the bathymetry survey, and we have some signed MOUs with the NDMA, and the echo sounder we have installed, and we are in collaboration with the RCA and NBL for ICS project. And we have completed the development of EM log transducer. Underwater drone of around 1,000 meters is in progress, and we completed our part in the Varanamala project. In the Operation Sindhura also we have done contributions. So coming to the main topic, it's divided into 4 parts. One is first we will start with the overview in the AI in underwater systems. Next, current development in AI underwater systems and future advancement and challenges and opportunities. Coming to the AI part of any system. So actually AI is a it's a break-even technology because in a long time before we have started we invented fire. So based on that we have advanced human, and then later it came our computers, internet. Now this is this AI, artificial intelligence, is the next transformative technology. In the AI, first we have to sense the environment and learn from that data, and then we have to adapt to change those data, and then we have to act intelligently. Now AI is, we have initiated. Now the real question is how rapidly, how fast we can adopt, integrate and leverage AI to gain strategic advantage, achieve technological superiority and drive economic growth. These are the core technologies required for any AI development and its implementation. One is the data acquisition and management. Next is the machine learning algorithms, deep neural networks algorithms. And then for implementation, you can start from any microcontrollers level to high performance computing. In the microcontrollers, if you use microcontrollers, performance will be poor, but in some applications it is possible with the tiny machine learning type of algorithms. And if you are coming to the high performance computing, there are exascale HPCs are coming, and we can use that for training your models and implement it. And then finally, for the autonomous requirement, that decisions to be taken. In the image you can see that first is the data, that is the main requirement, and then there are model architecture. There are multiple models that can be implemented in the AI area, and there should be a learning, and then we have to identify how much error it is happening and how much loss it is happening, and then we have to optimize the algorithm for the final implementation. This is a small explanation based on some experiments. So to understand, I have taken the example of an echo sounder. If you see the left side, in the conventional DSP or filter based approach, we used to have in the amplifier there are analog filters, and then at the digital side there are digital signal FIR filters. That type of thing we used to develop. In the machine learning or artificial intelligence era, there will be a convolutional neural network, RNN. That type of things will be implemented. If you see, when we are doing a conventional signal processing algorithm development, we used to focus in the time domain, frequency domain approaches, and we will be seeing the phase, amplitude. But when you are going for the machine learning algorithms, what we saw that we are extracting around, in this particular case, we have extracted around 16,384 parameters. But when we write programs in around 10 years back, we are using only 3 parameters and noise threshold, gain adjustment. That type of parameters only we used to have. So with these machine learning algorithms, we have done that CNN with the UNet algorithm. We got some improvements in the signals. So left side you can see that that image in the conventional algorithm should be like this, at the bottom, and then right side it will be more clear. We have done the testing at the lab only, not implemented in the ships or submarines. To implement it, because at the underwater domain, what we are facing is the lack of data. So this underwater environments are highly dynamic and unpredictable. So what we are thinking is, along with its operation, whenever it is going for its operational requirements, it has to collect the data. and that data to be labeled properly, and then it will be stored in the submarine or ship systems, and then later we can train in that system itself, and then we can implement it. So we can initially we can simulate, and then with the actual data you can correct it. You can see that a model training framework. What we are planning is the data collection. We have to get the operational real-time data from submarine ships, AVs and test ranges, and then data to be prepared for before implementing the machine learning algorithms. You have to properly label it and annotate it, and then it will be implemented using a neural network. Basically, fundamental element of a neural network is multiply and accumulation only. So that MAC algorithm we can implement, and then we have to do the continuous and federated learning approach. Federated in the sense there are multiple systems in multiple places, so they can learn together, and then model can be improved. And Edge AI for underwater and marine platform, that is the implementation strategy, and if it is required we can integrate with the digital twin integration, and infrastructure is HPC and AI. Now coming to the current development. At present you can see the step 1, people used to have the data collection using Internet of Things, and then data will be transmitted seamlessly. But in the underwater there is a limitation due to the bandwidth. And that step 3, we have to do the analysis, and then we have to take predictive actions. This is the autonomous bathymetry vessel which we developed at CDAC. This is having a control system, a navigation system, and a telemetry unit, and this sensor suite. Here we use the technologies, AI algorithms that support vector regression process data, that process data from the multi-beam echo sounder and LiDAR to create a high resolution 3D maps. And we use advanced autonomous bathymetry with AI, this AI, and its features are we are filtering the noise out of the sonar, and we are doing the predictive modeling and integrating that sensor fusion with mmWave radar, LiDAR, and optical camera. And final deliverable was 3D digital terrain model of the seafloor. And these are some use cases. Actually, I didn't do. My colleagues did this, and it's suggested that we can do this AI-based systems for the coral studio, for the coral studies and preservations. And bottom, it's a AI enhanced vision in turbid waters. You can see that the original it is turbid, and AI enhanced is more clear. And underwater inspection also we can use it. Marine ambient noise measurement also we can use AI methods, and AI can be implemented in the drones, and object identification and species also we can classify, like fish finder systems. This is the intelligent ocean network. Basically the technical and operational challenges are the communication and signal processing, and method for the energy efficient implementation, and its battery life. Because if you are implementing the AI algorithms, it needs more computational power. So that will take more energy and more computing power. And of course, time delay also will be more. These are the data sources and the key challenges for the AI systems, that is in the underwater systems, and the sonar and acoustic signatures are the data, and we need to have the camera and video information, pressure depth navigation information, temperature salinity, and structure health information. The major challenges in the data is noise. It will be noisy, and data may be incomplete, visibility is poor, and it's because of that is very hard to label. So this is my concluding slide. Now actually AI has moved from experimental to essential in marine industries. In the future, digital twin is, now also it is there, but fully operational digital twin, I'm not sure it is available. So real-time digital replicas of entire ocean and its operational systems. Operational systems in sense, like ships, submarines, AUVs, that type of things. And then hybrid communication for more bandwidth. And AI is the key to seeing and understanding the 95% of the ocean that remains unexplored. But we also feel that AI is not the solution to all our problems. Thank you.
Questions from the audience?
In what respect of application for underwater? See, one is picture enhancement. There are a lot of technology available for picture enhancement from noisy environment. What way what you showed was different, because you know the picture enhancement, even the modules are available on your desktop itself. So in what way you did better job using AI compared to normal picture enhancement techniques? I couldn't get any feel of that.
Sir, if you see the example of echo sounder, actually that noise, actually environmental noise is very high when it is going to for the operational type of things. So there actually we can apply the AI technologies to improve the signal. That we are improving the signal processing algorithms actually in that side.
I understand. Basically, it's a blur picture for various reasons. One is, of course, turbidity. There's a lot of floating, but that is applicable even when I'm taking pictures in, let's say, an other environment with smoke and all that. And those techniques are available. So I don't know, specifically, I see you use that only for that purpose. Elsewhere, similarly, when your last two statements, I couldn't see any correlation. See, if seize and explode 95%, in fact, more than 95%, AI can't do anything of that. I need equipment to explore that. AI can only, in what way, I don't know how AI can help that. 95% limit 95% if I don't apply more observation. Similar to other statements outlined in the last slide, they have nothing to do with AI. They are actually factual statements and they're true. So point a correlation of, see, AI can do many things, I understand that. But in the context of, your main job was to really do the ocean survey. In that, how AI will enhance, I couldn't get the clarity at all.
Sir, I understood, sir. Actually, that initially you told that regarding the image processing. Yeah, that clarity. But actually, sir, there are algorithms available for enhancing the images. But they are conventional algorithms, which is not learning from that image qualities. So that is why that artificial intelligence comes in that side. Yes, sir.
Actually, my question also stems from the same thing, that how will AI help? Because I believe AI is to remove the cognitive load from the human being.
Okay.
What you don't make sense of because it becomes too much for a human to process. And there AI comes and helps you to make sense of the data. Here the challenge is we don't have data itself. I don't think so we have reached the limit of human cognition in exploring the underwater world. So the challenge is the physical sensors and the collection of data, and which you can train the AI on, because at this stage AI will hallucinate, and if the image enhancement, he will assume something there. In fact, you have written 95% of ocean, so this is just my doubt. He can assume some marine animals which don't exist. So that is the challenge which you are facing the real world also, because AI is prone to that, and real world application of AI is still limited.
Yes, sir.
Where we have plethora of data, and underwater we have hardly any data to train the model itself. So that's my question.
Sir, actually, that's correct. We don't have that much data. So that is why we suggest that, because getting underwater data is very difficult in all conditions. That is there, sir. That is why we are suggesting that there can be one method. So if you have a system already installed, that is why I made the example of echo sounder. That is a very simple system. So that echo sounder is actually in all Indian naval ships and submarines. So if you have the data continuously stored, now actually the data is stored, that compressed data is there. So that data can be used for enhancing the echo sounder algorithms.
Sorry, but echo sounder is just pulse, distance, time, mathematics,
Correct,
intelligence. What kind of data we want? We have to define a data framework itself, first of all, which we don't have. What all sensors, what data to be collected to understand the ocean, correct? Then only we can make sense of, end use.
Correct, sir.
Or am I speaking because I am not a technical guy?
Okay.
I'm just a user.
Yeah, I have actually, sir, one small thing. Time is running up. You can discuss during lunchtime and etc. So, okay, please ask, sir, Nandi, sir.
Yeah, okay. I am giving just one example. I think we are developing the proof of concept of homing docking system. So we have used, the dock is having some specific shape, so like funnel shaped dock. We have collected the data using sonar, so that which is the front side, which is the back side, which is left side, which is right side of the dock, so that when AUV is deployed and we have instructed the AUV to enter through the front dock, and due to uncertainty, the AUV may deviate from that, from that actual position. In that case, it is drifting and arrived at the left side of the dock. Then this AI-based algorithm, it is helping us that this is the left side. I need to take a decision to go back and again come to the homing position and enter inside the dock. So this is one of the application I am telling that we are utilizing for homing docking purpose, sir. It's a learning based methods. Yeah, might be other options are there, but here we are using, with the data set, we are learning that. We have made the AUV learn that if this kind of situation arrives, then you go back, come to the homing position, and again enter into the docking station. Okay, thank you so much.
Actually, sir made a correct point only. Actually, for all requirement, AI is not required. That will overkill your processing and times.
Yes, sir. Can we proceed, sir?
Thank you.
Now I request Dr. Venkateshan, sir, to honor the chief guest speaker.
Thank you, sir, for your comprehensive framework on AI implementation in underwater systems, starting from the main framework of AI deployment and edge AI concepts, and connecting it with the bathymetry survey and seabed mapping, which gives us a very clear ideas about the concept. Thank you so much.
Thank you, madam. Thank you.
Our next speaker is Mr. Babu Jadhav, scientist, Center for Artificial Intelligence and Robotics, DRDO. He is a scientist at CARE with 20+ years of experience in robotics R&D, extensive work in autonomous robotic systems for hazardous applications. His research expertise includes autonomous manipulation, bio-inspired robotics, additive manufacturing, mobile robots and robotic arms, aerial robotics and intelligent control systems. His core contributions are design and development of advanced autonomous robotic platforms, expertise in robotic prototyping, navigation, and intelligent autonomous systems. Research achievements includes international conference publications, granted patents in robotic technologies. His awards and recognition includes Young Scientist Award, Technology Group Award, Popular Science Communication Award, and Spin-off Award for Hazardous Robotic Systems Development. We would like to call upon Mr. Babu Jadhav, DRDO CARE, to present his session on bio-inspired systems.
Good afternoon, all. I am Babu Jadhav from Center for AI and Robotics, CARE DRDO, Bengaluru. My presentation is nothing to do with underwater systems because I am mainly presenting the land-based systems. At the end of my presentation, I will give you some connection between this presentation and the underwater systems. So to begin with, I'll introduce you to what is bio-inspired system, their important key aspects, key components required for building bio-inspired robots, and their applications. Then I will discuss about what are the types of locomotion available on ground in nature, followed by brief technical discussion on legged locomotions. And then I will conclude my presentation by showing you various types of bio-inspired robots. Okay. Bio-inspired robots developed at CARE. So let's get started. What is bio-inspired robot? Bio-inspired robots are machines designed by emulating structure, functionalities, and behavior of living organisms such as animals, insects, to solve complex engineering problems. So for building various systems, what engineers are doing is they are trying to mimic various concepts of biological systems for their living. So key aspects of bio-inspired systems are locomotion, sensors and actuators, soft robotics, and their adaptability. So what is locomotion? Locomotion is basically a mechanism used by a robot for moving from one place to another place. How BI robots move? They move by emulating movement strategies of biological systems, such as walking, crawling, swimming, or flying. They use sensors to perceive environment, and the design of these sensors are inspired by eyes, ears, skin, etc. For motion of their joints, BI robots use actuators mimicking biological muscle functionality. For safe interaction with humans and to navigate through narrow spaces, BI robots utilize flexible materials to mimic soft-bodied creatures. Like biological systems, BI robots are adaptable and therefore they can be used in unstructured environments. Following are the key components required for building BI robots. Joints and structures are required for building locomotion mechanism and body of the robot. Various types of actuators are required for motion of the joints. To generate map, localize within the map, to detect objects, and for obstacle avoidance, they need various types of sensors. Various types of controllers are required for controlling motion of the joints. To process sensory data and to generate control commands, we need CPU along with GPUs. And to communicate useful information to the user, we need communication link in the form of LOS or non-LOS. And power pack in the form of battery or IC engine is required for powering the entire system. And following are the applications of bio-inspired robots. They could be used for inspection, search, and rescue operation in narrow and hazardous spaces. Examples are snake and insect-like robot. They could be used for underwater explorations. For example, biomimetic robot that mimic swimming motion of the fish can be used. Aerial drones, they are in use everywhere. They could be used for weapon delivery, surveillance, and reconnaissance. And BI robots can be used for medical application as well. For example, soft and flexible robots can be used for performing minimally invasive surgeries. So as I explained in the previous slide, various key important aspects of BI robot. In the interest of time, I will be covering only the locomotion part. So let us see what are the type of locomotion available on ground in nature first. So we have crawling, sliding, running, jumping, and walking. It is clear from this slide that legged locomotion is dominating type of locomotion on ground. And therefore, in the coming slides, I will be explaining the basics of legged locomotion. So why legged locomotion? Because they navigate rough terrain using discontinuous contact points. They are versatile because they can walk, crawl, and run using active joints. And they cause little environmental damage because of limited contact between foot and the ground. However, they are considered as costly type of locomotion because they need more number of active joints, complex control system, and they consume more energy compared to other type of systems. Robotic legs are classified based on leg configuration, number of legs used for building a robot, and number of degrees of freedom used for building a leg itself. So under the leg configuration, we have two types of legs, reptilian and mammalian leg. If the axis of hip joint is first hip joint is vertical, then they are considered as reptilian legs. And if the axis is horizontal, then they are called as mammalian legs. Under number of legs used for building a robot, we have 6, 4, and 2-legged 2 legs. 6-legged robots are considered as statically stable robot because they always have 3 legs on ground, and therefore insects like spider can move immediately after birth. 4-legged robots have quasi-static stability, and therefore example is that goats take few hours for stable walking. 2-legged robots or humanoid robots are considered as dynamically stable, and therefore they need very complex control system for stable walking. And example is humans take few months for walking, stable walking. So under classification based on number of degrees of freedom, we have 2 legs, 2 DOF and 3 DOF leg. 2 DOF leg shown here has 1 hip joint and 1 knee joint, and they are considered as non-holonomic leg. 3 DOF leg shown here has 2 hip joints and 1 knee joint, and they are considered as omnidirectional legs. So unlike wheeled robots, stability is very, very important consideration in legged locomotion. Stability is basically capability to maintain a given body posture. We have 2 types of stability, static and dynamic stability. A legged robot is said to be statically stable if a projection of CG falls within the support polygon, and dynamic stability is achieved through active control of the leg motion. Can you play this video, please? This video basically shows not able to play. Go next. Yesterday I played it. So basically that leg, what that video shows is that as long as the leg is moving, it is stable. Once it stops moving, it will lose this ability. That is the meaning of dynamic stability. So let us see some of the gait terminologies. Gait is defined as a sequence of foot placements. This picture shows 3DOF leg. During the motion of a robot, either foot is on the ground or it is in the motion. When it is on the ground, it is called as stance phase, and when it is in motion, it is called as swing phase. And the time required for completing both the phases is called as cycle time. So duty factor beta is ratio of stance time by cycle time. Beta is basically used for designing various gaits of robot. Lesser the value of beta, higher the speed of robot, and vice versa. So we have 2 types of gaits, statically and dynamically stable gait. Under statically stable gait, 4-legged robot has only 1 type of gait called tripod gait, whereas 6-legged robot has 3 types of static gaits. Under dynamic gaits, 4-legged robot has trot, bonding, gallop, and pacing gaits. So as we discussed, quadruped robots are basically 4-legged robots. As I mentioned in the previous slide, it has 1 static gait and multiple dynamic gaits. There is a pointer here. See, I have a pointer here. This one. Sorry. So in case of crawl gait, 1 legs move at a time while 3 legs are stationary on the ground. And in case of, these are dynamic gaits. In case of trot gait, only diagonally opposite legs move at a time while other pair is on the ground. And in case of pacing gait, 1 side legs move at a time while the other side legs are on the ground. And in bounding gait, rear legs move simultaneously while front legs are stationary on the ground, and vice versa. In case of 6-legged robots, that is hexapod robots, we have 3 static gaits, tripod, wave, and ripple gait. In case of tripod gait, 3 legs move simultaneously while remaining 3 are on the ground, and in case of wave and ripple gait, only 1 leg move at a time. And the sequence of motion of legs are given here. So using the concepts I explained till now, we have developed various types of bio-inspired systems at CARE. So this is how our division has evolved over the period of time. We have worked in the area of industrial robots, bio-inspired robots, autonomous navigation, perception and autonomy, and cognitive systems. Under the category of bio-inspired system, we have developed various robots, a hybrid legged wheel robot, 6-legged robot, 4-legged robot, snake, flying robot, and wall climbing robots. Now I will show you these systems one by one. So this is the hybrid legged wheel robot. Basically the design of this robot is based on 6 active wheels with passively articulating legs. The advantage of this design is that it ensures continuous wheel to ground contact to maximize traction force, and the robot is capable of climbing vertical step height equal to 1.5 times the wheel diameter. The robot can be wirelessly controlled using this joystick up to a distance of 300 meters. Can you play these videos? So these are the 2 prototypes we have developed. This video shows a prototype 1 and 2 negotiating very complex terrain. So prototype 2 is a miniature version of prototype 1 because this miniaturization was possible because of advances in motor and battery technology, and the whole structure of the body, structure of the robot was built using RP facility availability here. So these are the hexapod robots. Play these videos, please. These are the 2 prototypes we have built. Prototype 1 has 2 legs and tactile sensors for obstacle avoidance. It can walk like cockroach and ant. Prototype 2 has 3 DOF leg. It can walk like crab. It has omnidirectional capability. And here, since number of motors are very high, we have approximated kinematics using polynomial. And prototype 2 can avoid obstacle using IR proximity sensors. Here, both the prototypes use distributed controllers, master controller for generating the gate, and each leg has their own controller for executing the trajectory. So we were always asked a question whenever we showed the demo of our robot, that what happens if a robot falls upside down. So to answer that question, we have come up with a new design called a lockpot robot. It has self-righting capability. It can do self-righting in 2 ways, lateral and longitudinal axis. And this self-righting is possible. The important consideration in design to make the robot self-righting is number of degrees of freedom of a leg, joint range, and location of the CV. So this is the final prototype of hexapod robot. It again uses 3 DOF leg. It has omnidirectional capability, meaning maintaining the same heading, it can go from point A to point B in a straight line. It has ultrasonic sensors for obstacle avoidance. We have implemented tripod gate in all the 6-legged robots, and it has a rough terrain capability. These are the 4-legged robots. We have developed 2 prototypes. Prototype 1 uses 2 DOF leg, and we have implemented crawl and trot gate here. And in case of prototype 2, it has 3 DOF leg, and it has hybrid locomotion because there is a wheels instead of foot. Whenever it is walking on the flat surface, it uses wheels, and whenever it is taking turn, it uses wheels. Here also we have implemented crawl and trot gates. It uses ultrasonic sensors for obstacle avoidance. And the potential applications are, it could be used for logistics support. So we have also worked in the area of snake robot. This slide basically shows the general steps we follow in our design process. We start with the concept, then build a mathematical model, followed by simulation and prototype development. These are the 2 prototypes we have developed. The design of these prototypes are based on 14 active joints with alternate horizontal and vertical axis. Prototype 2 has free wheels to emulate differential friction. Here we have implemented lateral undulation gates, side winding and rolling, and also caterpillar gates. It has wireless camera, and it can hood up for covering larger area, and the potential applications are, they could be used for constricted areas like pipes. So we have also done some work in the area of flying robots, basically the entomopters. The prototype 1 could be launched from hand, and prototype 2 can take off from the ground. The design of these prototypes are based on X-wing configuration powered with single DC motor through modified slider crank mechanism. So this is the latest development at CARE. This is basically called a dual arm robot arm for object manipulation. It basically resembles upper half of the human body because it has 2 hands and 3-finger gripper, and each arm is having 3D. Each arm is having 7 degrees of freedom with 3-finger gripper and 2 kg payload capacity with a maximum reach of 1 meter. It has head with pan tilt mechanism, and head is mounted with stereo camera and 3D lidar for perception. It has GPU with 32 GB RAM. Position, velocity, and torque control are possible here. It has various modules, software modules, the perception module for object detection and segmentation, motion planning module for detecting collision-free spatial paths and trajectory, and grass planning module for basically detecting grasp, where to hold the object. There is a EtherCAT for robust communication, and there is a UI for definition of C9 task. So these are the videos showing a robot performing various tasks. Here basically user defines higher level tasks. For example, if you want to do pick and place operation of a robot, user need to define only the object name and what task it has to do, what task the robot has to do. Rest everything is done by the robot autonomously. So these 2 videos shows pick and place of different objects, and the bottom 2 videos shows assembly operation of like bottle opening and some bottle inserting inside a pipe. I have last one more slide. So we have custom designed Gazebo, an open source simulator for simulating aerial, ground, and underwater vehicles. With this customization, now it is possible to model environment as long as 3 km by 3 km. And there are various weather artifacts and primitive models available. Readily one can use them. There are sensor models and robot models are also available. We have developed at least 3 default scenarios: desert, urban, and village. User can directly use them for simulating their systems. Thank you. So before I conclude, I wanted to bring some connection between my presentation and the underwater thing. That recently we have signed an MOU with NIOT for identifying and modifying some of these systems so that they are suitable for underwater applications. Thank you.
Now open for questionnaire.
Thank you very much for a wonderful presentation, and we were able to see the flying robots and all. It's quite interesting. So in your presentation, you said something about 7 degrees of freedom. So what is that actually? What is the 7th degrees of freedom?
If you see human hand, we have 7 degrees of freedom. In the sense, basically it has 7 motors and 7 joints which it can control independently.
Okay.
So if I want to, let's say this is an object. If I want to pick up this object from various orientations, if I have less degrees of freedom, it's not possible. I need to have some, in this space we have 6 degrees of freedom, we have one extra so that I have redundancy. I can go and reach the object in various ways.
So you are adding one more degree of freedom more than the spatial movement. That's what you are telling.
Yes. It basically gives you an advantage of redundancy. I can approach a particular object from various directions.
Okay, thank you. And this flying robo, the flaps are made up of what material?
These are now normal, these plastic seats and the carbon rods, carbon composite rods.
Carbon composite.
Yeah.
So they were able to withstand the forces that is coming in.
These are all handmade in our lab by one of our scientists with glues and things like that.
So
they are
how
not
far,
the professional prototypes.
How height it can fly actually? How much height?
As far as I remember, it approximately 50 feet. That height only we were testing. We have not tested it in high windy conditions and things like that.
Okay.
One more thing, what I wanted to mention here is that these are not, none of these systems are official projects. These systems we have built using resources left out after finishing our main projects.
Sir, one more question. In a human gate cycle, it will be a stand phase and swing phase will be there.
Sorry?
Sir, in a human gate cycle, stand phase and swing phase will be there. For in a robot, it's...
Can you,
in human gate cycle,
human gate cycle, okay.
Stand phase and swing phase will be there. Swing phase will be help of gravity, we can achieve that in human gate. But in robot, it's possible to do that.
So what is your, if I understand exactly your question?
In human gate cycle, stand phase and swing phase will be there. Swing phase will be achieved by help of gravity. Like gate, then only we can achieve the gate cycle. So in the robot, it's possible to achieve that swing phase with help of gravity. You try that or?
No, you are talking about passively articulating legs, right? If I am having active legs, it is possible. And every robot has both the phases, stance and support for both are there. That is there. ZMP is one of the thing. Like I was mentioning, for static stability, in order to have static stability, the projection of CZ should always fall within the support polygon. Otherwise, we have to go to dynamic stability.
I have not followed CARE for almost 10-15 years now. Is there any product gone anywhere, either to armed forces or to agencies like NTRO or anything that has gone out of CARE? I'm asking a very frank question because I've been following since inception of CARE.
Nothing has gone out of CARE, whatever I showed till now.
No, I'm talking overall in CARE.
Overall, many systems. For example, we have developed a robotic system for inspection of nuclear power plant steam generator tubes. I was the lead in mechanical design of that system. We have delivered at Narora Atomic Power Station, UP, and it was developed during the time of, there was an embargo on import of nuclear-related technologies, and that system is being used.
Is it gone and used there? That's all I want to know.
Yes, that is one.
Okay.
Second thing is we have used for ultrasonic scanning of LCA wings, and we have delivered that system to HA. Third thing is ion beam polishing of mirrors, which ISRO uses those mirrors for taking high-resolution images. Like that, we have delivered many systems.
Ion beaming polishing robot came from America. I was the person
we have not developed the hardware part.
I was the person who actually funded that completely. It was on my supervision.
Okay.
Developed by TJK Murthy. Hope you know him.
Okay.
It was TJK Murthy who developed it. Okay.
Sir, we have not developed the hardware. It was only the algorithms for. Encryption system, we have delivered many, but yes, sir.
Sir, actually, can we proceed, sir? Actually, it was a really inspiring talk, and very happy to see from walking robots to flying robots, which are inspired from nature, and it is really helpful to our subsea environment, which we have started now. We are in the baby steps. Okay, so now...
we would like to call upon Dr. Vinith Kumar, sir, to felicitate our speaker.
Now we would like to invite Divakar sir to start his presentation, and I would like to give a brief introduction about him. He is alumnus of National Defence Academy. He joined submarine specialization in 2009, and he has technical expertise in submarine operations and underwater warfare. In anti-submarine warfare also he has got a very good technical expertise, and he has been the part of strategic naval operation and mission planning. He is one of the operational leadership of conventional submarines. You can proceed, sir.
Good afternoon to everyone present here. For the next 15 minutes or so, I, Commander Divakar from the Naval Headquarters, would present to you the broad contours of underwater domain awareness. This presentation has been kept generic, specifically considering the nitty-gritty of the topic involved, and any questions which are specific would be taken up subsequently. The scope of my presentation is as shown on the slide. Who else other than the men in whites would have a better understanding of the maritime domain awareness and the various challenges associated with building and sharing a comprehensive common operating picture in surface, air, and the underwater domain? Over the past many years, significant emphasis has been laid by the Indian Navy on achieving maritime domain awareness in its areas of interest. However, if one looks closely, we realize that the maritime domain awareness we presently concentrate on is more focused towards surface and the air components. The opaqueness of underwater realm has kept the subsurface domain elusive in scales incomparable to the surface picture. It may not be an overkill to state that the MDA that is currently available to the country through various mechanisms piloted by the Indian Navy is missing a credible underwater element. So, what is underwater domain awareness? Underwater domain awareness pertains to developing seamless operational picture in the undersea domain, including all natural and man-made entities operating therein. The two key words in this definition are natural, which relates to the understanding the environment, and man-made, which corresponds to the platforms and the equipment which are deployed thereon. I will now cover the perspective of maritime domain awareness. There are various government agencies which are constantly involved in gathering underwater domain awareness data for environmental exploitation, fishery management, generation of tsunami warnings, academic researches, and military applications. Majority of these agencies function under the Ministry of Earth Sciences, Ministry of Science and Technology, Ministry of Mines, and dedicated underwater research labs under DRDO. The Indian Navy has formal MOUs with these government agencies for sharing oceanographic, meteorological, acoustic data, and the prediction models. For an effective UDA chain, data which comprises of oceanographic, hydrographic, and acoustic data is very critical, as the same is utilized for design and development of underwater sensors and also the associated modeling software. This data, when supported by external intelligence and analysis, helps in effective sensor utilization for tracking and surveillance of the subsurface domain. The broad necessities of UDA are enlisted on the slide. As brought out earlier, UDA contributes significantly to developing the overall MDA, apart from providing economic security by facilitating regulated exploitation of the blue economy and prevention of illegal exploitation of our nation's rightful resources. UDA also plays a significant role in disaster management, wherein features like seismic tracking help in providing sufficient early warning on impending natural calamities like tsunami, or even helping enforce MARPOL compliance. UDA also helps authorities differentiate between natural and man-made objects on the seabed, thereby ensuring security apart from playing a major role in operational planning. Having understood what is UDA and the significance of UDA, I shall now be covering the means available for surveillance of an underwater contact. The available means of surveillance can be broadly classified into acoustic and non-acoustic sensors. The acoustic sensors would remain the mainstay of underwater detection. Various means of non-acoustic sensors are also shown in the slide. Acoustic energy traverses through different paths underwater. It is important for us to have a good understanding of underwater acoustics and sound propagation to optimally utilize acoustic means for detection of underwater contacts. The various paths that an acoustic wave traverses post emanating from an acoustic source on the surface is shown on the slide. The same was also covered by the presentation by NPOL Kochi. I shall now be covering the various UDS sensors utilized for underwater surveillance. The UDS sensors can be broadly categorized into three types as shown on the slide. Static sensors for UDA are required for persistent surveillance at specific locations, which would act as an initiating trigger for subsequent action. These sensors are either seabed based with direct connectivity to shore controlling stations, or buoy based solutions which should relay information to shore control station via SATCOM connectivity. Indian Navy, along with DRDO and industry partners, are progressing with the design and development of various static sensors such as FOIDs and Phosphonet presently. The mobile sensors are meant for wide area surveillance of contacts of interest. This has historically been enabled through CERTAS ships with theater level sonars and ASW ships fitted with hull mounted and towed array sonars. Various autonomous platforms like autonomous surface vehicles with ASW sensors, autonomous UUVs, wave gliders, and buoyancy gliders could also be utilized for the same. Airborne and satellite sensors can be utilized in surveillance of underwater contacts. A sonobuoy field deployed by fixed-wing aircraft and helicopters may be utilized for detection of underwater contacts. Satellite-based surveillance and surveillance through deployed buoys also contribute to monitoring of underwater contacts. Having understood the basic necessities for development of UDA picture, let me now move on to the focus areas that need to be progressed towards attaining the aim of a comprehensive underwater domain awareness. As one can glean from the screen, a 4-step process would be required to be pursued towards developing a robust UDA setup. I will be dwelling on each one of these steps in the subsequent slides. The first step in the development of a UDA chain is the collection of required data. As I brought out earlier, different acoustic and non-acoustic sensors are required to be deployed across the IOR for collection of requisite data in an actionable format. Sources of data vary from fixed seabed arrays to portable deployable buoy networks, to low-frequency towed arrays deployed from ships, to use of submarines and UUVs and AUVs, to deployment of aerial platforms towards radar and EOIR monitoring, in addition to deployment of and monitoring of sonobuoys. The next step in the process is information transfer. This helps to filter out actionable data from a tranche of gathered data. This information transfer can take place using terrestrial links like seabed or cable satellites, or satellite link as a sensor would necessitate. The next step is the most critical of the steps, and it includes data analysis and integration. Data gathered from various deployed sensors is required to be analyzed towards development of a single coherent picture. Thus, the final step in UDA, that is presenting a single coherent picture, is enabled through data collation, analysis, correlation, decimation, and selective archival of data gathered by UDA sensors. Presently, the Indian Navy collates and integrates data from various civil agencies under Ministry of Earth Sciences, Geological Survey of India, and Ministry of Science and Technology through established MOUs. The strategic requirement or the thrust area of UDA is the development of a national framework. The national framework thus arrived would aid in optimal dual use of UDA, that is, for security purposes in the military domain and from academic and furthering research in underwater domain for scientific fraternity in the civilian domain. Progressing The stated focus areas towards defining a national framework is thus an immediate requirement for enabling the nation to unearth the complete potential of a robust underwater domain awareness network. With this, I've come to the end of my presentation, and I'm open to any specific questions if the audience have any.
Do you have any questions from the audience?
Thank you for the presentation. I had a quick query. You have so many different agencies with which you are tying up together to get the data. How do you integrate all this data together, and what are the challenges? Could you kind of elaborate on where do you see the problems, particularly with respect to integration of the data which are coming from different sources, and possibly that can probably lead to some good problem statements for academia, industry to kind of try to solve upon?
So this, the first part of the question is the national framework that has to be defined. But before that, presently we have, the Navy has MOUs towards processing and collating and processing these data with Ministry of Earth Sciences, Geological Service, and this Ministry of, which I had already brought out in this presentation. So we have limited data that is coming in right now, which as a Navy we process and we use it. However, there is still a large scope of improvement, and that needs to be pursued. That is why this, the focus area of the thrust on the national framework that needs to be defined. That is still not defined.
That's exactly what I was trying to get at. If you could specifically point at what are the challenges in your integration, those act as good problem statements for academia and industry, and really some work can happen. If you can throw some light on that, that will be quite interesting.
So that starts with data collection, the first point, sir. The data collection, because right now, 20 years earlier, it was only the Navy that was probably using the underwater domain. Right now, there are a lot of agencies that are using the underwater domain. So, and we get data, but data in an actionable format, because we do not have defined protocols for data transfer as well. The ICDS, what we would call for, that needs to be defined so that today if NIOT is deploying a buoy somewhere, and that buoy is gathering some data, that data has to be in a format that can be processed by the naval processors that are already available. So that definition of the data protocols, transfer protocols, is a start point that we should look at standardizing. And thereafter, we still have a lot of data being collected but not being pooled into the processing pool of the Indian Navy. So that all of that needs to be addressed. That would probably be the start point for addressing the larger UDA problem.
I'll just add on. Our problem starts with the definition of data framework itself. The seamlessness by which we can share data. Everybody knows that most of our systems are imported. Everybody has its own proprietary format to process the data. Why we need to understand the underwater domain is this, and why environment where we operate. As you brought up 20 years back, we were only collecting it, handwritten returns going to some agency. It's called NODPAC. It used to have tagging of geographical tagging. So that place, what is the temperature profile? But you must understand this temperature profile I can only collect where I can go to, depth. I need much greater depths where human platforms as of now don't go. First part, collection itself. Archiving. As of now, we don't have that scale of archiving where we need, because you will, the vastness of the ocean itself would say how many data points you need to have. Then the modeling. What should be the density of the data point to define an ocean environment? That is a challenge, because that is what will come from academia. I am the user. I need to know when I go there, before I deploy myself there, I need to know what kind of acoustic progressing of acoustic waves of sensor ranges I expect there. And that's what defines operating, which is my good depth to operate, which is not a good depth to operate. You understand? So that is the where challenge lies, that integration. Plus, we also collect data from our own acoustic sensors, which are on platform. But that is only localized to that agency, and because of the security of information, we cannot share it. It has to have our own agency. If I share it, I do some acoustic processing, I cannot transfer it to a second system because that system has not been imported from the same country. That handshake doesn't happen. So this is where the challenge lies, that's why we need to have our indigenous system right from the collection, archiving, processing till the time it is operationally deployed. This chain has various links and this need to marry. So I don't know, I don't have the answer, but I only have the problem.
No, this is a very interesting problem. Ministry of Science, particularly NIOT, is a, you can say, technology center. If you can give us specific requirements separately, I'm not asking right now, maybe a half a page or 1 page note. By the way, I'm Dr. Goel. We started Ministry of Science. I was the founder secretary of Ministry. So I have a deep interest in this technology center. So we will try to see, coordinate with either industry or academia, try to solve this problem. If you can give us, okay, these are the specific equipment which we are importing from various places and we would like to develop. In fact, we are having in the Ministry of Science a program to indigenize equipments, particularly sensors. So if you can give us that, what do you need? Even the platforms, 1 page note, and I can assure you, we will not make it public and all that. We will try to see that those things are addressed in a very systematic way. So I'll just request you to do that.
We thank you, sir, for your conceptual presentation on underwater domain awareness, starting from the means of surveillance, types of sensors, and digital framework, as well as entering into the national integration part. We thank you once again.
We would like to invite We would like to invite Deputy Director to honor the chair.
Thank you, ma'am. Thank you, ma'am, for your invaluable time. I thank you both. And then before we proceed for the lunch, it is our privilege to acknowledge and appreciate the invalued industry partner and sponsors whose generous support has contributed significantly to this particular workshop. May I now respectfully invite our director to kindly join us on the stage and present mementos as a token of appreciation to the sponsors. Thank you, sir. As I announce the names of the organizations, may I request one representative each from these organizations to come forward and receive the memento. CDAC representative, please. Thank you, sir. Next, I'd like Samita Marine. Thank you very much, sir, for your kind support. Next, IROV. I may be slightly quick so that we don't stand between you and your lunch. I request the partners to be a bit quick. Thank you, sir. Next, MGR. I'd like to request MGR and Nippon. Ransom Aerospace Private Limited, Electronics Lab, Unique Group, Larsen and Toubro, Microgenius, Sumukha Marine Solutions, and Oceanautics. So all this endeavor was mainly to bring industry collaborations together. Thank you very much. Can you please, yeah. We sincerely thank each of these organizers for their continued support, partnership, and commitment towards advancing underwater robotics and technologies. Thank you very much, sir. You can please. We sincerely we also extend our gratitude to all the speakers, delegates, participants, students, and volunteers for their enthusiastic contribution and active engagement throughout the morning sessions. Lunch is now served. Please join us for the lunch and networking. We look forward to welcoming you back for the afternoon technical session. At 2, optimistically, we'll try and come back. Thank you.
So good afternoon, everyone. Welcome to the next session after the lunch. Post-lunch session is on infrastructure needs. So I invite the session chair, Dr. K. Karthik Selvakumar from Pondicherry University, and co-chair Shri G. Hari Krishnan from NIOT to the dais, please. I hand over the session to you, sir.
Good afternoon to all. It is my pleasure and privilege to introduce Dr. Karthik Selvakumar, Professor in the Department of Green Energy Technology, University of Pondicherry. He did his BE in Mechanical Engineering, ME in Production Engineering, and PhD in Fluid Structure Interaction from IIT Dhanbad. He has a rich experience, teaching experience spanning across different institutes, including NIT Jamshedpur before joining Pondicherry University. His areas of research interests are fluid structure interaction, renewable and wind energy systems, flow-induced vibrations and CFD, sustainable materials and green energy. So he has several publications in SCI indexed journals and has contributed chapters in books, several books, and he holds patents, design patents, multiple design patents also. So I welcome Dr. Karthik Selvakumar, chair of this session, to start the proceedings.
Thank you for your introduction, sir, Hari Krishna, sir. Now I warmly welcome Dr. Ashakendu Samanta, Chief Surveyor, Senior Vice President and Head R&D Division, Indian Register of Shipping, Mumbai, and he is nearly 30 years of ship and offshore structural R&D development experience and postdoctoral research from United Kingdom, and his research technical expertise in ship and offshore structures, fatigue and structural integrity, underwater welding technologies, marine structural design and classification rules. And he has contributed to as a project manager for development of common structural rules, CSR, in IAFC, and contributed to ISC fatigue and subsea committees, member ISC standing committee, and as academic and research contribution, he is editorial and reviewer board member of international journals and workshops, and PhD supervisor, visiting faculty and technical trainer, delivered keynote lecture in international conference, several publications in reputed international journals. His research focus on offshore structural safety and fatigue analysis, underwater welding and marine engineering technology. I warmly welcome on behalf of this underwater workshop.
Thank you. Dignitaries on dais, off dais, my dear colleagues, ladies and gentlemen. Good afternoon, everyone. First of all, my sincere thanks to NIOT for giving me an opportunity to express my views in these workshops. You have been listening for the last days till date, many presentations related to underwater vehicles and related to that subject. My subject is a little bit of different. Indian Register of Shipping is a classification society. You must have heard the name of American Bureau of Shipping from USA, Lloyd Registers from UK. Similarly, Indian Register of Shipping is the classification society of National Classification Society of India. It is established in 1975. We are the member of IX, International Association of Classification Societies, recognized as a scientific research organization by the Department of Scientific and Industrial Research Ministry of Science and Technology. We are the sole authority in providing certificates to vessels which are plying on water. We have in marine groups are there, mainly related to your ship classifications, plan approvals, rules development and research innovations, product and equipment certifications, and related to non-course like non-marines, many other things are there, particularly industrial related and industrial training. We have the presence all over the world, from USA to Europe to Gulf to Far East and all ports of India. We had participation in the international forum like IMO, you must be knowing, International Maritime Organizations, IX, International Association of Classification Societies, ACS, that Association of Asian Classification Societies, supporting government initiatives, particularly in various committees in technical requirements, IMO and IX. We are the part of this Harit Nauka, green tugs, offshore power supplies, use of biofuels, and many, many other fields. I may not be able to take you the entire of our what organization they does, but related to these subjects, what research is going on, I can tell you these are the major areas of the research where IRS is involved. Rule development and classifications notes or guidelines related to marine, environmental protection and sustainability, which is one of the predominant subjects, particularly related to IMO, then autonomous ships and cyber safety, digitalizations and data analysis, ship structures and hydrodynamics, vibrations, noise, formal safety, risk assessment. These are the just few glimpses which I have been showing. These are the particular rules and classifications and all guidelines related to your decarbonizations and alternative fuels. Then in technology related to which is the remotely operated vessels and autonomous surface vessels, wind turbine related, biofouling, underwater radiated noise, and guidelines which is under development, wind-assisted propulsions, air lubrication systems, onboard carbon capture, and the nuclear power technology. You must be knowing that thing, IMO is going for this decarbonizations, and the aim is 2050 non-zero, net zero, means there will be no carbon emissions. So in order to achieve that things, you need to find alternatives which is not the fossil fuel. The moment you are burning fossil fuels, the carbon will emit. You may not be able to sustain after certain times. So how to arrest that things? So you need to find out what are the alternative fuels and what are the alternative technology. Discussing that things, this nuclear power is one of the important factors which I will be coming later in a bit details. These are the hydrogen fuel cells ferry for Cochin shipyard. This is the 100 passengers ferry for this. These are all hydrogen fuel ferry which is already delivered in the for different shipyards in India. This is Garden Reach shipyards. This is Cochin shipyards, and these are the new generation electric ferry. Again, it is for this Garden Reach shipyards. It is delivered in 2014. Whatever slides I have been showing that thing, it is all practical things which we are involved in. The things which I was discussing, that what are the alternative technologies which are coming. One of the things are wind-assisted propulsions. We are going back to 100 years when the vessels was floating or flying due to the air, abundance air is there, which is the environment. Right now, again, we are thinking the air which is there in the environment, how to harness that air to assist the propulsion, even it is not fully, partially, so that we can reduce the burning of the fossil fuels. So this is one of the projects where we are involved with marine. Marine means it is Netherlands, and there are many other classification societies and other industry. They are involved in a joint research project, and the purpose of these things to develop the guideline. We are also involved in this air, air lubrication systems. What is air lubrication systems? Injecting air under the hull, reducing frictional resistance, so that again the resistance will be less and your burning of the fuel will be less, and so that your carbon emissions will be less. This is the carbon captures. If you are not able to replace the fossil fuels, then carbon will be emitting. And it is not so easy to replace the fossil fuels instantly. Your technology will be evolving, and it may take decades, 2 decades, 3 decades to completely replace the fossil fuels. So in that case, you will be still using these fossil fuels. So what will happen to this carbon which is being emitted due to the usage of the fossil fuels? Can you capture that carbon which is being emitted, and you can utilize that carbon to some other industry, or at least you can put it back to the deep of the ocean? So this is called carbon captures. This industry is already there in the onshore. We are thinking how to utilize that technology on board vessel. So this is we have already developed that guidelines. This is nuclear maritimes. Alternatives or green fuels could be used to meet IMO decarbonization targets. The present renewable power generations capacity is inadequate to support the productions of the alternative fuels. So even if alternative fuels, whatever you are thinking, whether it is hydrogen or methanol or ethanol or even LNG, it may not be sufficient to reduce that entire carbon emissions. So you need to find out an alternative solutions, and this might be the game changer. This is the nuclear power is conventionally used in naval ships, submarines, and icebreaker. So why not we cannot use that technology for the merchant vessels or in the passenger vessels? Yes, there are certain risks involved, and you need to mitigate that risk. You need to find a way that how can you, because if there is some kind of a tragedy, it will be very difficult for come back again to introduce such type of technology. So you need to ensure that you are mitigating all the risk before implementing such technology. We're also involved in digitalizations. Yesterday I was discussing about this digital twin. These digital twins we have already introduced in case of this when the vessel is being built with the shipyards. But when it is in operations, there are certain difficulties because I need to get the data in order to find out the real-time solutions. So there are two ways communication has to be there. Though they are ship owners or shipyards or the other associate industries, they are also to be ready to give that data back to us to understand what is going on so that solutions can be given. This is the so far which we have been discussing about this Indian Register of Shipping. Now, what are the things we are involved in providing certifications, particularly the role of classification societies in different underwater technologies. When I am talking about this underwater technologies, my discussion may not be only limited to underwater vessels, because we have been involved in various type of underwater technologies. One of the underwater technologies is the underwater acoustics. Underwater acoustics, plays important role for marine life as well as the stealth aspect of the defense vessel, and thus minimizing the underwater radiated noise from the ships is a concern of all commercial and defense vessels. Why this URN is important? One is that naval operations, acoustic stealth, because the noise which is being propagated or generated due to the propeller or any other rotatory machinery like engines or digisets, it is being propagated through water, and if it is being detected by enemy ships, they can understand what type of vessel is flying. So this is a risk involved. So you need to mitigate, you need to mask that signature. So this is one of the aspects which naval vessels they want. And this another aspect is that for marine mammals. Whatever noise is being generated by the vessels which is flying, so it is actually affecting the marine mammals. So IMO is coming with certain guidelines, MEPC 1 Circular 833, the guidelines for the reductions of the underwater noise for commercial shippings to address adverse impact of the marine mammals. So there are various ways it can be calculated for this underwater radiated noise, and I do not want to go to the physics behind that things, rather than I can give you the overall idea how it is being implemented and who are the client where we are giving such kind of a your projects or something. This is the CFD analysis we have been doing, where the solving flow physics around propellers, and once that fluctuating pressure surface is being calculated, it is being used as a BEM model, and how the signature is being propagated due to the propeller, it is being shown here. This is the acoustic propagations using BEM model for different hertz. You can see that thing, how that things is actually being propagated for this different hertz. And this is also this calculation based on this APM, where this your ship model along with some kind of a water surface is also being meshed or being taken into account in calculating that underwater radiated noise. This is the actual vessels which we have been calculating, or which we have been doing that service for different vessels, whether it is a naval vessels, predominantly for the naval vessels, but right now for the commercial vessels also it is important, because the passenger vessels, whatever the noise is coming, it should not be affecting the passenger inside that things, because they will be feeling uncomfortable. So this is the commercial shipping noise. You can see that things, it is a particular times of this Indian Ocean regions on 15th February 2026, and you can see that thing, how many vessels are plying in that regions, and how these vessels are actually creating the noise, and how this noise actually will be affecting the mammals in that regions. So this is the, people have been doing research on that particular field to understand how to calculate your underwater radiated noise from the shipping community for a given time, how many vessels are plying, and how this particular one single vessels is generating how much noise. Underwater explosions is another field which is called an underwater technology, which is important again for this naval vessels, because if there are any explosions beneath the water, the energy will be propagating and it will be affecting the ship hulls. So it will be ultimately affecting the integrity of the structural integrity of the vessels. So it is two important things are there. One is that thing charge, that how much quantity of the charge TNT, and what is the distance between the charge and the vessel. So it is both way it will be affecting, and you can understand this is a very complicated and time-bound solutions needs to be done in order to find the effect of underwater explosions on the vessel. Because if we know how it is affecting, you can design the vessels and you can understand what could be the scantling or the thickness of the vessels needs to be done, or the structural integrity to be done, in order to understand whether it will be sustain such type of explosions or not. This is the actual project where due to the explosions, how actually affecting the hull, where the stress, how much is the stress it is being generated, and whether it will be within the allowable limit or not. Underwater welding, this is also another technology. This is a flagship project between IIT Guwahati with IRS, where we are giving some kind of a theoretical knowledge that how the underwater welding being done inside the ocean or inside the water, and some kind of a practical training also being done. Here actually, this actual practical trainings are there. This is the actual image. The participants, they are actually going under the sea or under the water, and after going there, they are doing that welding. So here, there are many things involved. One of the things is actually your theoretical things, another is the practical things. So in order to do this underwater welding, you have to first of all do this your diving, and then you have to know the welding underwater. So the sample which they have done this weldings, these samples are being tested. Different testing is being done in the laboratory, and if it is passings, after passings, we are giving such type of certificate to the participants. We have two batches, we have completed that things, and I can proudly say that things, all these people, they have got the job after doing that some kind of a training.
Sir, please conclude in another 2 minutes.
Yeah, so this is the underwater cleaning, where this due to the hull fouling, how actually it will be affecting, and due to this hull foul, the resistance will be increasing. So we are simulating that things in different way, and ultimately calculating due to the how the hull fouling is generating and how it is actually being a. This underwater tourism, another subject where you can do this. MIB 2030 has one of the key themes to promote ocean, coastal and the river cruise, and we are involved in giving such kind of a certificate for submersibles. This is 20 years back, we did some kind of analysis to viewport to give the fatigue life of these things. Underwater pipeline is another subject where we are involved in Dangote, the Nigerian conglomerate, where 108-kilometer pipeline was laid up, 48-inch pipeline, entire designs and the inspection was done by Indian Register of Shipping. This is the underwater communications. There are two ways. One is the hardware, one is the wireless. We are involved in one of the projects in Bombay where this underwater communications line was laid. The entire inspection was done by our sister concerns. This is the autonomous surface vessels. We are involved in this L&T defense and with this Majagan dock. This is the also we are we are involved in this research. We are also doing for this Cochin shipyard for this autonomous surface vessels, which is expected to be completed in 2027. This is the last slide. I wanted to say the importance of this classification society in underwater technology. You must have heard the name of Titan, which is the submersible developed or constructed by OceanGate USA. It is mainly, it was the purpose of tourism to see the wreck of the Titanic, which sank in 1912 in Atlantics in the below of 3,800 meters. This submersible has the composite carbon fiber, is 6.7 meter and speed 3 knots and test up to the 4,000 meter capacity 5 people. During the constructions, the Marine Technology Society Committee of Manned Underwater Vehicles, now called the Submarine Committee, drafted a private letter to OceanGate in March 2018 expressing concerns with the design of the Titan and urging them, the ship, to be classed by a classification society. They did not do it. You understand what is the fate of that things. And it imploded inside the ocean on 18 June 2023, killing all these 5 passengers. So this is the importance of the classification society. Thank you very much. If you have any.
Thank you, sir, for the informative presentation.
Thank you, sir. If any one of the attendees, anyone have any doubt, you can
sir,
get clarified now, or you can get after tea time.
Just one
so
question.
it is a wonderful presentation, sir, Samantha, sir. And from starting to ship registration to rules and regulation, and you move towards the industry 4.0 and rules and different types of fuels, and about that wind induced, like we move towards the past to present how we can empower whatever knowledge, like Indian knowledge system, we have multiple knowledge system, how we can explore in our real-time recent years. And decarbonization, everyone is speaking about decarbonization, so how ship is one of the logistic industry, how we can reduce the carbon in logistic industries. So it is a wonderful, insightful, thoughtful, provoking talk. Thank you once again on behalf of the organizing committee, sir. Thank you, sir.
Now I request Dr. Raju Abraham, Group Director, Mechanical Design, to hand over a memento to our distinguished speaker as our token of appreciation.
Now I call upon Dr. N.R. Ramesh, Scientist G, Group Director, Resource Exploration and Service Group, National Institute of Ocean Technology. His educational background, he is a production engineer and with the M.Tech from Ocean Technology from IIT Madras and Mechanical Engineering, PhD. And he has overall 25 years of ocean research experience, 10 plus years of automobile industries. Key infrastructure contribution, he has been hyperbaric test facility established that up to 6,000 meter plus 600 bar, unique in Asia, and pulsating flow experimental setup at IIT Madras, soil mechanic machine interaction lab at Anna University, and launching recovery system LAS on board Sagar Kanya. Research and achievements, 39 publication, yes, international standards, and 5 international patents, 8 major sea trials, 500 plus days of ocean sailing experience. We welcome you, sir.
Thank you for the introduction. Distinguished guest of the day, Padma Shri Dr. P.S. Goyal ji, former Secretary MOES, Chair and Co-Chair of the session. Dear colleagues, ladies and gentlemen, very good afternoon. Today I will be talking about the hyperbaric test facility, hyperbaric test requirement for the subsea systems and per se, and the facilities available in India and elsewhere in the world. My flow of the presentation will be like this. The requirement for this hyperbaric testing due to the deep sea environmental conditions and the background of our building this test facility here at NIOT, and the test facilities available elsewhere in the world, some of the facilities, and then our future improvements and facilities which we are envisaging over a period of time. So as you are aware, India is one of the pioneer investors in the International Seabed Authority, which is controlling the international waters, and India has been allotted 150,000 square kilometer in Central Indian Ocean Basin, out of which 75,000 square kilometer has already been explored, and then it has been handed over back to International Seabed Authority, and 75,000 square kilometer has been retained with India. And similarly, India has been allotted sites in the Southern Indian Ocean and Central Indian Ocean in 26° south for polymetallic sulfides exploration. So, and NIOT has the mandate for developing the technologies for exploration and exploitation of living and non-living marine resources. So, living marine resources, somebody would have already presented, like fish aggregation device and things like that, which are required for the fisherman community, and non-living resources mainly per se will be the minerals available in the seabed. So, in that context, NIOT is developing the technologies for exploration and exploitation of such minerals which are available in the seabed, which is the depth of which are ranging from around 4,500 in the Southern Indian Ocean up to 5,500 to 6,000 meters in the Central Indian Ocean Basin. So, our machinery has to be developed and deployed to such depths which will be used for collecting the minerals which are lying on the seabed and bringing back to the mother vessel on the surface of the water. So, as you know, the machineries which are developed has to sustain a harsh environment, which will be as cold as 1 to 4 degrees, and then a depth of around 600 bar at 6,000 meters. That is 600 times of the atmospheric pressure, which we are feeling now. So, such extreme weather conditions has to be sustained by the machinery, and in developing such machinery, we are facing a lot of testings for such machinery which has to be deployed. So, for developing, so the systems which are developed for that exploration and exploitation, we will be testing in our, we developed a hyperbaric test facility in NIOT, which is capable of testing up to 900 bar, which is equivalent to 9,000 meters depth of water. So, way back in 2007, August 15th, it was dedicated to the nation. So, which is available in our campus. It is a state-of-art facility which is only available in this part of Asia. So, these systems which are developed in NIOT will be tested in the hyperbaric test facility before they are deployed in the ocean. So, the requirements are, as I told, low temperature and of course corrosive environment, and then these machineries which are developed cannot be has to work for a long duty cycle, and you cannot deploy and retrieve very often, and hence they have to be very rugged, and the maintenance has to be very low, and it has to, the integrity has to be very strong, so that they are so much the systems are very reliable for operations to days together. So, as I told, these are the facilities which are available elsewhere in the world. One at KSRC, Krylov State Research Center in Russia. They have 3 facilities, 3.2 diameter and then 9.5 meters in length. There we are proposing to test our personal sphere of our Matsya, human submersible, which is going to be developed. Here only we are proposing to be tested. And after that, we are also proposing to build our own facility, which I will be presenting later in the slides. And one more facility is available in Norway. They have an inner diameter of 1.1 meter and the depth of 3.5 meters. And they have both have operating pressure of 1,000 bar, which is equivalent to 10,000 meters. Because the depth in the Pacific are much more. So, that is why they are having up to 10,000 bar. So, this gives the glimpse of the hyperbaric test facility available at NIOT. It is the configuration is vertical type. So, the diameter of the hyperbaric chamber is 1 meter and the clear length is 3 meters. So, a system of 1 meter dia and a length of up to 3 meters can be tested in this facility up to 6,000 meters. This facility is being used for testing the, as I told, the systems being developed for the deployment in the ocean for our machinery like crawler and other systems. So, we have to qualify for the pressure integrity and then leaks if at all any, and then functioning of the underwater motors also are possible with this facility, because there will be feed through. There will be a feed through in the top nut here, through which through the connectors you can actually feed through the power and signal cables, and the systems can be operated at the desired pressure, say 4,000 meters depth, like 400 bar or 600 bar, whatever is the requirement. we can actually operate such underwater motors or pressure accumulators and things like that, and we can see. We can also have, the facility also have a feed through for signal connectors, and then the cameras and other things can be fitted inside, and then we can visually see also. So this is the specification, broad specification. We can test up to 900 bar, and it is a low carbon steel SA 723, and then it has a clear, as I told, a clear diameter of 1 meter inside and the length of this thing, and total weight of the vessel, which includes the vessel per se and top and bottom nut we call. And it has a special closing technology of the quarter nut technology, which we need not have to, elsewhere in the world, they will be putting lot of bolts and nut for this one, or closing for several windings, but here a quarter turn will lock the whole vessel itself. And the total vessel, weight of the vessel is 26 tons, and it is sitting on a tripod. You can visit the test facility available here, and the working medium is water along with anti-corrosive medium. It is ethylene glycol base. We will be adding 4% of that to avoid any corrosion of the system being tested. And as I told, this system was dedicated to the nation in August 15th, 2007, and till now 1,600 cycles have been completed till now. So these are the glimpse of what are the tests being conducted. That is our subsea electronics, which we are some of the pressure tolerant, which will be used in the some of the items will be pressure tolerant, which will be used in the enclosures with pressure compensators, but electronics, they are put on the pressure containers. Those have to be tested along with the connectors so that the sealings are ensured. And then as you know, some of the components will be failing in the fatigue. Those things also can be tested using the cyclic pressure testing. And then electrical resistance, insulation resistance can be tested online through the feed-through available on the top nut. And then functional performance, also online performance, as I told, we can run the system and then we can see the healthiness before deployment in the subsea machineries. So typical components which we have tested so far in this our hyperbaric test facilities include pressure housings, subsea batteries, and then sensors, buoyancy modules which has to withstand that much pressure and give the required buoyancy. It should not crack, and then water absorption should not be there. So for that we have tested the buoyancy modules, manipulators and valves which are supposed to operate hydraulically at that pressure, and then underwater connectors, the sealing and then integrity of the connectors and cables, and then of course acoustic transducers also at that pressure. Otherwise, at normal atmospheric pressure, we have ATF where we can test the acoustic transducers, but at the more pressure ratings we have tested here. So the importance comes from this. So once we are testing and we are comfortable of the integrity and then the system, then we will be going ahead for the deployment in the ocean for our sea trials. Because of the importance comes from the fact that our platform, that is the vessel, at present we have a fleet of 4 vessels, 1 ocean going and 3 CRVs. Ocean going is Sagar Nidhi, which are used for most of our deep ocean deployments. So it is not, it is very precious to get the ship time, so that all the organizations in India, they will be submitting their requirements. So it is very precious. The precious ship time should not be lost because of the failure of some of the components at the rated pressure. So that gives the importance for this hyperbaric test facility, where we will be testing the components or systems per se before we are assembled in the total our machinery. So as I told, as a part of the augmentation or improvement, NIOT is going ahead with the establishment of a deep ocean simulator of 1500 bar, which is the requirement of DNV standards for our Matsya 6000 human submersible. And then so we have to test twice of the thing. So that is the DNV standard. So once we are deploying at 600 bar, which is at 6,000 meters, we have to test at 1200 bar. So that gives the requirement for a higher capacity testing facility. So we are going ahead with the establishment of deep ocean simulator, DOS 1500, means the rating of 1500 bar, and it is a slightly increased working diameter of 1250 and the same working length of 3 meters. So we are expecting the work to be completed by end of this year. It will be installed in the same place where the existing hyperbaric test facility is functioning. And we are also going ahead with a deep ocean simulator of 900 bar, but here we are going ahead with the increased diameter. This we are contemplating in our other campus because the requirement will be very high, and then the inner diameter will be up to 2800 mm, 2.8 meters, which will be almost the same as the facility in KSRC, Krylov State Research Center, and then for the length of 3 meters. And then here the configuration will be horizontally mounted, and all others will be same, like it will have a pressure ramping and things like that, and it will be complying to all the ASME and other standards. Thank you. Any questions, please?
Sir.
Sir.
Basically both are same. No. Both are not same. Simulation, listen to me, simulation word is used when you create an environment.
Similar to that.
Not similar. If I am doing a computer simulation, there is no environment. I am only solving differential equations.
Yeah.
Okay? What you are doing with the 900 and 1500, simulate is the wrong word. Put it test facility.
Test facility.
You are not simulating.
Okay.
You are actually testing.
Okay.
So just to tell you, please change the word.
Yes.
It's not a simulate because simulate gives me a feeling that you are actually not doing
the thing, and we are only simulating the condition.
like computer simulation.
Fine.
Okay, simulator word is normally used when you actually don't create that environment, but you are creating a 1500 bar.
It is a misnomer here.
It's a test facility. Yeah?
Fine.
So otherwise, it's a good word. I'm just thought this came to my mind when I heard that.
Definitely we will take into account. Thank you.
Good, very good.
Anything?
Thank you, Dr. Ramesh, sir, for your wonderful and thought-provoking presentation. Now what happened, everyone, we move towards Atmanirbhar Bharat. So whenever we see your presentation, whatever facility we are going to set up, that is, we are moved forward ahead of many facility. We no need to depend upon other foreign countries. So it is, day by day we will expect more facilities, in-house development made in India. That will be from scientists like you, many people working on that. And first kudos to NEOT team and all the directors and management. And once again, thank you for your presentation.
Now I request Sri C.R. Deepak, Head of Quality Control and Swachh Bharat, to present a memento to our distinguished speaker as a token of our gratitude and appreciation.
Now we invite Dr. G.V. Pavan Kumar, Naval Architect and Marine Engineer, Faculty, School of Naval Architecture and Ocean Engineering, Indian Maritime University from Visakhapatnam. And he has overall professional experience of 16 plus years in ship design, shipbuilding, ship repair and maritime consultancy, expertise in vessel design, structural analysis, project management and marine acoustics, research and technical expertise in ship design, structural calculations. So we welcome you for your wonderful thought-provoking talks in the area of shipbuilding and towards future sustainable goals.
Good afternoon, one and all. Myself, I am Pavan from Indian Maritime University, Visakhapatnam. The topic of my presentation today is on the advancements in the research fleet specific to Indian scenario. Though the topic is slightly different from the theme, but we see here that research vessels play a very important role for ocean exploration activity or whatever ocean studies need to be done. Research vessels are a must. We have seen over period that there have been lot of design improvements which have evolved in the conventional shipbuilding activity. I want to keep specific to research vessels. What are the designs that can be adopted for the future research vessels? I'm from this campus in Visakhapatnam, where we carry out academic courses of undergraduate and postgraduate in ship design, that is naval architecture and ocean engineering. Earlier we were known as National Ship Design and Research Center, NSDRC. We have contributed to a lot of indigenous ship design and shipbuilding for MOS research vessels, as well as most of the passenger ferries that fly in Andaman. Looking at the international scenario of existing research fleet, we observe that there are more than 350 plus research vessels which are operating for major ocean exploration activities. Among them, if we see, the most of the percentage of research activities happening in the coastal regions. They are broadly classified to global, international, regional, but looking at the scientific programs that have been carried out, we see that the demand for research vessels to operate in shallow waters is much more compared to the deeper waters. And we see that the major fleet holders in the world are Russia, USA and Japan together, where they hold more than 60% of the total research fleet. And in US and Europe, we see that the interesting observation what we found out with the latest statistics is that all these vessels are getting old. The normal service life of a ship, conventionally we take it to be 25 years, but we see here that ships which are operated by Canada, Russia, Australia and Mexico are more than 45 years old, whereas Bahamas, Japan, Spain and Norway are less than 25 years old. So the fleet renewal program is something which is very important and which is identified to be a huge gap even in our Indian scenario. Present research fleet that is operated by Indian institutes, namely Ministry of Earth Science, CSIR and Geological Survey of India, if we see them, we see that most of our Indian research vessels are also quite old vessels. We are operating 2-3 vessels which are more than 40 plus years. And we have new vessels, Sagar, Tara, Anveshika, which are coastal research vessels got commissioned in 2018-19. So they are almost 8 years old. We also see that there are now fleet renewal programs which are already tendered out and few are under construction. But what we observe is that in the statistics, in a total of nearly 11 research vessels that we operate, other than the defense, relating to non-defense institutes, we see that of the 11, we categorize them into, say again, ocean research vessels which operate for international waters and global scenario, regional research vessels and coastal research vessels which operate in say up to say 10 meters water depth. They don't come less than 10 meters. There are certain navigational issues, but still we see that the other shallow operations which need to be carried out are mostly carried out by hiring fishing vessels. And among them we have one buoy tender vessel, Sagar Tara, which I classify to be under the regional class. Remaining all are coastal vessels and they all are conventional designs. So we see that here there is a need to enhance our fleet towards the ocean exploration activity, and more specifically we need to include more number of small research vessels. We are looking at operations in shallow waters up to say 10 to 2 meters. So instead of hiring a fishing vessel, it's a must that we have a specific scientific research vessel which can operate in shallow waters. Same time, government has also initiated the Polar Research Vessel project, which has been long-standing from a long time, but soon it's going to materialize. Looking at our present scenario of operation of research vessels, I've just made a chart to also look at the financial aspects, considering 25 years of service life. For example, if I take Sampada and Kanya, which are got incepted in 1983, should have been replaced in 2008 and 9, but still we are operating it without any replacement plan. But soon we are now coming up with framing the specifications for replacement, because there are a lot of other administrative and financial constraints. But still, what we observe here is that the cost of the vessel is going to increase if we delay in renewal of the fleet. Every year, the vessel building cost as well as the scientific equipment cost is increasing. The statistics what we have seen for Tara Anveshika, even Manjusha, which was conceptualized from our organization, 50% of the research vessel building cost is scientific equipment, and that is going to shoot up a lot. So fleet renewal planning is something which we should start immediately after we commission a vessel, which Europeans already do that. They have a perfect fleet renewal plan. The next version of vessel, what they are going to have, will be designed immediately after delivery of the first vessel. This way, we see that the approach that they have is really helping them a lot in not only reducing the cost, but also getting the product what they want for what scientific programs they have to operate. I'm also looking at other scenario of conversion of existing fleet to green. Now we have a lot of green technology, even our IR class presentation also shown that new class regulations have also come up. Why don't we look at converting our existing ships with certain green technologies that we have? We have some advanced propellers which have come up, Keppel propellers. We have even Mavis ducts with low noise reductions. We have hybrid propulsion system where not only relying on conventional engines, we should go with other combinations of battery, LNG, fuel cells as also the power source for running the machinery. We also have ballast water treatment as well as waste heat recovery systems. So I would like to say that we should also look at the feasibility of conversion of existing fleet to green. Here what we observed over the period is that in our Indian scenario, what we do is whenever there is a need for a new replacement of vessel, first we look at the financial budget availability, then we, within a short period of time, we frame the specifications, and we give the responsibility to the yard to come up with the design as well as shipbuilding. This approach has many constraints because the final product what we get may not exactly suit our scientific operations. It comes with what the yard is giving us. Though we frame the specification to our requirement, but still we have to rely on the shipyard who is going to do the job. There is the second approach where D&D, Naval Designs, as well as some other European institutes also follow, like NOVA and UNOLS. They do the entire design. They do the detailed design and only use the yard for fabrication. So this approach takes a lot of time for the initial design, but the construction time will come down. So if we can plan the fleet renewal immediately after the delivery of the first vessel itself, it gives a lot of confidence to improve the system and also to support all our scientific programs. We can see here that there is a lot more to explore considering the Indian coastline and the vast water surface that we have. And use of research vessels is something which we have to still plan properly to see that we capture a lot of data that is available. So to give you a basic understanding on the construction activity in specific to research vessels compared to the conventional vessels, these research vessels make use of scientists who are non-mariners. So the conventional design of other vessels is not applicable here. We have to see that the habitability of these vessels is much more comfort, as well as the aesthetics are more important. At the same time, the facilities that are there should be much more enhanced. We also need to look at a lot of space availability for the laboratory as well as the equipment that is going to come. The equipment will be based on the programs that happen, and there should be a modular arrangement that these provisions that are provided on the vessel should have a flexibility to interchange the equipment as on demand basis. Similarly, the new regulations which are coming up on silent requirements are much more effective to research vessels. Our research vessels should be much more silent compared to the conventional systems. So here are the options that are available for the next generation research vessels, which are multi-mission flexibility, zero emissions hybrid propulsion systems. They should have advanced sea and coastal mapping configuration to be adopted. And when we look at hybrid propulsion configuration, it doesn't mean that the ship should entirely operate on a battery system. The ship should be a dual mode in a hybrid combination, where in the total operation profile, at least if I am able to say that 4 hours duration, I'll be completely on battery, so that there is zero noise and zero emissions. So certain scientific programs which need low noise and no emissions, in such scenarios, the battery switchover will be a better option. Similarly, we are looking at modular labs. Earlier, conventional designs had wet lab, dry lab combination. Now we are looking at modular labs where, based on the scientific programs, the labs can be interchanged. Similarly, robotic integration with the handling systems. Handling systems play a very important role. I have been listening to the morning session. Field trials, there are a lot of field trials involved, deployments, retrieval issues. People going on board really face a tough time in handling the objects and retrieving them. So your scientific vessel should have systems which are much more easy to operate and friendly. So we have come up with certain double articulated A-frames, knuckle frames, and even communication system that should be there. We should have wireless joystick operating system for handling systems. So such upgraded systems shall improve the scientific vessel to a great extent. And not only hybrid, we also look at wind-assisted propulsion as presented by IR class. We have rotor sails, crane sails, even kite sails, where certain period where the wind supports, we should switch over from the conventional system to wind-assisted system. This is a hybrid combination which have been brought up by Wärtsilä. In a conventional system, we have an engine which is driving the propeller. We have an auxiliary engine which is driving the throttle load. Now, we have come up with a energy storage system where we have a battery, and in a mechanical mode, you have both the engine and auxiliary engine giving power for both propulsion and throttle load. And we have a say generator mode in which the main engine is giving propulsion to the propeller and the auxiliary engine is down and battery is supporting the throttle load. Similarly, if we can go with hybrid mode where both the engines are down and completely the main propulsion as well as the throttle load is through the batteries, and we don't expect the power to completely suffice with the engine power, which will be very low in compared to the main engine power requirements. But for slow speed operations, this hybrid mode with zero emissions will be a perfect option. We also look at enhancements in the supporting systems for hosting the acoustic sensors. We have gondola blister drop kill arrangements which have come up for placing the acoustic sensors which are free from the bubble sweep that is generated by the flow. Same time, mostly we rely on the OEMs or the foreign vendors for manufacturing. But I feel that these things can be indigenously done, where if we know what is required and then accordingly we start the concepts initially within ourselves and then validate those designs and come out with a better performing systems of appendages. We also look at a combination of containerized labs, where we can also say that based on the mission profile, we can reallocate the spacing to increase the deck space or increase the lab space. And same time, we can also have precision navigation with advanced fiber optics gyro. We also look at system where we have telepresence. We see now real-time underwater imaging of ROV that is carried out is live streamed to our desktops through 4K image systems, but still we have not upgraded our existing fleet to that extent. But we feel that there is a need tomorrow, if we are able to send ROVs or send man submerged to such depths, there should be a live streaming possibility. So your vessel, when we design, we should have proper interaction with the user community to see that the design itself take care of the needs that are required. And more specifically, research vessels are deployed with crew who have to be acquainted and well trained with research equipment as well as handling system operation. Conventional marine crew may not be the right option. So we have modern fleet which have been developed to operate for specific requirements. These modern fleet that have been developed by INOLS are mostly towards mission specific. We tend to develop ships which are multi-designed. So here are few arrangements of modular arrangements of accommodation as well as lab and integrated bridge system, along with the articulated boom crane up to 4.5 to 5 meters for various scientific operations that we can carry out. These are the different combination of the launch and retrieval systems, even from moon pool or through the A-frame or through the side frame that can be done. And all these need to be upgraded to the mission requirements. As Visakhapatnam IMU campus, we were involved in designing and construction of the existing fleet. We have from Sagar Pashmi Purvi till Anveshika. So we feel that these designs are all conventional designs. So the next generation research vessels should be all hybrid. And now the new upcoming research projects which are under construction are the ocean research vessel that is being built at GRSC under the Deep Ocean mission. We have 2 coastal research vessels coming up for GSI and 1 acoustic survey vessel for NPOL. The major issue what we identify here is the specifications. We prepare the specifications and the yard comes out with those specifications and try to see that they overtake the owner's requirement. Where we find continuous struggle in negotiation with the yards. If the specifications are more clearly defined, which have to be defined with the vendors, with the availability of the systems of ship as well as scientific equipment, then there can be much more clarity. And such scenario can only establish we have longer duration in specification preparation. Mostly our working model, we see that we prepare the specification in 1 year. I feel that that will not work out. If we
are running out of time.
Yeah.
Please conclude in another 1 minute.
So we have the new technology of using AI systems also on board. We are also now looking at using Starlink internet base for data transmission. And what I see here that in the future programs from SWAN AUVs to the ocean observatory systems, research vessels play an important role, and all these future research vessels should be done in coordination with all user community so that we have the next generation research vessels which are much more capable to explore the oceans in a much better manner. Thank you.
Thank you, sir. Thank you for your wonderful presentation. A country which rules the ocean, it can control overall all the world. So it is happening in and around the world, the situation is there. So these research vessels are more significant for our nation growth, and whatever we are doing, that is a great contribution. So much more work we'll be looking forward from you. Thank you for your presentation. Thank you, sir.
So one question from my side.
Any queries from?
Avan?
Yes, sir.
So nice presentation first of all. Then you are presenting about these hybrid vehicles, right?
Yes, sir.
So which can utilize batteries and changeover, during the slow speed operations and all. So any plans for such vessels in our Indian waters? For example,
Sure, yes,
Indian
sir.
yachts or something?
Recently, we are working for a small research vessel for Incois, where we want the vessel to be completely hybrid, which will have the dual option, but less than say 10 to 2 meters water depth, slow speed operations up to 7 knot speed. It should be running for 4 hours endurance on battery.
Okay. Then recharging will be done from the engine itself, right?
Yes, yes. Recharging will be done from the engine or the auxiliary engine.
Then I think if you could throw some light on the clean ports, which are now emerging, and difficulty of our vessels to approach those ports in the future, right?
Yes.
So what could be the challenges what we could face?
IMO has come up with certain non-mandatory guidelines, but to all the stakeholders, it has requested to develop underwater noise management plans, and also to under Harit Nauka and Harit Sagar scheme of Government of India, which has come up. We are looking of a greater transition to happen with all vessels to turn out to be green. And soon, in India, it has started now. Vizag Port, we have made a underwater noise management plan, but soon emission regulations are already on, sir. 2040, we have to be reducing 50%. So regulations are there, but the transition is taking time. We have to convince the shipping companies as well as the designers. It's a big challenge. It's not so easy, but soon the transition guidelines have come out. It'll come out soon in a slow manner. But in Europe, Port of Vancouver and Port of Seattle, they have made a fantastic model of green ports, where they are also giving incentives to the ships which are much more silent. At the same time, they're fining ships which are more louder. Both way. So these guidelines will soon turn over, sir. This area is gaining importance.
One more question, actually. Yes. This is not a question, actually. This is a suggestion based on our experience in the scientific research vessels, because this topic is for scientific research vessel. Driving into the numbers, even yesterday, our chief guest was suggesting that already there is a cabinet notice moved for almost 20 ships. How we are going to realize is the different ball game. But thinking in that line, right now, if you see the scientific equipments management in the ships itself is a big challenge right now in the country. There is no big, multiple companies are not there to manage the scientific equipments which is available in the scientific vessels, including winches, when we launch even CTD and observing with the multi-beam or side scan data sets and all. That there is a lacuna there. This needs to be addressed as a policy. Then second one is the port entry of these research vessels. For the people to go inside and coming out, we need to have passport, actually speaking. For all the ports, even though it is a research vessel, and we are taking our own equipments which is coming from the institutes and going back to the institutes. In the last 30 years, I am seeing, 92 onwards, I am sailing in the research ships, but still the same methodology
Same
only.
method is there.
There should be some big policy changes should be there. Yes, sir, yes, sir. So actually, sir, he is also part of the research from the Maritime University. That's why I am putting forth into the forum. Yes, so this is a forum that we can take it as a matter, because all the research ships, if you go, who are all going into the research ships, they know well. We have to wait there, and material movement for the customs as well as for the security, all those things needs to be clear, then only we can go inside. This also because when we are considering the research ships for the futuristic way, this point also need to be noted.
I'll just augment to what sir has asked, sir. We found this a big challenge because there is a lot of time which is lost for boarding. At the same time, we see that the vessel operational time is also a challenge. In the 365 days, there is regular maintenance time, availability of the vessel, multiple scientific programs. So the proposal what we are putting up here is categorize your vessels as regional class, ocean class, and coastal and small. Whatever small activities are there in shallow waters, you have small vessels which need not get into a port. They can enter into a fishing harbor where the access is much more flexible. When you need to go for a deeper waters operations, only such scenarios you go for a specified port entry. The option is already thought that NIOT will have their own jetty.
Sir, due to time constraint, we can have a detailed discussion during our tea break.
Okay, thank you.
Tea break.
Now I request Dr. Basanta Kumar Jana, Deputy Director of NIOT, to present a memento to our distinguished speaker.
Next, I call upon Mr. Srisha S. Bhatt, DGM, Business Development and Marketing, Shipbuilding Business Segment of L&T. He spent his first 10 years of career working in the design department of submarine business located at Mumbai, where he handled detailed design and engineering of Indian strategic platforms. Making a switch of design role to commercial one, he is now responsible for bringing a new business opportunity to shipbuilding business of L&T from both domestic and international market. We welcome you, sir.
Thank you. Honorable session co-chair and chair and all the dignitaries in the audience, very good afternoon to all of you. So I represent L&T Precision Engineering and Systems, which was earlier branded as L&T Defense. So we have been involved in all the major defense projects in the country across marine, land and also aerospace domains. So any naval or land platform that Indian Armed Forces are using today, there are a lot of components in that which have been supplied by L&T. Now coming specifically to the submarine business, so we have been involved with India's strategic submarine program for very long time, for almost 3 decades since the time it began, mainly as a construction partner. But then over time we also acquired a lot of design skills as we saw about how the Naval Design Bureau goes about its business, and we learned from them. And now this is an attempt to develop our own midget submarine or mini submarine, which has been going on for the last 2 or 3 years. And I would like to just throw a light on this development that we have been carrying on. So first is that the first idea is, why do we need this kind of strategic, small size submarine? We'll just look into that. And then how the program went ahead, what were the challenges faced, and what was the way ahead that we are planning. What are the kind of challenges faced during the process, mainly related to the propulsion systems, energy systems, and more importantly, miniaturization of all these systems. All this was a major challenge. What are the gaps we have in the indigenous ecosystem, and then how we can take this forward. This is going to be the presentation outline. So first is that, why do we need a small submarine? We already have a nuclear submarine program which is going on. 2 of those nuclear submarines are already entered the fleet. And then we also have a conventional diesel-electric submarine fleet for a long time. So what is the need for this small submarine? Now if we look at the recent operations like Operation Sindoor and all these kind of recent warfare, what we realize is the nature of warfare has changed. It is no longer a conventional war which used to happen in several decades ago. So we need to have modern technologies, of course unmanned, uncrewed systems, UUVs, these are all the future. But then for this niche area like a small submarine, they sit somewhere between a full-size submarine and an unmanned submarine. It gives the advantage of a certain mission profile where we may have to deploy certain special forces or commandos to a destination for certain secret operations. Now that cannot be done with a full-size submarine, and it obviously cannot be done with an unmanned vessel as well. So that is where this kind of a mission profile comes into picture with this small submarine. And apart from that, it also has some export potential. There are some smaller countries which would like to have this submarine capability, but then a full-size submarine is too expensive for them to operate. So we also have had interest from such smaller countries who are interested in acquiring this smaller submarine with a small crew, and it's not as expensive as a full-size submarine. So that is where this product fits the bill. And then technology sovereignty. This is a long cherished goal. Over the years, we have been building up capability in India to develop the critical defense systems indigenously, but still there is a long way to go, especially with respect to certain propulsion systems, energy storage systems, and weapon systems. In all these areas, to some extent, we are still dependent on foreign OEMs. And that is one gap we would like to address. When we build this kind of a platform and when we design it from scratch, we come to know of all these challenges in more detail. And that helps us to find a way to address those challenges. And then the collaboration between academia, industry, and the Navy. This is again a cherished goal, and there is already a lot of collaboration happening. But then it is not fully cohesive, I would like to say, because the Navy has their own requirements, the industry is constrained by its own financial or other constraints. So it needs to be properly streamlined so that all these three factors can collaborate together. So, and then the ecosystem again is not so fully developed for miniaturized equipment. So that is another gap this project hopes to fill. So just a brief overview of the specifications of this vessel. So its displacement is planned to be less than 550 tons, whereas a full-size submarine, conventional submarine may be around 3,000 to 4,000 tons, and a nuclear submarine is well close to 10,000 tons. So this is a very small submarine, we call it a midget. And it is more suitable for littoral operations, that is close to the coast, and with the limited endurance which is sufficient to carry out these littoral operations. The propulsion is diesel electric, it's a hybrid system. And then a minimal crew, because there is always a space constraint in a submarine, so the idea is to have a small crew and more automation. And the purpose is to have these special forces and ISR activities in the coastal waters and littoral waters. So these are the design goals on the right side, that we would like to first develop an in-house design capability, because submarine design is a very niche field, and while we have achieved some progress in that in the nuclear submarine program, in this miniaturized conventional platforms, there is still some way to go. And of course, the design processes should be built, a knowledge database has to be built so that for the future projects and future generations it is useful. And then across the entire life cycle of the submarine, not just the building of the submarine, but also the operation, maintenance, refit cycles. For all this, we should have sufficient database in place. And finally, to contribute to our goal of Atmanirbhar Bharat, where maximum part of these submarine platforms can be built in India. So this is just a brief general arrangement of the vessel. Going from left to right, we have the propeller and the propulsion system at the aft, and then there is a rescue seat, the air compressors, bilge pumps. Now the SDV, what you can see marked there, that is a special or unique nature of this platform. It's a swimmer delivery vehicle in which special forces can sit, and it can just come to the surface and then they can be deployed. Below that we have the batteries arranged in two groups across the midship and slightly to the forward, and then there are accommodation bunks. In the bridge we have the usual communication mast and radar mast, and at the front we have some torpedo systems and related weapon systems. So this is the kind of design that has been evolved now. We understand the Indian Navy is also looking for to initiate this kind of a program, and so the requirements of that program may result in some minor changes in the arrangement depending on the requirements. So now what are the major challenges we faced here? First is that the crew is going to be a very small crew. That means it requires a high amount of automation. And when we talk say automation, I mean maximum operations have to be carried out autonomously. That also requires the systems to be very reliable. But then again, since the design ecosystem is not so well developed, we may have to slightly reduce that reliability and replace it with redundancy, so that if in case of failure of any system, there is a redundant system which can take over. But that brings a challenge because space on a submarine is very limited. So the more redundant systems we introduce, the more difficult it is to going to fit them into that compact space. So that is where reliability becomes very important. And then hovering control, we'll look at the hovering system in the subsequent slides. The purpose of the hovering system is to maintain that submarine at a fixed depth and without moving too much up or down, so that the special forces can be deployed from it. And then the sensors weapons are going to be very important, and how they integrate with the entire operation of the submarine. That is another crucial aspect. So these were the major challenges encountered during the design phase. Now coming to the technology gap, the lithium-ion battery systems, there is no indigenous OEM who makes lithium-ion batteries for submarines. In the older submarines, we have lead-acid batteries. Now for that we have indigenous manufacturer, but lithium-ion is a newer technology. And while we have electric vehicles and all these are being developed, but submarine requires a very different kind of batteries and battery management systems, more importantly. So for that we don't yet have a domestic supplier We are working with some potential OEMs and trying to develop that technology, but it is still some way ahead. And similarly with the propulsion systems, the diesel generator for this has to be very miniaturized. It has to be submarine grade, which is not available in India yet. And similarly for the drive electronics, this is one more area where there is a gap and we are still dependent on foreign OEMs. Now, again, the same challenge comes with all these critical areas like sonar suite, navigation system, diesel generators, power generation. So in all these areas, since it's a mini submarine, all these systems have to be miniaturized. Now, we have built a nuclear submarine where all these systems are fully indigenous, but then there we have more space available, more power supply available. This is, in here the constraint is space and power. So miniaturized systems are not yet fully developed. We are still import dependent, and there are a lot of issues with trying to fit that whole system within the space of this mini submarine without compromising their functionality and ability. So again, with the mast also, it needs to have minimum radar cross section. So all these areas are where we are to some extent dependent on foreign OEMs, and that is one area which in the near future we hope to address. Now within the indigenous ecosystem, again there are gaps. So as I said earlier, foreign OEMs for a lot of major equipment, and the tier 1, tier 2 ecosystem is not yet fully developed for such a platform. Now coming to academia, there is a limitation on the amount of hydrodynamic testing facilities that are available in India. We have it to some extent, but this kind of a platform requires a lot of detailed tests for which we have to carry out the model tests and related hydrodynamic studies abroad, mostly in Europe. And then again, we don't have much of this underwater acoustics and stealth research happening in India. That's a very niche field. So this again is a foreign dependency. And the control system expertise also is limited to certain very few institutes in the country. Now coming to the standards and the governance part. So there is no standards, no national standard for this kind of submarines. They have to be developed afresh. And there is no regulatory framework for this also, because as of now in the Indian Navy does not have this kind of vessels. So all these operational aspects are yet to be developed. And there is no domestic certification body till now which has worked on mini submarines. So some of the lessons that we learned, the first is that of course start with the ecosystem and not with the platform, because we cannot start production and then realize that there are no equipment suppliers available. So that equipment ecosystem has to be developed. We have to work with the OEMs, develop their capabilities many years before we can even reach a stage of cutting the steel. So this collaboration is going on for the last few years, and hopefully by the time this program that the Navy is planning to reach a certain stage of contracting, all these issues should have been sorted out. And then since I mentioned earlier about the reliability and redundancy, so a lot of simulation is to be done using digital twins and similar or actual physical models to simulate them before they can be deployed on the submarine. Miniaturization is very independent. We cannot take a full-size submarine equipment and try and miniaturize it. It has to be developed ab initio from scratch, from the first principles. So that is another challenge. The control system maturity is again non-negotiable, because the nature of the mission is such that the control systems have to be very robust, very solid. The collaboration between the user, the industry and the academia, this is the way forward, because that's the only way how we can get the required results. And then again, standards, since they don't exist, we have to create the standards. So the hovering control system, this is a very important part of this. So what I mentioned earlier, now the mini submarine has to be deployed at a certain depth in the sea, and so that the commandos or special forces can be sent out of it to carry out their mission. So now during this stage, now if a submarine is moving, we can hold the depth. But since it is supposed to be stationary, it is very difficult to maintain it at a particular depth. So that is where the hovering system comes in. So we cannot use, the submarine has to be steady, it shouldn't have any forward movement. And so we cannot obviously use the propulsion, we cannot use thrusters because they generate noise, and that noise can be detected by the enemy. They will have an underwater signature. So basically the entire propulsion system of the submarine needs to be turned off, but it has to also remain steady without moving up and down, without, it has to maintain its depth. So this is a major challenge, and which the hovering control system seeks to address. And it's operated by this variable ballast system. So it has a ballast system where the water is taken in or given out just to maintain the submarine at a particular depth. And this is achieved using a very simple control system, which I'll cover in the coming slides. So this is the architecture of it. So we have a tank, and we have tank in and sea out, tank out valves. So if the submarine is holding steady and the depth begins to rise, if it starts lowering, the ballast system compensates for it by giving out water, and then it maintains that depth. That is how it works. And this is using an LQR logic, because a PID can only control one axis at a time. But the system needs to factor in various parameters, not just like x-axis or y-axis movement. Multiple parameters has to be monitored at the same time. That is why it has been based on a LQR logic. And it gives a continuous feedback, and then the calibration required is also less. So that is why it was adopted over the conventional PID systems. So the first stage was, the first image is how it was, the concept was developed. So dummy circuit was built to simulate how this actual system is going to be. So here the test was just whether the pump, or the pump which has to actually control the flow of the ballast water, whether it is getting the signal or not. So the test is only whether that LED connected to the pump system is turning on. So once that was achieved, we developed a kind of a physical model where there is a tank and there is a seawater. There are two containers used to simulate that. And then the flow was checked, whether the flow is actually happening or not. And based on the results of that, a full actual physical model was built, and this was tested at our in-house testing facility in L&T Talegaon near Pune, where we have an underwater tank, and this hovering system could be tested. So this is just a brief video of the test. So that platform has been submerged in the water. We can see that it is rising slowly, and it comes up to a particular depth, and then it stops, and then it again goes down. So plus minus 300 mm. So if we define a certain depth that it has to maintain based on the mission requirements, the platform will be maintained within plus minus 300 mm. So that is within the acceptable limit of the operation. So it has now come to the top, and now it is holding, and it will slowly start moving down. So it has held the depth. So now this is important because this is without turning on the motor, without turning on any thruster, just by using ballasting and deballasting of the water, it has been achieved. So now it is going down, and that particular stability is achieved. So now what is the way forward here? First is from the naval side, or from the government side, this regulatory framework has to be defined, because since we don't operate this kind of submarines, so this will be a new experience for all of us. And so it requires a proper framework of regulations to be in place. And then the indigenization, of course, is a cherished goal, and that we all have to work towards. Test facilities, since we don't have them and we are dependent on Europeans for carrying out all these important tests, so developing that also will require a lot of support from the government side, which is the way forward. Now for the industry, so indigenous content, increasing indigenous content is always target. And then that industry also has to come together and work on it, so that we are not always dependent on foreign OEMs for this, and collaborate with the academics and research organizations to improve the R&D. And certain foreign OEMs who may be willing to share a certain technology, we may have to depend on them in the beginning, so that we can develop on it on our own. And for academia, we first need hydrodynamic testing facilities so that the testing can be carried on. And submarine design and submarine engineering is a very niche field. I don't think anybody in India actually learns it as a specific this, because we don't have that kind of a curriculum in the country. It's a very specialized form of naval architecture. So that could be developed. And then energy storage, battery, lithium-ion batteries and the battery management system is something that should be developed. So just to summarize, the ocean does not yield to the unprepared, but it rewards those who build, iterate, and collaborate with purpose. Thank you.
Thank you, sir. Thank you for your innovation, but it needed more work needed. You said Atmanirbhar, but every component needed from other countries. So that part also we have to think.
Yeah.
But that idea is innovative. We hope L&T will succeed in future. Any queries?
One question from my side here.
Yes.
Very nice presentation and.
Yes, sir.
Reasonably extremely well with respect to aerospace. First time I'm hearing your branch.
Right.
And I have a lot of respect for L&T. But today, your presentation more like a crying baby. Really, I'm literally like everything is a problem. I don't see much difference between a big submarine and a small submarine in terms of design principles. Let's say hovering. Hovering is the same problem whether it's big or small. I don't see a difference except that your pump size may increase for a big one, pump size will be small for a small one, and things like that. They are called engineering problems. So engineering problems have to be solved, no doubt about it. But the day I felt that everything is a problem, and as if it makes it too much of a difference between big submarine. See, maybe that you got drawings from somewhere else for big submarines, or you are designing small, I don't know, that is the issue. But otherwise, in principle, see, control system parameters have to be tuned for a given inertia. Basically, here inertia or drag will come into picture. So big means bigger inertia, small means small inertia. So all those problems are engineering problems to be solved by the engineers. But the way you posted this problem, miniaturization of some of the things like thrusters, yes, this is an issue. But if you can design big one, you can design a small one also. So I don't know whether where are the issues, but
I'll explain that, sir. Actually, if we consider a nuclear submarine, so there is a nuclear plant on board. The energy available to it, to the equipment on board is unlimited. And then
see, no one is comparing with the nuclear submarine. In fact, this nuclear submarine in the world are not even 1% of the other submarines. So don't compare with nuclear submarine.
No,
you compare with other submarines. There are, how many countries have nuclear submarines?
But 4 or 5.
But otherwise, other submarines are much more. So you don't have to compare with other submarines. Similarly, you make a big mention about battery management system. What is the problem? Actually, inside the battery is inside the submarine. What is the pressure inside?
Set atmospheric pressure.
Atmospheric. So what is the problem?
No, but
I don't see any difference in battery management system whether it is a car or a ship or a submarine. Because what makes the difference is if it was underwater, let's say we are talking of a robotics. If that goes, then you go under pressure. Here you are not under pressure. So what is the difference? As an engineer, I don't see any difference. Now, question on lithium battery. Lithium battery is not available. I agree with that. But we are making cars. So it's available for car, it's available for submarine also.
But then the safety and these kind of aspects are much more critical because if a battery in a car catches fire, unfortunately, the person will just get out and go. In a submarine, they are doomed. So that level of reliability.
Can you make that statement that battery in a car can catch a fire and you can run away?
No, the requirements are much more stringent.
Millions of cars are, I agree, some accident do take place. You know why accident do take place? Because someone has made a mistake. It's not engineering, it's not design. People do not follow standards, whether it is a wire type or whether it's spacing type. Accidents happen not because of an incapability or wrong design. They happen because of the workmanship.
Yeah,
you must understand
to
that.
a great extent, yes.
So comparing that, you can afford a fire in a car. I cannot accept that statement from an engineer. I can accept from a politician. But an engineer making a statement that I can live with a car where it catches fire.
Not to say that I
don't accept that statement from an engineer. Understand, no?
Yes.
So don't make this statement.
No, that was a simplistic way of putting it, but I'm just trying to say that the standards and the requirements are far more stringent. I know temperature control.
That's correct. But they are not much different from a big submarine.
Yeah, but then we also don't have lithium-ion batteries in big submarines also in the country, sir.
So you say that, it's a common problem.
Yeah.
Lithium-ion battery, see, lithium-ion battery is not available from aircraft. But today you know that people are already making aircraft based on lithium-ion battery. In another 5 years, you will have a RTA. In fact, we have our own design going on in LAL with RTA with lithium-ion battery. We are working on that. And L&T is a much more professional body than actually many of the organizations we have in the country. So I was just thinking.
This is to bring out the challenges that have been faced, sir. It's not to say, complain that everything is a problem. These are things which were faced and we are working towards. Yeah, that we are, it's on track, sir.
Go ahead, sir, with the permission. I'll just tell, sir, there are submarines, big submarines. Japanese have moved to lithium ion.
Yeah. Japanese have moved. They have even
They are
replaced
conventional submarines of 3,000 tons. So
But
my
we have-
question,
we are yet to
my
reach
question
that.
is different. But your aspect regarding safety is true. Lithium-ion batteries are vulnerable to something called thermal runaway. Therefore, the charging, which is management system, has to be much more stringent. And the firefighting, once the fire happens in that constrained space, what
Yeah.
kind of firefighting system will you do? Because you can't, isolate the source of oxygen because it has its own source of oxygen. So the firefighting system has to be designed for a lithium ion, which cannot work for this thing because it has its own source of oxygen. Anyway, my question was about your hovering system that you're designing. You're saying you're not using any pumps.
No, there is a pump to control the ballast and deballasting, sir. But
Yeah.
the propulsion
So
system of the submarine is switched
It's
off.
much more difficult to achieve that because I, being a submariner and I have done these missions, it's much more simpler to use control surfaces at slower speed than using ballast system. Because ballast system has its own rate of flow, rate of pumping out. By the time you start taking control, the inertia takes control.
Yeah.
And also there is a change in buoyancy because you're moving something out. You're moving people out.
Yeah.
You're taking water in.
So that has to
Correct?
be compensated, yeah.
Yes. So it becomes the control surfaces are much more capable of taking those weights at lower speeds. I just want to know where the input came from that you want to have this hovering system rather than a propulsion, because it's a manned submarine finally.
Sorry, it's a?
Manned submarine, correct?
It's a manned submarine.
Yeah.
No. Now the achieving that near stability when there is no forward motion, that is where the challenge was.
And another regarding the stealth, start and stop of a pump is much more compromising stealth than the motion of your
But
control
then
surfaces.
compared to if a
Because
propeller
it creates a more sound,
yeah.
a transient.
But then if a thruster or a propeller starts running, then that will
It
be much
runs
worse.
at some other speed because they are optimized to run at that speed, propeller. Just input.
Yes. So it will have around 10 to 15. No, for the
You fly aircraft with two. Why do I need 10 people to have a submarine?
No, that.
If you're not talking of months, see, maintenance is different. You're not talking of crew with respect to, let's say, serving people. I'm not talking of air hostess here. Crew means I have in aircraft 8-hour flight or even 18-hour flight. 18-hour flight will have normally not more than 3 or 4 pilots. So why do I need 10 people in a submarine for for carrying out? You think it over. You have to. When we can have an aircraft with 2 crew, why you need 10 people for submarine?
No, now if you look at the naval submarines, they have 100 odd crews.
Why?
In fact, sir will be
Naval is a separate issue.
better position to answer that.
That is not for. That is for supporting man itself. I'm not talking supporting man. If you are having submarine only for these operations, you don't need more than 2.
No, but then you have the systems, electrical systems, weapons and sensors, radar, communication, all these need people. We have not yet reached the stage.
Are you
where-
talking of keeping submarine for months in the water?
No, the
Question
mission-
is, what is the endurance? If you are just, you said submarine, you are taking only for a short period, you are going out, taking people coming back. If it's an 8-hour operation, I don't need more than 2. If it's an 8 weeks operation, you may need probably 20. So you have to think of your specifications which you brought. They were all very, very qualitative. You didn't come out with the numbers yourself. So you have to
that because
specify
we didn't
properly.
want to reveal it in a forum, that is also another requirement. So because we also have other shipyards developing it.
Okay,
So the
thank you once again, sir. Thank you so much. We'll invite. Discussion we can have after, during tea time.
And now I request
Thank you.
Sri M. Shankar, Group Director, System Integration, NIOT, to hand over a memento to our distinguished speaker. Now I request Dr. S. Ramesh, Deputy Director, to hand over a memento to the session chair, Dr. Karthik Selvakumar, as a token of our appreciation and gratitude. I request all to join high tea and reassemble at the same venue at 4:15 sharply for the valedictory function. Thank you all.
check, hello, hello, check, hello, check, hello, hello, check, hello. 1, 2, 3. Check 1, 2, 3, 4, 5. Check 1, 2, 3.
Good evening, ladies and gentlemen. We now move on to session 7, Industry Readiness and Operational Expertise. It is going to be a group discussion. This session focuses on industry readiness, operational expertise, and pathways needed to bridge the gap between technology development and real-world deployment. The chair of the session is Dr. K. Sudarshan, NPOL. Sir, may I request you to kindly grace the dais? And the members of the jury will be Lieutenant Commander Balaji, DSRV Pilot Indian Navy, Dr. D. Satyanarayan and NIOT, and the co-chair will be our very own Commander J.P. Singh. I'll hand over the session to Commander J.P. Singh to make us sail forward.
A very good afternoon to all of you. I am Commander J.P. Singh, retired from Navy and joined here as a scientist and presently looking after as a piloting of Matsya 6000. I'll take this opportunity to introduce Chair Dr. K. Sudarshan, Associate Director, retired from Naval Physical and Oceanography Laboratory, Kerala. His core research and technical expertise is underwater system design and testing toward more dunked and seabed structures, surface ship and submarine system for Indian Navy, having an international exposure of advanced training and installation activities in Canada and Russia, and academic and research contributions guided postgraduate students at IIT Madras and IIT Calicut. He has been awarded with NPOL and DRDO Technical Group Award in 2007 and 2009. He has also been contributed towards underwater sensor development. Current contributions include member as a technical committee for Matsya 6000 project and contributing to the Ocean Technology Vision Document and NIOT 12th 5-year plan. Along with the team, we have Lieutenant Commander Balaji TA from Deep Submergence Rescue Vehicle as a pilot, Submarine Rescue Unit, East Indian Navy. He has done a bachelor degree in biomedical engineering from WIT University, an alumnus of Indian Naval Academy. He is having a professional experience of being commissioned in the Indian Navy in Jan 2018, associated with Submarine Rescue Unit since 2023. His operational expertise involved in submarine rescue operation and underwater mission preparedness contributed towards advanced subsea and rescue operations. His major achievement is participating in Indian maiden involvement in exercise Pacific Reach 2025, contributed to successful international submarine rescue operation in South China Sea. Research and technical interest, he has been into deep sea exploration, underwater vehicle and subsea systems, emerging marine and rescue technology. His professional focus towards operational excellence in underwater rescue missions, advancement of deep submergence and subsea technology. Along with team, we have Dr. D. Satyanarayan, Scientist F and a Project Director of Matsya 6000 from National Institute of Ocean Technology. His professional experience includes 25 years of teaching research and deep sea technology development, former lecturer in MIT campus, Anna University. Major contributions, he's been project director for current Matsya 6000 human occupied vehicle, design and development of PROV 500 meters subsea vehicle, ROSEP 6000 with the depth of 6,000 meters as a subsea vehicle. Participation in Antarctica expedition, ephemeral submersible operations at France. Research and technical expertise includes subsea vehicle and ocean technologies, hydraulic pressure vessels and failure analysis, FEA, CFD and smart materials, AI applications in marine system. Research achievements include 64 plus journal and conference publications, 627 citations, H-index 13, I-10 index 1704 patents filed, 2 is being awarded, recipient of National Geoscience and NRDC Societal Innovation Awards. Professional contributions include Indian representative in Integrated Ocean Drilling Program and a member of Ocean Society of India and Institution of Engineers. Now I request Chair Sirs to please take forward this. Thank you, sir.
Very good afternoon. I think we have a good audience because most of the places, in the end of the day, you will see only very few people sitting. But I'm very glad that for a valedictory function, we are all fully staying back. Today, I have been asked to cut short very briefly because most of the people have to leave. So I thought we will make it very brief and we will take out the salient points, what will come out from the topic for the today is given as industrial readiness and operational expertise. First of all, I would like to thank the organizing committee, the director NIOT for giving me this session, because this session was supposed to be taken over by Commodore Srinivas from L&T Defense. Unfortunately, due to some personal exigency, he could not come, and I was asked to take over. From the industry readiness point of view, I would like to share our experience at NPOL, because as you all know, morning we had a lot of NPOL presentation, NSTL presentation. Only the NMRL, the Naval Material Research, could not come for this particular. Otherwise, you would have got an overview of what is DRDO's Naval Labs doing actually. From the NPOL, we have almost 3 decades of experience, especially in the design, development, and production of sonar systems exclusively for the naval requirements. In general, in NPOL, we have the first science and technology projects, then we have the technology development project, then we have the mission mode projects. For the mission mode projects, the naval staff qualitative requirements is directly given once we prove our technology demonstration. So hence, this is the channel in which most of the projects are sanctioned. So, but the NPOL name, which came out in the front line, was after the 71 Indo-Pakistan war, where our system failed and our eminent professor, Captain Paul Raj at Stanford, who is there, was the pioneer who did this APSO sonar for Indian Navy. The advanced panoramic sonar hull mounted, we used to very frequently say it is Captain A. Paul Raj sonar. That's how the project name was called APSO. And subsequently, for all surface ships, the hull mounted sonar, which came into the different versions, like upgradation and the new generation sonar is now in all shallow water crafts, which are coming out now very recently. And subsequently, we also had a lot of towed systems, right from the project HUMVAD, hull-mounted variable depth sonar. Wherever you have the limitation on the surface ship sonar, we moved into the hull-mounted and variable depth systems. Of late, surface ship sonar, we had the Marich project, where NSTL and NPOL did a marvelous job in advanced torpedo decoy system, which has been accepted by Navy. And most of these places, either surface ship or the submarine sonars or the dunking sonar, which most of the people who have shown in the underwater domain projection in the morning, where the day one when we have proved the technology, we induct our industry as a co-partner right from the day one. So we need not wait for the last day to transfer our technology to the industry. And that was our success story came out. Within very few years, we could develop all the sonar, and under the qualification rigorous testing by CQA and other people, we partnered our industry right from the day one, and we could succeed in developing the sonar systems for our naval application. If you see this journey of what is called the industry, the public sector unit, Bharat Electronics was the major contributor. And of late, for the transducer technology, we trained our Keltron people to take the technology along. We gave all the infrastructure and facilities available in-house and asked them to be a part of our organization. They recruit the people and send it to us, and we transfer the technology from the day one, how we assemble the hydrophones, how we assemble the transducers. And this lesson was taught to all these people, and that's how we could fast production come through these public sector units and private sector industries. And small vendors were groomed, especially in the encapsulation of the acoustic transducers and other areas. All these people came along with us. And transfer of technology was not at all an issue, because the day one itself, they were partner along with us. So with this, we have also finally come to the stage of exporting our sonar system to the friendly nations. So the core competency where we had was in the engineering, materials, and thermal management, signal processing, and display. What you saw in the morning, a big slide where NPOL man presented the whole thing. And of course, we had the major defense partner, L&T, especially in the case of the mechanical system, especially the winch and handling system for deployment and retrieval, and also for many other systems, including our ATV projects. So with these few words, I'd like to introduce this point, industry readiness. In the case of underwater technology, we are making into three different areas. One is the scientific research, one is the commercial application, and another is the strategic and defense requirements. The technology readiness level in all the three is totally different. If you look at the scientific research, it may be in the area of TRL 1 to 4, and if it is in the area of commercial, it may be in the 4 to 6. What I'm talking with respect to our Indian scenario. And also we have now come to the stage of TRL 4 to 7, where I can see many of the industries which have gathered here have developed one way or other some of these underwater robotic systems, which I'm very happy to note that actually. So with this expanding blue economy and the defense requirements is driving our production from foreign dependency, and I hope this will take us with key challenges which will be listed shortly. With this academics and R&D institutions and startups, I think we should be in a position to go indigenized development shortly in the next 5 years for our various systems. With these few words, I will hand over to my colleague, Mr. Satyanarayanan, to talk on the industrial, because he was the man who was interacting in the Matsya for many of the industry available in our country. Over to Satya.
Thank you, sir. And good afternoon, everyone, and distinguished guests here gathered here, and all the participants, students, and ladies and gentlemen. Actually, sir has thrown several points, And if you see the current scenario, in Indian scenario, if you take for example, we are seeing an aggressive growth in the market. Actually, there is a aggressive expansion happening, and even it is touching the 100 million US dollars. And slightly the market is shifting and it is transitioning from pure government funding to institutional capital, and highlighted by the recent $1 million seed rounds that is happening in the Vikra Ocean Tech. And the venture capital, towards that we are moving, and we are going to get a lot of capital investments for this underwater robotics very soon. And we are also attaining the commercialization maturity. So we can clearly see that from academic R&D prototyping, we are moving towards sustainable revenue generating commercial operations globally and as well as in Indian scenario. And what are the strategic and defense drivers? If you see already, Sudarshan sir is listed out. They are actually from defense. The defense drivers are huge, and they are putting in lot of efforts and driving this commercial development globally as well as in India. And the blue economic alignment is also giving us a good driver factor. And there is enough amount of critical infrastructure protection activities happening, like the rising civil demand in indigenization of ROVs to inspect the aging dams, ports, and subsea telecom cables. So they rely on expensive foreign equipments in the previous years. But now indigenized ROVs and indigenized Indian ROVs are doing these jobs. And there is a considerable amount of technological innovations and capabilities are being developed. And if you see nowadays this man-portable AUVs, they play a major role. And they keep, almost 45% of market share now. And we are also seeing lot of deep sea milestones happening, about 2,000 meters operations, lot of activities being carried out. And the software-driven capabilities are also happening. So wherever we go now, the buzzword is AI, generative AI, and so many things. So these software-driven capabilities are also helping us and to improve this market and this industrial readiness. But however, we have certain bottlenecks, and there are ecosystem challenges also. So we have discussed in past 2 days the critical component dependencies, the INS-DVLs, sonars, and specialized thrusters. Even now we depend on global market. So that's one point we have to take care. And there are infrastructure and testing deficits also. We have very, very limited testing infrastructures, the towing tanks, the hyperbaric testing facilities. So these facilities are very, very limited in India. And we are dealing with the extreme environment. If you see, particularly in India, we have very muddy waters. So these muddy waters is a huge challenge for ROVs and underwater robotics. And the tropical marine environment, because the global market designs their systems based on their own local environment. But if you come to India, the tropical waters, they pose a huge different challenges for us. So these challenges have to be overcome, and we have already discussed internally. Because of paucity of time, I will just put out some recommendations for the future way forward. So we have considerable amount of startups trying to come inside this industry. So we have to provide a targeted, subsidized precision engineering manufacturing facilities. So you have to target the precision engineering and the industries which are willing to come into this underwater robotics, give them some subsidies. And you have to create some micro clusters. So Chennai, Visakhapatnam, wherever you see the marine industry, if you can create some marine clusters and micro clusters, that can be a very good working methodology. And whatever this open source available, this hardware framework has to be done. So we have to combine these hardware frameworks and bring it into one umbrella. And the fast tracking of various validation infrastructure, sharing our knowledge and as well as our infrastructure. So we have to fast track. See, we are sharing, but the sharing does not happen very quickly. So we have to fast track these sharing of facilities and streamlining of our defense certifications and regulations. And these are some kind of recommendations after this group discussion and after this workshop we'll be able to put in. I hand over the mic to my colleague. Sir, you can do that? Yes.
Dr. Satya, you have brought very valid points, especially. We will bring it out in the final summary. In fact, when we saw some of these industries, I think the facilities, whatever available in DRDO or in the other agencies, it is open to all. There is no doubt about it. We should exploit maximum all these facilities available, like our seakeeping tank, towing tank, and the lake facility, especially the NPOL has got an underwater acoustic research station at a place called Idiki, where you can have a depth of 70 to 100 meters, and you have all the facilities. We have a platform, and I think right from the day one when CMERA has brought their AUV, it was tested there, and subsequently L&T also has done their test. So the maximum infrastructure as on today, with respect to whatever our limitation, we have the facilities available. That should be, I hope we should bring out a yellow directory of all the national test facilities available at one go in one place. And similarly, the tools available for this underwater robotic exploration in the case of scientific or in the defense area. Like NIOT has got an ROV, Polar ROV, then we have the latest AUV which is coming up. All these tools, once you use, after that only with the necessity comes, you are taking this out. I have a feeling this should be maintained and this should be available, especially when you had a major crash of Bay of Bengal, the search. Immediately there is a call coming from Delhi, who has got the side scan sonar, who is having ROV. I mean, people were not aware who has exactly. Yes. All this should be at one place, like an yellow directory in the telephone. I should be able to call them and take those equipment for our survey or for any other application in the case of some emergency issues. So this is how I think we should bring out these salient points in our recommendation.
Yes, sir. Actually, we were discussing about that yellow pages, and
exactly,
we also came out a proposal that we should have a journal or quarterly newsletter. So whichever industry is coming up or whichever new information is coming up, if we are able to capture those new developments in that yellow directory or in the newsletter, that will be a good proposal.
Yesterday when I was scanning through the net, there is something called Indian Underwater Robotics Society. Are you aware? I was not aware. In fact, like our Ocean Society of India, there is an Underwater Robotics Society. I don't know whether anybody is member from here. Or okay, because I think we should strengthen that society because this is the right time where we should pull all the people and make a registration so that at least we can exchange ideas, we can bring out certain, as he says, some journal over a period of 6 months or 3 months, and that will give us more information because this Ocean Society of India was started at NPOL in the year somewhere 2003 or 4, if I remember, and now everybody is life member and we have a different type. Every 3 years or 2 years we meet at the various laboratories like NIOT, NIO and other places. So similarly, my recommendation is also we should be a member of the Underwater Robotics Society. Only when I scanned through I came to know, otherwise I was not aware such a Underwater Robotics Society is available. This was a good information. So with this I will request our Lieutenant Commander Balaji to give his experience. Basically he is the man who is in the submarine rescue unit as a pilot. He will share what is essential for us and what training we should have exactly. Over to Balaji.
Thank you, sir. Good afternoon, everyone. Firstly, I'd like to thank all the presenters since yesterday for giving me so much food for thought, and Dr. Pawan from IMU in his lecture for setting the context for the points I'll be bringing forward. Like rightly put by Commodore Dalbir, PDSMO, that as the end user and operator, I have problems, and for the solutions, we need help of the audience who are gathered here. So when we discuss about underwater industry and operational readiness, I think we sometimes focus heavily on the platform and asset, the autonomy and the sensors, but underwater operations is much larger than just the platform and the asset. The ocean is one of the very few environments where operational infrastructure is much more larger and more expensive than the asset itself. We know that AUVs, ROVs, unmanned systems, underwater robots have certainly advanced in the past decade. But operationally, the real challenge is not just building these systems once. It is sustaining repeatable operations in a highly dynamic environment. It is the sustained repeatability of the operations that is the true mark of success in the underwater industry. The sea conditions change constantly. Communication is limited. The underwater is a by default communication denied environment. Weather windows are short. You can't operate all throughout the year. We have particular windows in the year where we can operate these systems. Maintenance cycles are very demanding. Even operational availability throughout the year becomes a challenge. And unlike many other industries, underwater capability depends heavily on the operational ecosystem. Support vessels, like rightly put during the IMU lecture, launch and recovery infrastructure, a pool of trained operators and maintenance expertise, and testing environments and long-term sea validation. One thing that struck early on in my career during sea operations is how deceptively the ocean works. From outside, it obviously looks vast and open, but once you start operating in that environment, you can realize how quickly conditions at sea can change and how unforgiving the sea can be to unreliable engineering. The engineering needs to be robust and reliable for you to repeatedly exploit it. Which is why I feel industrial readiness and operational expertise have to evolve together. Because technological capability alone does not automatically translate into operational maturity. One aspect that often gets overlooked in these discussions on underwater capability is the dependence on established global classification and certification ecosystems, which was already brought out yesterday, and I would like to reiterate and focus that today much of the operational trust in subsea systems, especially for deep sea and human occupancy vessels, is linked to standards and validation frameworks and processes that have evolved over decades by a handful global established organizations, mostly in the West. So as India expands its underwater research and operational ambitions, I think an important goal should also be in developing stronger indigenized capability in subsea design validation, testing frameworks, and operational certification ecosystem. That does not mean working in isolation. In fact, collaboration with experienced international players will remain extremely important. But over time, operational maturity also requires confidence in our own validation, engineering, and sustained frameworks. So even today, while we have achieved sustained manned underwater operations in the defense sector through submarines and saturation diving systems, taking humans safely and repeatedly, that's what I'd like to impress on, repeatedly into the deep ocean still remains technologically and operationally challenging. I think India is currently at an important inflection point coming to that. Unlike aerospace or telecommunications industry, the long-term economic and strategic potential of the subsea domain is still not fully appreciated publicly. But I believe India is gradually building the ecosystem required through scientific programs, underwater robotics, shipbuilding capability, startups, and operational experience. The challenge now is integrating these capabilities into a sustained operational ecosystem. Having said that, I'd like to bring to the notice of this audience that when I say about the ecosystem, since it's a life-saving capability that I work for, the submarine rescue unit, for submarine rescue where we operate similar subsea systems, there exists established ecosystem. For example, ISMERLO exists where we have an entire database of all the kinds of ships, depending on their grading of how well we can exploit them to use our subsea systems. But when it comes to subsea exploration, scientific expeditions, we don't have a universally accepted database or framework to go about it. So I think going forward, this is what something we'll have to establish, because we can make as many prototypes as we want, but to be able to repeatedly put it at sea and validate them is the real challenge. Having said that, I'll return it back to the chair.
Thank you, Lieutenant Commander Balaji. You have shared very valuable points, especially from the operator's point of view. And to my left, I have one more co-chair who is also an expert in the submarine rescue unit. He has dived in the French submersible very recently, and I would like to share his, I request Commander J.P. Singh to share a few words about the operational expertise.
Thank you, sir. I very much agree with Lieutenant Commander Balaji, whatever the point he has been brought. For my expertise, I just want to tell I was the first commissioning pilot for that deep submergence rescue vehicle in SRU East. And during my operations, I've done many meetings with the submarine where we have actually transferred the people live from the submarine to the surface. So every day is a learning day, which I have been over the years have built as an experience. You have to stick to your standard operating procedures and you have to keep validating it. Once you set the SOPs, doesn't mean that it is forever. Next time you will learn something. Next time you will learn. So you have to keep updating your standard operating procedure and very much stick to your emergency operating procedures. So these are the two Bibles for any underwater operations. Apart from it, like we have go, no-go conditions. At no time user will take any risk, and there is a very thin line between confidence and overconfidence. So this is over a period I have built that expertise, and now we have done a successful trials of our Matsya at L&T Kattupalli Harbour. We have built a good confidence on our life support systems. Our vehicle floated, we have done some maneuvering trials, and we are looking forward with the same confidence to do our 500-meter trials as well. Although me and my colleague, we have dived to the deepest from the India, 5,000 and 4,000, and we have got that confidence that we are very much capable of going to 6,000 meter, but we are going in stages. So to broaden the confidence of the operations, we are building the Matsya indigenously. So all the equipments we are validating, all the things which have been engineered is being captured by the operator, and based on that we are developing our operational manuals, which will also be having a technical literature and having a maintenance manual. So these 4 or 5 documents are the baseline for any operations of underwater, which I've learned from my experience. And believe me, I have stuck to these things, and till now I have not seen any accidents. And touch wood, I was absolutely having a successful dive. Indian Navy reps are here with whom I've used to dive and accumulated some 3,000 dive hours and done some 50 target mates and deepest dive to 670 meter and again deepest dive in Matsya to 5,000. So I'm always proud to bring this thing, our expertise, and I'm very much proud that I'm a part of NIOT, and being as a pilot of Matsya in a very few months you will hear the news that we have touched 6,000 meter. With that, I'll conclude and over to Speaker, sir.
Thank you, Commander Singh. It is a very confidence booster for Matsya 6000. Definitely, we will be going ahead with our positive approach, because that itself boosts our energy to go ahead in the project at the earliest and finish it, because the operation is very, very important. So just due to paucity of time, I am throwing to the audience basically only one question, because we have to have the other valedictory function, which will have a valid point for our recommendation. Please. Jena, please.
Thank you very much for today's discussion. The industry and R&D or development, we have to have a more in the specific, what are the industry we have to target, the timeline where we are missing, because R&D will take a long time, where industry may not be ready to take up our product what we developed. So we have to now choose what are the industry you have to target and what development we are doing, like underwater robotics we are doing today. So we have to, just as a timeline you have to fix, then accordingly what are the industry, where so several component is there. India, we know we don't have much things. So we have to now, from the beginning itself, we could have tried, then we can able to achieve something. Thank you.
Thank you, Jena. I think I'll try to conclude this session with a session summary. Valid points have been brought out by Satyanarayan and our Commander Balaji and Singh. If you look at critically in our industrial side, the technology readiness level, in fact, I saw on the international level also, we have the global TRL where ROV has got the technology readiness for 9, in fact, which is for the defense and offshore and other cable maintenance area. AUV has got around 7 and 8, especially for deep sea mapping and scientific research. The resident AUV and subsea is around 6 to 7, that is homing and autonomous docking systems, which are in the. So if you look in an overview, we have a lot of challenges to be addressed, which I think a lot of people have brought out in their presentation. If you see in a nutshell, India is now moving from a low volume, lab scale prototyping to dedicated commercial grade mass assembly facilities. And the national strategy for robotics and defense indigenization policies and deep tech startups are building out physical manufacturing units, and some of the dedication production facilities like our Sagar Defense Engineering and Planistech and IORI are coming up. So if you look at all this, finally, what my feeling we should recommend is there must be a shift from the government funding to venture capitalist. Otherwise, the government funding for these areas will be very minimal, which like our mutual fund and other, we should be able to explore, especially for these small units where they are investing in the lot. From the strategic point of view, there is a lot of demand for checking the cable, coastal surveillance and other areas. Testing and infrastructure deficit, I am sure, like NIOT is building the future 1,500 bar test facility, which is very, very essential so that we need not depend upon KSRI or anybody else. And also, these small startups, we should have something like IDEX. And also, we should have incentives for these subsea manufacturing people, like tax holiday, like our DG Naval System, Dr. Srinivas brought out yesterday. And establishing certain micro clusters for marine application. And also the regulatory body, especially when I saw the training, what we need from the operators, we should have a regulatory body for deployment of these underwater robotics and testing in-house, and also bring out the trained operators, that is whether ROV or AUV, we need, because when you deployment only, you know the condition, what are the risks involved, and other. So everywhere this regulatory authority is needed, which yesterday also I think in our group discussion, our DG brought out, you need something, IRS can also venture into this. Like DNV now we are paying through our nose and getting certified. I think with this experience in the future, we should be able to have our own certification agency in India. Like IRS can take for other, since they are doing for surface ship, for robotics also they should be building the, it is all based on our internal experience and expertise. So, and also a directory by which, where we have who has what tool for such and such application should be available. And also, once in 6 months or in a year, this Indian Robotics Society, if you can meet at different places like Ocean Society of India, I think that will give a very positive approach. And we will be developing in the next 5 years, the underwater robotics, we may reach out at least 3rd or 4th country in the world to come to this issue once our Matsya succeeds. Thank you for all this. Thank you.
Now I request Director, National Institute of Ocean Technology, Professor Balaji Ramakrishnan, to please facilitate the speakers.
So nice to meet you, sir. In fact, coincidentally, we were discussing some of the points that you precisely said. Thank you so much. Thank you. I think even the workshop also we are going to have some systems of that must be something like a momentum and continuity. Yes. Correct. Thank you. Balaji to Balaji. Thank you, sir.
We shall now, thank you very much for gathering here. Now we are at a stage that we'll go to conclude the event. We shall now move on to valedictory function. I invite my co-host to kindly guide us through this.
Kishore, name board.
Ladies and gentlemen, after 2 days of insightful deliberations, engaging technical discussions, innovative demonstrations, and meaningful interactions, we have now arrived to the concluding session of Underwater Robotic Workshop UWR 2026. We shall now commence the valedictory section of UWR 2026.
May I respectfully invite our distinguished dignitaries to kindly grace the dais. Padma Shri Dr. P.S. Goyal, former Secretary, Ministry of Earth Sciences. Rear Admiral T.V.N. Prasanna, Joint Secretary, NSCS. And our very own Professor Balaji Ramakrishnan, Director, NIOT. Sir, kindly grace the dais. Thank you very much, sir. May I request Professor Balaji Ramakrishnan, our director, to kindly welcome the dignitaries with a bouquet.
Thank you, sir. We are privileged to have with us Padma Shri Dr. P.S. Goyal, a distinguished scientist, institution builder, and visionary leader, whose contributions to India's space and ocean science program have inspired generation of scientists, engineers, and technology leaders. I request Padma Shri Dr. P.S. Goyal to kindly lead the valedictory proceedings and invite the session chairs to present the key recommendations emerging from their respective sessions. Sir, please.
Good afternoon to all of you. First, of course, let me apologize that I was not able to come yesterday, but today I've been whole day. I must compliment NIOT and particular Director Professor Balaji for organizing this workshop. What is interesting to me is that we are integrating, starting from the user, the so-called, all the, you can say, the people who are involved in that, stakeholders, right from users, R&D, academy, as well as industry. So this is probably first time that we are able to put all the stakeholders together. So that's a great achievement by itself for a cause like underwater robotics. Other important aspect is that we should not see underwater robotics in an isolated manner. We have to see in a larger context of the country, which I perceive two. Number one is the so-called blue economy. And we all know that the economy from the ocean is going to make a much, much larger component in the future, not only this country, but also whole world. And if you are not able to make use of that, if you are not able to exploit the resources from the ocean, then we are going to be loser. Or whosoever doesn't do that will be loser. So we have to be, when we are talking of a Viksit Bharat 2047, we have to be part of it as an ocean community. So we have to develop a robotic capability, underwater capability for that. Second thing is the national security. When we are talking of let's say, national security, earlier there used to be a dominant factor on earth. Then, of course, later it moved to the air. Now, if you really see, it's moving towards ocean. It is not just Iran and USA issue which is going on today. But if we have to really see what people are doing, international forces, everyone wants to have a control over the sea routes. They want to have a capability of choking a sea route for other countries so that it will affect the economy. See, one thing has emerged very clearly, that in future, the biggest weapon will not be atom bomb. The biggest weapon will be our ability to disrupt the economy of our country. And on that, the control over sea routes will be playing a role. And in that context, we have to see the capability. So today we are talking of underwater robotics, but we have to take a larger aspect of the overall capability under the sea, which of course there was a presentation from Navy. Then we are looking for the situation awareness, what is happening. We want to have a complete visibility to what's happening in our neighborhood. So all that makes part of that. And to my mind, the underwater robotics is an important component of that. So we have to link the underwater robotics for these two. So this is the overall context I see the underwater robotics, this workshop. Now the question is, having had this 2 days workshop, what is that we have understood? What is that we have achieved? And what is that we have not achieved yet to achieve? From the discipline I come, I don't look at success at all. If we have been very successful, that's okay. That's part of the game. What is important is where we have not been successful or what we need to do in future. So I want to see that part, or maybe in this session. See, purpose of validatory session, which I discussed with all the organizers and Balaji, was that we will try to capture what we need to do as a country in future, in immediate future. And of course, some of these things were described by previous session also, which is a good session because you came up with some good recommendations. So we'll try to capture all of that together in this session. And it's not complete by itself. What we'll do is we'll request the organizers to prepare a paper based on whatever we discussed today, and then come up with a recommendation. But one important point, recommendations have to be actionable. I mean, making that, okay, we should do everything and all that may not be possible. So we have to keep the realities of mind. I mean, the recommendation someone made was the government should fund all that. We know that government is not going to fund. They are not, the government cannot fund blindly to all industries, everything what they want. There has to be, there is a mechanism in this country existing. The finance in this country is one of the most toughest system. To beat that finance, everyone struggles, whether DRDO, whether it's space, or whether Ministry for Science, or even armed forces. So we have to understand the limitations of the system and then make a recommendation which can be done. So what we'll do is, first we will listen to each session. What they feel, because session chair, when you are chairing a session, you are not just, you are listening everything much more carefully than probably we sitting in the other benches listen. So what you have captured from this session, what you like as an actionable action, which can be implemented by the system. You can also bring out the agencies to do that. And later, I'd like to add some more points to that. I'll just give you an example. When I look at some of the technologies that have not happened, I was just incidentally discussing with Balaji, Dr. Balaji sitting here. We have not produced an aircraft engine successfully, you know how many years? GTRE is existing from 1960s. I don't remember which year it came. My first interaction with GTRE, people in DRE will know that, was first time in 1973. I went there to weld some pipes for my satellite work. I was young engineer, scientist C, and I was not allowed to do that because the director at that time said, oh, you want to take my facility? I am so busy, my engine is waiting and I cannot allow you to do that. 1973, that engine has not come out even today in 2026. So how many years? You can count. So point is, why? We do not have an engine test facility. You are developing an engine, 60, 70 years you have developed that, but you have not created an engine test facility. So we have to understand these limitations in advance. I mean, imagine if we have developed a rocket like GSLV and all that. I remember when we started developing PSLV, our test facility for PSLV actually started earlier than the development of the rocket motor itself. Because unless the rocket motor test facility is available, unless I can test it, there's no use. So I'm just giving one linkage. So there can be many linkages like that. If I am going to develop a capability to go to 6,000 meters, I must have facilities to test that. No, once in a while we can go to Russia, but that cannot be norm. So like that, my request to all of you will be, when you are making a presentation, particularly the session chair, please see what is lacking. And if you have a suggestion to make a mechanism, also you do that. If you feel, okay, who should take a lead? Whether NIUT should take a lead, whether NSTL should take a lead, whether NPL should take a lead, or maybe some wing of armed forces. So you can come up with your own suggestions. We will try to see, we'll try to interact with the various stakeholders there to see who should do that. But come up with recommendations. So I'll try to first collect that, and then maybe we'll try to summarize towards the end. Would you like to make any other comment? So I think we'll go in a sequence. The first session we have, this is Dr. Sarang from BITS Pilani. He's there? Yeah, Dr. Please come. Just bullet points.
Very good evening, everyone. The dignitaries sitting on the dais and this august gathering. It's a privilege to have been a session chair for the first session in this particular workshop, and I'm obliged to give a. Hello. I would be obliged to give a brief summary and a recommendation as was pointed out in that particular session, as well as is pointed out by our guest, the specific suggestions from my side also. So this session was on the subsea vehicle technologies. The first speaker, Dr. S. Nandi, talked about the unmanned underwater vehicles. He briefed about the development cycle of unmanned underwater vehicles, discussed about the global market trends and drivers for these technology challenges and the enablers. He did mention about the capabilities and gap analysis across the various areas of UUVs. He did talk about the AUV 150 and AUV 500, which CMERA is developing in. The detailed discussion was on the homing and the docking system as well. And Dr. Nandi pointed out the need for indigenization of the individual items which are part of this particular vehicles. The next speaker was Dr. Vedachalam. He talked about the human-occupied vehicles, manned and unmanned vehicle ecosystem, and its adaptation in the national capabilities was discussed. He walked us through the Matsya system and subsystem, challenges of manned system. He talked about the criticality, the life critical and the mission critical system differences were mentioned to the audience. The different aspects of a rescue system were discussed, and how do we move from the mission preparedness to the mission execution was also pointed out there. the basic recommendation there was the utilization of this for entire biological, geological, and the scientific capabilities and how it can be efficiently tapped. Our next presentation in the session was from Captain Vikas Gautam from the Indian Navy. He talked about the launching retrieval of the submarine system. He discussed about all the 16 subsystems of the vehicle, including ROV, SSV, HPU, and LSRV. He discussed about the operations, responsibilities, and tasks of OIC and all crew who is involved in this process, criteria of operations, when to have the decisions like go, no-go situations. The inclusion of Matsya into this particular platform was the most interesting aspect for us to understand. And he did mention very specifically that this real-life experiences of Navy should be included or discussed with all the scientific capabilities in India to enhance our national level understanding and ecosystem. So we relate with those particular recommendations here. On a specific basis, sir, I wanted to also mention the need for the standardization certification as we are talking about. I am here also as a part of the panel 7 of Bureau of Indian Standards, who is a SC41 panel committee. And all this organization, NIO, NPOL, NIOT are also part of that panel 7. And we are looking for the standardization of underwater sensor nodes, including static as well as mobile entities. Though as a vehicles, we understand it comes as a standardization in a different body, but as a part of the sensor network, it can fall under the ISO, under the underwater acoustic sensor networks. So I'm doing that study, and in next month, I'm supposed to give that proposal to Government of India. And hopefully, the cycle is 2-year cycle for standardization. We will be able to achieve that. But whenever these standards come, it doesn't come from the proof of concept. It has to have the testing facilities and our own experiences associated with that. Then only we would be successful in putting the standard, because it has to be globally adaptable. Of course, we can have our own Indian standard for Indian scenario, but it would be much more meaningful if it can be globally accepted. So that's one input we are trying to look at. Thank you. Thanks again.
Thank you very much, Dr. Saran. Very, very nice exposition. Now we'll request Dr. Rohit.
Yes.
Hi.
Good evening, sir. I was chaired for subsea vehicle demands. The speakers were Commandant Deepkiran Singh from Coastal Surveillance. He gave practical insights on the India's coastal surveillance architecture, and he briefed about the operational requirements. Next speaker, Dr. Pramod Kumar Maurya from CSR NIO Goa. His topic was ocean research and resource exploration. He gave an overview on deep sea exploration and resource mapping, especially on GNS denied navigation solution and its priorities for indigenous marine robotics. Third is Dr. Jensen V. George, NCPOR Goa. He gave a brief explanation on the polar exploration, and his insights were on India's polar programs requirements for ice-capable subsea platforms, under ice navigation, and how polar data informs climatic model and forecasting. The next was Dr. R.S. Mahesh Kumar from CMLRA on the topic ocean biodiversity. He gave a brief outline on the approaches for autonomous biodiversity monitoring, multi-sensor survey design, AI-assisted species detection, and priorities for scalable ecological surveys. And the last was Mrs. Aparajita Sharma, Ecological Survey of India, ASI. She gave insights on underwater heritage. Especially, she mentioned on how robotic platforms and imaging workflows support discovery, documentation, and preservation of submerged cultural heritage and best practices for low-impact archaeological surveys. Based on the understanding, there are few demand categories which they highlighted in terms of mission: persistent coastal surveillance, deep sea exploration, under ice monitoring, biodiversity surveys, and non-invasive heritage surveys. In terms of performance demands, considering the depth rating, endurance, high payload capacity, and high resolution sensors. In terms of navigation demands, GNS denied navigation, acoustic modem, large surface layer buoys, and low bandwidth but reliable data links in terms of autonomy and AI demand, onboard decision making, adaptive sampling, anomaly detection, AI-assisted seabed imaging, and automated routed planning. In terms of integration demand, fits into the coastal security systems, interoperability with ships, common data formats, and open interfaces. In terms of indigenous demand, requirement for indigenous design of platforms, sensors, communication, software, supply chain. Based on this, the key observations were maritime security needs to be persistent underwater surveillance. Ocean exploration requires deep-rated, long-endurance robotic system with modular payloads. Polar research needs more AI-based capable platforms. Biodiversity assessment benefits from continuous and autonomous monitoring and AI-enabled analytics. Heritage preservation relies on high-resolution, non-invasive survey technologies and how technological transformation of AUV, ROV can use for heritage. On the whole, I would like to summarize that development of an indigenous subsea vehicle and sensor ecosystem, prioritizing modularity and open interfaces, invest on AI-enabled underwater data analytics and automated interpretation tools, establish national underwater technology facilities, and prepare a national roadmap for underwater autonomous systems, including standards, certifications, and workforce development. Thank you, sir. Yes, sir.
And I cannot make out anything specific about it. It's all just a wish list. I would look for something specific that you would like to say, okay, this is what we must do immediately. Otherwise, this remain valid 10 years back also, 10 years later also. Your wish list, isn't it?
No, sir, this was the consolidated statements.
I understand.
Yes,
I'm looking for, I'm looking from your side, whether you'd like to come up with something like we need to do immediately, we need to organize ourselves as a country, or we need to set up some new mechanism. Otherwise,
yes, sir.
Okay.
Shall I give the recommendations, sir?
I'm not able to get what we can tell, let's say, decision makers. Let's say either to Secretary Minister or saying, you should do this. I'm not able to do that. These are looks that part. So specifically, if you have some, no hurry right now, we'll request you, maybe a few days later and all that, mail to our organizers, we'll look for something very specific.
Sure, sir.
The co-chair, maybe you can send us.
Sure, sir. Thank you, sir.
Thank you very much.
Thank you, sir.
Okay, we'll go to session 3. Dr. Virkeshwar Rao. Virkeshwar Kumar, sir. Virkeshwar Kumar, IIT Kanpur. Is there?
Good afternoon, everyone. First, I would like to sincerely thank the organizer and NIOT Chennai for the organizing the excellent event. My session featured 4 interesting talks covering different aspects of autonomous underwater vehicle AUVs. The first presentation was given by Mr. Rajeshwar Reddy from L&T Defense, and he had talked about the challenges and achievement in AUV technologies in industry. He highlighted that highlighted the progress made in indigenous AUV development, emphasizing the nearly 85% of system components are indigenous, reflecting the India's growing self-reliance in underwater technologies. Even that we should more emphasize about the collaboration between industry and academia. So second talk was presented by Dr. Siju John from the NCTL. He discusses the evolution of AUV and the current status of AUV in India, and he has highlighted the development of high endurance AUVs with indigenous sonar systems. CFD simulation, towing tank experiments, and wind tunnel testing were used to optimize the vehicle's hydrodynamic performance and drag coefficient and stability analysis. In the third talk, Dr. Abhilash Sharma from IIT Madras have talked about GNC systems, the works integrated simulation experiment, deep Q learning, digital twin technology along with the multiple sensors. He have demonstrated the extreme conditions, AUV testings, like 250 kilometer per hour, air speed, wind speed. In the final talk by Dr. Raju from the NPOL, he have discussed about the development of advanced underwater sonar systems and the application of novel materials to enhance sonar performance. Overall presentation look very nice, but my recommendation is how to improve our manufacturing. We develop something in R&D labs, but they know direct facility to develop in industry. So that thing we have to emphasize, because indigenization is saying 85%, and data is there in Lenti is claiming that. Do we have industry to produce in mass production? Yes.
No, you know very well how industry works.
Yes.
Industry does not work for R&D.
Yes.
Industry works for money, right? So when you say collaboration, we have to create a model where the industry does R&D or participates, but they have to look for ultimately the return.
Yes.
So what is that you are specifically recommending? I'll give an example.
Yes.
IIT Chennai has created IIT Park. Okay. People come there, they get support from the academy, but they do their own R&D. But then there is their own expenses. Will that model work for robotics or ocean technology today? One has to examine that. Okay.
Yes.
See, the other model, let us say, I'll just give example, ARCI Hyderabad.
Yes.
They have the expertise in powder metallurgy.
Yes.
What they did was, they said, you come here, we'll give you space,
Yes.
you work with us, develop a product, give us very notional money, and then market your product afterwards and develop your capability.
Yes.
Whether such a model can NIOT create, of course I know that the director is already doing that, can create such segment, okay, we create 10 rooms, industry comes there, you develop product, we'll give you the technical know-how, also help you, hold your hands, and then you go and market your product.
Yes.
Whether such a model should be done by not only NIOT, but NSTL, NPOL, who are the laboratories working in this area. So what is your specific recommendation?
Yeah, so my recommendation is like concept of IIT has research park concept, the industry, they invite the industrial partner.
There's lot of investment. You know how IIT Industrial Park is making a lot of money. You are aware of that?
Yes.
So whether that much, because there you're looking for immediate returns.
Yes.
Do you have that kind of returns in this kind of, in this activity?
Not in this, not that way concept, but NIOT can develop, invite private partners to sell their product, something like that.
Thank you very much.
Okay, thank you.
Okay, we will now go to the fourth session. Dr. Preetha Roslin, SRM University.
The fourth session is on autonomous multi-robot systems. The first topic is on design and development of man-portable class of AUVs for MCM by Dr. Kushal Bhattacharya, NSTL DRDO. He has delivered his insight thoughts on CE mines, modes of operation, operational challenges. He clearly differentiated mine sweeping from mine routing. He stressed the importance of man-portable AUVs. He highlighted the core enabling technologies of AI-driven target recognition, inter-AUV communication, GPS DVL-aided navigation systems. In the second session of AI-enabled underwater systems by Dr. Shibu CDAC, he made visualization of autonomous vehicles, bathymetry survey, and seabed mapping. He mentioned about the core technologies of AI and the comparative analysis of ultrasound-based depth estimation. The AI framework is clearly mentioned from training phase to the edge AI deployment for underwater systems. He also presented his group works on marine image enhancement and detection. The third topic is Mr. Babu Jadhav from CAD DRDO on bio-inspired systems. He briefed about the locomotive concepts in soft bio-inspired robotics. He explained different classes of robotic legs and system stability. He explained about quadrupod and hexapod gates and also showed the visualization of different soft inspire developed by CARE, including snake robots, dual arm robots, and flying robots. The fourth topic is underwater domain awareness by Commodore Divagar, Submarine Operations Indian Navy. He briefed about the different maritime environment for different marine exploration. He explained about the means of surveillance, namely acoustic and non-acoustic. He mentioned about the static and mobile sensors, satellite-based sonars. He focused the key areas from data collection, data analysis, and integration into the national framework. The key takeaway from this session is the need of higher intelligence and autonomy in AUVs and underwater systems. There is a need for seamless technology transfer to happen between all these research institutions so that India's own indigenous vehicles comes into existence with all their research experience, leading to marine operations also successful. The user and operational challenges need to be incorporated while developing the technology in underwater systems. Thank you.
But I still didn't get, madam, what is that you expect, let's say, next action? Research is okay, but do we leave research at research R&D level only? How do we go further? See, I mentioned two contexts. One is a blue economy, other is a defense. Unless we link with one of these two, the R&D is going to be R&D and no further, you go on publishing papers, no one is going to bother about it, right? So question is, how do you link with at least one of the two so that there becomes a push from the government or push from the organizers somewhere in the government setup, okay, this is what we need to do. So I didn't get that kind of a specific
Sir,
thing.
that's what I mentioned in my point, like there need to be a technology transfer between all these research institutions where every institution has its own indigenous capability. So that has to be developed in one particular system.
See, you're not connecting. Why should someone be interested in technology transfer? There has to be a commercial interest, no? See, when you say technology transfer, a lab has developed. So we don't really ask for money for a government lab to transfer the technology, but someone has to take it up. He has to take it up to pay money. So where is that linkage? See, first is we should allow technology transfer. That's a good part. So if you're trying to say that, okay, technology transfer should be made easy, then this comes to the same point what we discussed earlier session, that you create an ecosystem for transfer of technology, and then the industry should make money. If that's what the point, then it's the same thing.
Sir, it is like, no, I'm mentioning about all these institutions who were presented as a keynote speakers today. So every institution has its own capability, so, and it's very unique also. And that has to be implemented in one common system where a complete product comes.
Okay, we'll try to address in different context. Thank you. Thank you, ma'am. Yeah, we'll have Dr. Karthik Selvakumar.
First of all, I thank the opportunity to the director, Professor Balaji sir. As an academician, he knows understanding working between the scientist and academic environment. And I like to thank Professor Dr. P.S. Goyal sir, Padma Shri, and TV Rear Admiral Prasanna ji to allow me to present the recommendation and consideration to carry forward. The first session, session 6th, infrastructure needs. So it was underwater technologies role of tech classification in societies, done by Dr. Ashokendu Samantha IRS. So in this thing, he thought about different rules, regulations, and classifications of different safety procedures and how to build and everything. So here what we have to carry forward, he done about CFD analysis and everything. So what we have to carry forward, instead of going at a late of, like he is risk assessment auditor, we can go as a design stage, implement the rules and procedures. And suppose Ramana sir, he told from IMU, we have a design, we give design something, but later when work output, it will come as a different part. So their part, we have to establish the IRS in the starting stage of design to the end of the product, final part. So what are the carry forward from the first session? Involve classification bodies at the design stage, not just during testing. Develop India-specific codes. So wherever we formulate code, our condition is different than national conditions. So we have to formulate our work according to our conditions. So the codes, so we will be 100% Atmanirbhar of, so we'll be not depend upon other foreign countries. Then the second session has been done by Dr. Ramesh from NIOT, and it is about hyperbaric test facilities. So testing pressure, hulls, components, crew, system under simulated deep sea pressure is non-negotiable. So that's why we have working on Matsya for a very long time. To safety is the main preference. And hyperbaric chamber full scale hull system. So what are the things carry forward? Build, upgrade hyperbaric test facility with both R&D and certification capability. So we can be a part of, for foreign countries, like ISRO is launching satellites. Similar to that, we can be a part of testing facility and certification center toward the world, and linking, create a national facility model, so lab startups, MSME can. So what happened, everyone cannot access to a lab, or everyone cannot develop a laboratory. One particular laboratory with multiple specialty that can be useful for testing and certification. So that can be a NIOT will provide that part. So linking testing data and digital twins to cut. So before design stage, we have different simulation, like not simulation, testing environment, as Professor Goel said. So similar to, we can go for that, and before all the setup done. So uncertainty is everywhere. So uncertainty we may not able to understand, it may come at any point. So we have to focus that point. Not only going for a standard procedure, we can go for some uncertainty too, it may happen. So third part has been done by Dr. G.V. Pavan Kumar, IMU, advancement in research fleet towards ocean exploration and underwater robotics. So what happened, modern research vehicles. So resources in land is very less. Resources in ocean is very huge. So everyone knows who is working on, so from blue economy to we can oils are there, multiple resources available. So working on research vessels, not only for like naval part or defense part, we can go for economy. So who rule ocean, who rule, so our country, in order to improve our GDP, everything, we can more focus towards. So what are the carry point, what we can do? Upgrade research fleet with modular launches. So what happened that some system is damaged. So we have a modular setup that can be replaced any time period, not only for 10 years or 5 years, it can go for more than 15 years, 25 years. So each end, that can be a, we can, our component machines testing facility will be there, that can be fed into one vessel. Only if our component damage, we can replace the component. So like swappable system type, we can do it. So create an open data policy for ocean survey data to boost academy and industry R&D. So some of the part we need money, not only from government, we need to like partners from our industry. So fourth session is indigenous design and development of small submarines, challenges, lessons where that has been done by the L&T, from L&T, Anup Deshmukh, Anaga Deshmukh, and Raju Dahal. So system, what happened, they proposed about submarines, a small type of or miniature version of submarine. So what I have a look, they have started before 2 years, they have said. So miniature version of, like Professor Goel already suggested, there is a no miniature version, what we can do, because whatever available in that, so miniature version of submarine, that whether they want to convey into a small type of research or exploration vessel, or it can be a part, can be used for defense or any research aspect. So that we have to little bit confident, because L&T is more focused, and we can give a confident they may do better result output out of it. What are the carry forward thing we can do it? Prioritize noise reduction as a system level design goal from day one. Fund test rig and simulator before building full prototype. Before building the full prototype, we have to test in a real-time testing environment or simulation environment, that part. So like endurance part, they said battery power packed system. So battery power packed system that we have to work on as an energy background engineer. I am saying battery charging and discharging cycle under different pressure condition or atmospheric, like under oceanic condition, what it may happen, we have to work on more concept on battery system. Specifically, we can go for a battery system management or battery thermal management, and different operating condition we can see. We can engage with the industry or partners, we can collaborate. So common threads of all 4 sessions, we need infrastructure first. So not testing certificate, we need to have an indigenous testing facility, everything, so Atmanirbhar. Then standard safety, we have to follow standard safety in all aspects. So that part we have to do, build as per the Indian standards and codes that we have to follow. Modular, it can satisfy the international standard, but we have to identify what are the uncertainty in our indigenous condition, like many other, like speakers told about various problems. Modularity plus data, take future-proof data, so that can reduce the cost for upgradation. So we can easily upgrade at any very lesser cost system. Ecosystem approach, government, labs, industries, academic, and classification, we can work together in our part. We can, like funding or technical transfer and other part, so that part everyone suggested that version. So it is a mutual beneficial for our nation growth. Jai Hind. Thank you for the opportunity provided.
Thank you very much for a nice summary. Thank you.
Thank you, sir.
Now we'll invite Dr. R. Ramesh.
Good evening to everyone. A group discussion was held on technology gap and indigenization effort of underwater robotic vehicle with eminent scientists, chaired by Dr. Srinivasa Rao, distinguished scientist and Director General retired from the NSTL, and Dr. T. Sandhanakrishnan, Scientist G, NPOL, Commander P.K. Srivastava, Scientist G, Ministry of Earth Sciences, and Dr. S. Ramesh, Scientist G, Deputy Director, NIOT. So we had a detailed discussion and deliberation about the technology gap and indigenization effort. And in India, we know that indigenization of underwater vehicle like ROV, AEV, swarm robots are being developed by various institutions like NSTL, CSIR Lab, NIOT, L&T, and other startups. And we found that the subcomponent like a battery, propulsion, navigation, communication, positioning system, scientific sensor like a multi-beam sonar, synthetic aperture sonar, and HPU motors, most of the components, all are critical component. It's very compact, energy efficient. Mostly we are importing from global market. And the quantity is very, very limited. Hence, the local industry are not interested to build in India. This is what we found in the deliberations. And in the first recommendation is given, we need to make a national level program to develop a compact sensor in the country. Maybe we can, to give a subsidy to the anchor industry like that, we need to make a recommendation, sir, actually. The first one is a national level program for sensor development. And next, all the vehicles, now we are using the imported processor like Intel and Cortex, and we are using an open source for mission planner and the development of software. So we need to have some kind of indigenized architecture to make the processor indigenously, and the mission planner development, like maybe CDAC or other institute, maybe we can involve, maybe we can build our own processor which can capable to run artificial intelligence, other GPUs. So we need to build our own processor for taking care of autonomy, as well as we need to make a software for the mission planner, is the second recommendation, sir. And see, presently, for Matsya, we are using a DNV Germany for classification and certification. Like China and Russia, they build their own code with the help of Lloyd and other agencies. So all the failures happening in the offshore field has to be recorded, and scientific basics has to be developed. Maybe with the experience with the NIOT, maybe we can build a code for developing underwater vehicle like a man-submersible, autonomous underwater vehicle, remotely operated. So in India itself, we need to make a code, rules for the underwater vehicles. Maybe jointly NIOT and IRS shall participate and we can make a code. There are three recommendations we made from our group discussion, sir. First is national level program for sensor development, subsystem development, then indigenization processor and the software development, and classification and certification for underwater robotic vehicle like a Matsya, man-submersible, ROV and AAV, sir. Thank you, sir.
Thank you very much, Ramesh. Very specific recommendation we have made, and that's very important because interfacing is an issue. So we need to solve that in a larger context.
Thank you, sir.
Thank you very much. Okay, the last presentation is from Dr. Sudarshan. Your session probably was much more focused on making recommendations anyway, so that's very important. Thank you.
I think all the technology requirements and what has to be done in future has been very well brought out by all the session chairs and other people. Only in our group discussion, it was basically the technology readiness level and operational experience. Before that, I thought once in 6 months or in a year, the associated R&D, industry, the startup, must meet and discuss with requirements of underwater robotics, especially in the three different directions, like for research, then for the commercial, and for defense application. That is one major point, sir. The technology to be either upgraded from the present one, what are the requirements, or developed in future as a small in-house technology management journal, which DRDO brings out every 3 months or so. It is online available. You can see what is happened in the lab in the last 3 months or 6 months. From each lab, we are supposed to give in, depending on the technology, what is developed. So similar application will help us to know our status in underwater robotics. And also, this Indian Underwater Robotics Society, I was not aware. I think we should all become members and see what can be done, which that is one point which I thought we can share. And also a directory of yellow page where all subsea robots available in Indian scenario at various startups or various R&D labs should be brought out in one small document, which will be available at NIOT in the online or wherever, each laboratory or wherever it is available. The area for concern for industry readiness, yesterday also our DG Naval Systems former Dr. Srinivasa Rao brought, there should be a lead anchor industry for underwater robotics with the CSR funding. It was one recommendation which he made yesterday. With a tax holiday and 5-year, 10-year goal, what should be done? And create a mission mode architecture for an underwater robotics. That was one point. And of course, an integrated approach at the national level. The testing and infrastructure facilities available for this underwater application, combining all the national facilities should be at one place for people to come out for tomorrow. Any startup who want to test their equipment, or it should be available because it is our national test facility. And some incentives for those people for subsea manufacturing, because they are all coming up in the very fast track mode, which I could see from the small, what is called the exhibition, what they have put, like a CDAC who has come out in a very fast track manner. And as finally, I want to say a regulatory authority for training of the people especially in the case of ROV and AUV in future, which we need a continuous regulatory authority for deployment of underwater robotics, or like every time we are having different standards, DNV and other things, we should have our own in-house, what is called the standards for such and such application. So finally, I also felt like RCA, where they have the GOCO model as you brought out, the government owned and company owned. In NPOL, what we do is we give all the facilities available in-house for Keltron to come and do assembly, testing in-house. Because they recruit the manpower and post it into the laboratory, and one of our scientists goes and guides them, especially in the mission mode projects, which immediately once it is completed, it is tested in-house with all the facility, and then transferred to industry in a very fast track manner, and time-boundedly the project gets completed. So similar facility should be available to the industry, like at NIOT or in wherever it is called the GOCO model, the government-owned and company-owned model. So that is one this thing. And also, I hope we have learned the failure of the lessons learned from the Titan, which must be available in the open literature. We should also look at that for future whenever we go for the applications. So this is what I could, and I am very happy that we have an in-house strength, definitely yesterday as the DG NS brought out, which can be used for our technology development, no doubt about that. Thank you, sir.
So there's only 2 points on your presentation. Number one is, you said all facilities to be at one place.
Not at one place.
No.
What I meant is,
maybe I mistook that then.
Sir, no. What I thought is, it should be given to the industry to explore all our facilities available.
Yeah. See,
either in NIOT
NSTL has got a facility.
Yes.
Let them have it. They should make it available.
Yes, yes.
NIOT has got.
NPOL has got a DT test facility.
Yeah.
So all these facilities should be given for the
Secondly, see, GOCO model, when it works when government has a requirement and government also has R&D, whether it's RCI or UNISRO. What we are doing is, see, I am too familiar with the GOCO model with the RCI.
Okay.
See, we are making gyros for missiles. Missile needs gyros.
Yes.
DTG. So what we do, we bring the industry there, they produce it because it's a RCA design, and they give back to RCI.
And infrastructure is given. Yeah.
Now, GOCO model will not work here.
Okay.
I tell you why. Because here the R&D is different unit, whether it is NSTL or whether it is a NIoT. The user will be either, let's say, fishing industry, suppose. If then R&D user is very different. Similarly, if it's a Navy, if Navy's requirement, then
this facility will not.
So the GOCO model has to be modified. It will not be the same as, I'm not trying to say it cannot be done.
It should
we need to have a
meet to our requirements.
We have to modify that GOCO model, which is working in RCI and elsewhere.
And also they have requirements for ISR, so many places it goes.
See, their own requirements, but here it's not so.
That's right.
Okay. Thank you very much. Okay, before we proceed, would like to make any other, okay, I just wanted to really share some thoughts with you. These are recommendations we have made note, and I'm not really going to repeat them again, but just a few comments I'd like to make. See, when we really see as a country, we have to break it up into segments. One is the overall integrators of the technology. Suppose we are talking of a robotics in this case, underwater robotics. Someone is integrating. It could be NSTL because they integrate for the defense requirement. It could be NIoT, which will be, let's say, for microbiology or some of the ocean explorations with respect to geosciences, or NIO. So one is an integrator of these technologies. Now, what integrator needs? They need to have the capability to be able to put all these elements of the technology together. We discussed, okay, they have to have a capability to have a mathematically see everything integration. Nowadays, there are a lot of software available, CATIA and all that, so that you can see every element, integrate on computer. You can see EMI effect on that. You can see various coupling. You can see data transfer, all that you can do. So those things are already available with these labs because they are capable and they have got a lot of money. That is not an issue. So at integrator level, what is missing? Maybe some of these capabilities are imported. For example, hydrodynamics. I'm not very sure whether there is an Indian code available. We are mostly using the code supplied by someone else. Now, that code, whether it's working with respect to all Indian ocean environment and all that, I'm not very sure. So whether we should have a Indian code development by itself, there's one thing I thought we should give an emphasis on that. Correct me if I'm wrong on that, but I understood that most of the time code is all imported. So that's one emphasis. Someone has to develop, whether IIT Chennai or someone IIT Madras or someone else, but we should really put focus on that when it comes to the integrated system. Then it comes to subsystems. Many subsystems are, most of the subsystems are imported. I'm talking subsystems of the robotic itself. I'm not talking of the science component, that comes later. So in that subsystems, whether it's electronic or mechanical, for example, thrusters. In fact, I was very happy today to see that in NIoT, there's one company which has given the original thruster, including the brushless DC motor and the propulsion system. Now, that is a very good thing. Now, can we have such a thing standardized? You can say, see, suppose you want, if you have you want to buy a fan, electric fan, you will find a catalog, and he'll give you, okay, this is small with a 40-inch or something, a 30-inch fan and all that. So you get some standardization in that. Can I have that kind of a standardization on thruster, let us say, and some company can develop that, one or two companies in the country. I was happy to see 2 days back someone, Hyderabad, they have developed now the propulsion system for normal, you can say UAVs, air UAVs. And they have developed at least 5 to 6 different types of propulsion thrusters. And later he says that he's also trying to develop the electrical drive and with a possibility to have a diesel for that, so that long run and all that. Now, can we think of this kind of a development, whatever is not available? So I would like to have a list, someone to prepare a list of which are the things we are importing and take a systematic effort that, okay, this we need to develop with this capability. If you are looking at thruster, define the range. For a robotic of this type, I need 1 kilowatt thruster. With this kind of, one is the power, other is thrust. You have to define both. So can we come up with the specifications? Not general, okay, someone was mentioning today that this is very small, this is very big. No, we have to actually come with a specific numbers. We need a development of a 1 kilowatt or 5 kilowatt thruster with this power and this thrust. Actually, the efficiency will decide relate between the two. So can we come up with that? So someone should do that, come up with a list of equipment to be developed. Now, third thing related to that comes is, then how do we integrate? So very good point has come in the discussion today that you should develop the standards for integration itself. Is it possible? See, when we talk of a satellite, we have actually from the ages, we have been developing, we normally don't take IEEE bus because that is not very safe. There is a one architecture developed long back by us ourselves, which is supposed to be safe set, and we have been testing for last 20 years. We don't change that. Why? Because it works, it never fails. So similarly, can we come up with some kind of a standard for interfacing? Now that's one, so that, today our Navy friends also were suggesting, they have got equipment from France, something else and all that. Can we develop our own standard? And that's something which only R&D units like an IoT or NSTL should together. I would really recommend that we can make a group of experts who can come up with this kind of can we have a integrating software, integrating systems standards. Then other issue comes is the certification. And that has been discussed earlier also, and you also brought this point. Certification capability in IRS, we have to have only one agency. We can't have many certifying agencies. But then they have to come up with a capability. When we were having our own development of Master 6000 here, we engaged DNV. In fact, we were trying to see whether someone could do that or not. But then our effort was that whatever we are learning from DNV, we should transfer to IRS so that IRS gathers that complete know-how, and next time when we develop anything, we don't have to go. So we have to actually enable IRS to be able to certify any future development of robotics with man or without man. That capability, we have to really say very explicitly that if IRS needs some support from the government, they should take our recommendation and say that, look, the scientific community wants us to do this. So this could be another recommendation. The other important recommendation I have in mind is that whenever we lack facility for testing, whether it is a 900 bar or 1200 bar test facility for various components, at what size, because size becomes very important there. So we should not be looking for, we should not be lack of test facility like, as I told, the GTRE engine development. Very openly I'm criticizing an organization which is a very important organization for the country, but I know that there's a issue there. So we should not get into that. So test facilities, doesn't matter where they come, but we should identify which is not available. And let it come anywhere, any government laboratory, whether it's in DRDO, whether Ministry of Earth Science or somewhere else. It doesn't matter. It can be even at IIT. But let the facilities, so can we identify what is not there? We already listed that NIoT is going ahead with the 900 bar as well as 1200 bar facility. Only last issue comes is, what we have not listed that in is a test facility for our Master 6000 sphere, which actually we are going to Russia right now. Now, I personally feel, I'd like to get an endorsement from all of you, that even such huge facility of something like more than 2.5 mm diameter, so that whole capability, that kind of a capacity, whatever may the cost, 100 crore, 150 crore, I don't know the cost, but countries should have that facility. It doesn't matter, Master 6000 will go with Russia, even the second model will go for Russia, but ultimately countries should have this capability because we are going to develop ourselves as a developed country. In fact, we should remove our mind that we are a developing country. We should really aim at, as a developed country, so we should develop these facilities. So is there any other facility if you have, please bring it to the notice. Electronics testing and all that I don't consider an issue. Because that we have done, VMI facility, we have got a number of things, every laboratory has got. So those are not the issue. Specific to my mind, this particular issue is only with respect to the pressure. Otherwise, all facilities, because we have been developing missiles, because we are developing the launch vehicle, we have been doing satellites, all those facilities exist in the country, except probably the pressure. But if there's anything else needed, I think we should really think of that. So these are very specific, which I've captured. But again, I'm inviting, if you have anything else which is left out, please leave a note, small note, or mail to organizers. We will try to consolidate all these things and then put together to the so-called, you can say, policymakers of this country. We'll approach them. But with this, thank you very much, and thanks for the opportunity.
Thank you, sir. Your address reflects the vision of a scientist, institution builder, and the nation builder to strengthen the nation's collective effort towards advancing underwater robotics in India. May I request Professor Balaji Ramakrishnan, our director, to felicitate Padma Shri Dr. P.S. Goyal with a solemn memento. Sir, we are blessed to have a visionary like you with us to have summarized the workshop's key recommendations. Thank you very much, sir. Thank you very much, sir. We now present a brief video showcasing NIOT's successful indigenous homing and docking demonstration and important milestones towards persistent and autonomous underwater operations. May I invite your attention to the screen.
Either of these technically will work. If this is a clear water, we can use the vision light.
Thank you. One of the key highlights of this workshop has been the active participation of students through poster presentation and live demonstrations, showcasing the knowledge, skills, and innovative solutions they developed during this program. We will now watch a short video capturing some of the remarkable student demonstrations, poster presentations, and memorable moments from the workshop.
request Team NIOT 103 to introduce themselves.
Good morning to all. This is Mahesh from IIIT Sri City, Chittoor.
We are from Center of Autonomous Systems and Research Lab. So our main vision and mission of our vehicle is detecting of underwater vegetation using ROV.
Thank you to all the students coming from all the places, from other states and participating and proving your capability. Thank you so much.
Actually, we have invited abstracts from the students. We got a very good response. Actually, 48 abstracts received for poster presentation. 26 we received for demonstration poster presentation. So the results you have seen. Actually, among 48, we screened 19 preliminary screening we did. Then we presented to all the jury member. And subsequently, the demonstration come poster presentation, 26 abstract. With vehicle, we identified only 6 for the preliminary. Whole Sunday we took to see the demonstration. This is the video we have seen. So, and the major theme we kept swarm robotics, underwater communication, guidance, navigation control, homing docking systems, robot for marine biodiversity observations, hybrid vehicle, underwater observation and surveillance, bio-inspired robotic vehicle. This is the theme we kept, in which we got a good response, sir. So we'd like to.
Thank you very much, sir, for summarizing the event. To evaluate these presentations and demonstration, we were privileged to have a panel of jury members whose expertise and guidance really enriched the event. May I now invite the jury member to the stage for felicitation. The jury members are Dr. R. Srinivasan, scientist of NIOT, Mrs. K. Amuda, scientist of NIOT, and Dr. G. Dinesh, scientist of NIOT. Kindly come to the dais. May I request Rear Admiral T.V.N. Prasanna, sir, to kindly present the mementos to the jury members as a token of our appreciation. Ladies and gentlemen, a big round of applause for the jury members.
Thank you, sir. Throughout the workshop, the poster and demonstration sessions showcased exceptional creativity, technical excellence, and innovative thinking from participants and young researchers. I respectfully invite Professor Balaji Ramakrishnan to kindly present the Best Poster Awards. The third prize goes to Kanishk A.L., Hari Prasad, and Samiksha from Vellore Institute of Technology. Their work demonstrates AI-assisted optical beam tracking, physics-based hybrid link simulation, and OOK data transmission, a low-cost prototype study for ROV perception. The second prize goes to Rishikesh and Prasad from Coimbatore Institute of Technology. Their work demonstrated active electrolocation based precision docking system for underwater robotics in zero visibility environments. And the first prize for the poster presentation goes to Ayush Vishnay Aditya Pratap Singh Tomar from Defense Institute of Advanced Technology. Their work entitled GNC Strategies and Algorithms for AUV Docking.
Thank you, sir. We shall now proceed with the presentation for the Best Demonstration Awards. Thank you. For the presentation of the Best Demonstration Awards, may I respectfully invite Padma Shri Dr. P.S. Goyal, sir, to kindly present the Best Demonstration Awards. The third prize goes to Trishit Roy Thakur, Shubham Ranjane, and Bidisha Das. Can you kindly come to the stage? So they are from Weltec University. Their work was on swarm approach flapping tail underwater vehicle for identifying friend or foe. The second prize goes to Ahalya and Sounder K from Jerusalem College of Engineering. For the second prize, the demonstration was on design and implementation of a buoyancy-controlled autonomous underwater vehicle with optical and sensor-based navigation. Second prize to Ahalya and Sounder K. Congratulations. Thank you. And the first prize goes to Yoganath, Sandeep and Magesh. Can we have you on stage? Yoganath, Sandeep and Magesh. Congratulations, a big round of applause to them. They are from Indian Institute of Information Technology, Sri City. They demonstrated on sensor efficient framework for AUV guidance, navigation and control in GPS denied conditions. Congratulations. Congratulations to all the Best Demonstration Award winners. The demonstration showcased practical innovation, engineering excellence, and the spirit of translating ideas into real-world technological solutions. Let us also acknowledge and appreciate every participant whose enthusiasm, innovation, and commitment contributed to the success of this workshop. Thank you very much. Thank you, sir.
Thank you all. As we move towards the conclusion of UWR 2026, I invite Professor Balaji Ramakrishnan, Director INNOVATI, to deliver the closing remarks.
We are delayed by at least an hour, so I would like to be a little short. Dr. Goyal, our mentor, well-wisher, source of inspiration, but I'm sure he made all the session chairs to face the examination. Well, of course, he is a fatherly figure and he has all the reasons to say the recommendations and all that. Prasanna ji, the real spark behind this workshop. That's how I wanted to describe him. And I also appreciate, he attended all the sessions, the whole, through the 2 days, thoroughly, throughout. I think that I really appreciate Prasanna ji, and expert invited speakers, session chairs, participants, students, all my dear NIOT colleagues behind this workshop. Very good evening to all of you. I know this is 2 days of hectic workshop, a lot of deliberations, technology. I think we discussed a lot about all of these topics. But I would like to assure you all, along with the chair of this session, that we will take these recommendations very seriously. All these discussions, the interactions happen during even the breaks, lunch breaks and tea sessions and so on, all the deliberations to collate into a white paper that we are going to come up very soon. And we'll also discuss the way forward very soon. And we would like to inform you that NIOT will be very happy to play any role in this process of building the roadmap for the country's underwater robotic ecosystem and as well as development. Given the responsibility, we have already demonstrated, and given the expertise as well, we'll be very happy to take any role in this, the ventures. And I'm really looking forward, all the institutions who have taken a lot of time and effort to reach out to us, this workshop. I'm really looking forward to work with all on this wonderful journey. And thanks for your support, efforts to join the workshop, and all of suggestions. Good luck and Jai Hind.
Thank you very much, sir. Your vision, encouragement, and leadership has been instrumental in making this workshop a meaningful platform.
As we come to the formal conclusion of this workshop, it is time to express our gratitude to all those whose support and participation made this event a success. May I invite Dr. S.B. Pranesh, Workshop Coordinator, UWR 2026, to propose the vote of thanks.
Good evening, everyone. எனக்கு எப்படி இருக்குன்னா ஒரு பெரிய மழை பெஞ்சு ஓஞ்ச மாதிரி இருக்கு. It's on a positive note actually. There is always a sense of happiness during rain, and we'll wait for the rain to stop to move on to the next activities. Similarly, the workshop on underwater robotics 2026 has come to an end. Though the workshop ends today, it's only a beginning of many more advancements and collaboration in underwater robotics. The workshop started like this. The Maritime Security Wing of the NSCS is in the process of developing a national framework on underwater robotics. As a part of this initiative, the stakeholders meeting was held on 7 January 2026 to deliberate on various aspects of the field and foster coordination among all stakeholders involved in underwater robotic projects across the country. The mission director and director of NIOT participated in the meeting, and following discussion with NSCS, it is proposed to conduct the workshop on 1st and 2nd June 2026 at NIOT Chennai, with the participation from all identified stakeholders. Hence, NIOT has taken up this task on conducting this workshop at NIOT Chennai with the approval of Secretary MOES. I am truly honored to be a part of this event. Feel privileged to propose the vote of thanks on this memorable occasion. First and foremost, I extend my heartfelt gratitude to our esteemed chief guest, Vice Admiral Biswajit Dasgupta, NMDC, for gracing us with this presence and sharing such valuable insights. His words have truly inspired and enlightened us. Heartfelt thanks to Padma Shri Dr. P.S. Goyal, former secretary, and a distinguished personality closely associated with NIOT for decades, for graciously accepting our invitation and presiding as a chief guest for the validity session despite his busy schedule. And thank you very much, sir. I would like to sincerely thank Dr. M.E. Ravanamurthy, Deep Ocean Mission Director, for taking time to join us, for your encouragement address. Your presence has added great value to this event. Also would like to thank Rear Admiral T.V.N. Prasanna, Joint Secretary NSCS, for his presence and introductory address. Our deep appreciation goes to our respected and beloved Director, Professor Balaji Ramakrishnan, whose vision, guidance, constant support made this event possible. Your leadership has been instrumental in making this program a success. Sincere thanks to Deputy Director, Dr. S. Ramesh, and our Group Director, Dr. N. Vedachalam, for their constant support, guidance on daily basis to make this event a Himalayan success. With the presence of seniors as well as our director, I would like to declare this event as a Himalayan success. I would like to thank all speakers, session chairs, co-chairs, and participants who contributed their knowledge, time, and effort. Your contributions have made this event both meaningful and engaging. Special word, tons of thanks to the organizing committee, volunteers. Your dedication, teamwork, behind the scene efforts ensured everything ran smoothly. Thanks to the organizing members. Maybe I'm stopping with the small word, tons of thanks. We will have a separate Thanksgiving session maybe in another 2 days. I also would like to thank our sponsors, partners for their generous support. To our audience and students, thank you for your enthusiastic participation, for being such a wonderful audience, attentive gathering. Your presence made this event lively and worthwhile. At this juncture, I would like to thank Innovatians, estate and team, finance and accounts, establishment and administration, stores and purchase, and CAG team for extending their help for running this event towards a great success. Would like to thank Mr. Srinivas, Om Cinemas for wonderful audio and video setup. As always, self-help group of estate did a wonderful job keeping the campus clean and green. Many thanks to them as well. I thank everyone who directly and indirectly contributed to the success of this program. With this, I conclude my word of thanks. Wish you all a pleasant evening ahead. Thank you very much. Jai Hind.
Thank you very much, sir. I am sure that directors sir present on the dais and other senior scientists will agree that a special appreciation are due to you as well for successfully coordinating and delivering UWR 2026 at such a short notice with remarkable efficiency. Thank you very much, sir. Ladies and gentlemen, nation comes foremost. May I request all of you to stand for the national anthem.
पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उत्सव जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगल गायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे जन गण
Thank you all for joining us. We wish you a safe journey home and look forward to meeting again in future collaborations. Thank you one and all.
Jai Hind.